Algorithms are everywhere. Whether you are writing software, analyzing a genome, predicting traffic jams, producing automatic movie recommendations, or just surfing the internet, you're dealing with algorithms. Every single branch of computer science uses algorithms, so a course on algorithms and data structures is an essential part of any CS curriculum.
It's important that the algorithms we use are efficient, as users want to see the search results in the blink of an eye, even if they search through trillions of web pages. A poorly thought out algorithm could take literally centuries to process all the web pages indexed by a search engine, or all the Facebook posts. And thus, algorithmic improvements are necessary to make these systems practical. That's why tech companies always ask lots of algorithmic questions at the interviews.
In data science problems, like ranking internet search results, predicting road accidents, and recommending movies to users, advanced algorithms are used to achieve excellent search quality, high prediction accuracy, and to make relevant recommendations. However, even for a simple machine learning algorithm like linear regression, to be able to process big data is usually a challenge. When advanced algorithms such as deep neural networks are applied to huge datasets, they make extremely accurate predictions, recently starting to even outperform humans in some areas of vision and speech recognition. But getting those algorithms to work in hours instead of years on a large dataset is hard, and performing experiments quickly is crucial in data science.
Algorithms are everywhere. Each of trillions of cells in your body executes a complex and still poorly understood algorithm. And algorithms are the key for solving important biomedical problems, such as what are the mutations that differentiate you from me and how they relate to disease. In this specialization, you will learn the theory behind algorithms, implement algorithms in a programming language of your choice, and apply them to solving practical problems such as assembling a genome from millions of tiny fragments, the largest jigsaw puzzle ever assembled by humans.
To conclude, algorithms are everywhere, and it is important to design new algorithms and to implement them. To turn you into a pro in algorithm design, we will give you nearly 100 programming assignments in this class. Your solutions will be checked automatically, and you will learn how to implement, test and debug fast algorithms, solving large and difficult problems in seconds. We look forward to seeing you in this class. We know it will make you a better programmer.
Algorithms are everywhere. In fact, you just saw 5 algorithms solving the fundamental sorting problem in computer science, and they all have different running times. In fact, while 4 of them are about to finish, one will take a much longer time. In this specialization, you'll be able to implement all of these algorithms and master the skill of answering both algorithmic and programming questions at your next interview.
Hi! In this short video we will solve a code problem together. The problem itself is quite elementary, so the main purpose of this video is to show you the general pipeline of solving code problems in this class. The problem is called a plus b. In this problem we are given 2 digits on the standard input, and our goal is to output their sum on the standard output. You can see 2 sample tests here on the page. For example, if the input for your program consists of 2 integers 3 and 2, then your program should output 5. If on the other hand the input consists of 2 integers 7 and 9, then your program is supposed to output 16, of course. The next section consists of 3 starter files, which in this particular case are actually solutions, not just starter files. So the files are for programming languages Python, Java and C++. Finally, the last section contains an instruction consisting of 4 steps on how to solve this problem. So let's go through these 4 steps together. The first step is to download one of the starter files. For this, let's select the C++ starter file and let's download it. Okay. Now the file is here, and let's take a look inside. So this is a very simple solution which first creates 3 variables, then it reads A and B from the standard input, then it computes the sum, and then finally it outputs the sum on the standard output. So to run this program we first need to compile it. So this is the second step of our instruction. For this we highly recommend to use the same compiler flags that are shown on this page. This will ensure that your program behaves in the same way on the testing system and on your local machine. So in this case let's just copy the flags and use it to compile our program. So this produced an executable file A-out, and we can now run it. Let's give this program, for example, 2 and 3. So the output is 5. Well, one more test, for example, 9 and 4. The output is 13 as expected. So far so good. And now the next step is to actually submit this solution to this problem. Let's go to my submission tab, press create submission, then replace a file by this CPP file, and press the submit button. So after a while the testing system shows that our solution passed all the tests, which is quite satisfactory. In this particular case, the grader output is empty, meaning that there is no error message in this case. To illustrate it one more time, let me repeat the whole procedure quickly for the Python programming language. So we first download the starter Python file. Let's take a look what is inside. So the program is again very simple as expected. So we just take A and B from the standard input, and we output the sum of A and B. Now we need to run this program. For this you might want to go to this available programming languages page again, just to check how we compile, how we run actually Python scripts. So we just use Python 3. So let's do this. For example, 4, and the output is 8. So which is as expected. So let's just go ahead and submit this solution. So you go to my submission tab, you press the create submission button, and then you replace this file by a+b pi. So when the file is uploaded, you finally press the submit button. So in a few seconds, this solution will be accepted by the testing system. Well, this wasn't very challenging, right? In the next video, we will see a much more interesting example of a computational problem. For this problem, we will start with a naive solution. We will submit this solution to a testing system to figure out that it is buggy actually, that there is a bug. So we will fix this bug, submit it again to find out that our solution is slow. We will get a time limit exceeded feedback message from the testing system, meaning that for large data sets, it works in more than 1 second, for example. So this will require us to come up with a much more faster solution. We will implement it, submit it to the system again to find out that it is still buggy. We will use stress testing to locate the bug, to fix it, and to finally submit a correct solution to the system, which will pass all the tests. In this video, we will consider a more interesting code problem. this problem will require us to implement a faster than a naive solution, first then to debug it, then to stress test it, before we actually come up with a correct solution that will be able to pass all the tests in the testing system. So the problem is called the maximum pairwise product problem. In this problem, we're given an array or a sequence of n numbers, and our goal is to find a number which can be obtained by multiplying some two numbers from this sequence. So recall that our problem is given a sequence of n non-negative integers to find the maximum pairwise product. So the input to this problem consists of two lines. The first line contains just a single number n, which is at least 2 and at most 2 multiplied by 10 to the 5. The next line contains the sequence of n numbers, which are non-negative integers not exceeding 10 to the 5. So our goal is to output a single number, the maximum pairwise product. The page contains also two sample tests. For example, if an input to our program is a sequence of length 3 consisting of numbers 1, 2, 3, then the output should be of course 6, because this is just 2 multiplied by 3. For a slightly longer sequence of size 10, the output should be 140, and this is 10 multiplied by 14. So as usual, there is also a section that contains starter files, and let's again choose C++ as our programming language for this problem. This is how the starter C++ solution file looks like. So we start by reading the number n from the standard input. We then create an array or a vector of size n. We then fill in this vector by elements of our sequence, element by element, that we read from the standard input. We then pass the array numbers to the function max pairwise product that computes the answer to our problem. Let's see what is going on inside the function max pairwise product. So we start by initializing the variable result by 0, and we then go through all possible pairs of different elements. That is, we go through all possible I and j, where I is less than j. We do this by two nested loops. And for each such pair, we check whether the product of the corresponding two numbers is greater than our current result. And if it is, we update the result. Finally, we return the result. So this algorithm is correct for an obvious reason. The goal in our problem is to find the maximum pairwise product, right? So to do this, we just go through all possible pairs and select the maximum product. Okay, to check that it is indeed correct, let's, as usual, compile it. So for this, we use the compiler Flux for C++. Okay, and then we test it. For example, for the sequence of length 3 consisting of numbers 1, 2, 3, the answer is 6. Let's test it one more time. For example, this sequence of length 5 consisting of numbers 3, 4, 5, 1, 2. So the answer is 20, as expected, because this is the product of 4 and 5. Okay, so it seems that this solution is correct, and let's just go ahead and submit it as a solution to the testing system. So I've just submitted our current solution to the grading system, and unfortunately it hasn't passed all the tests. In particular, there is an error message shown in the grading system. Let's take a look. So it says that our solution failed test case number 3, which consists of just two numbers. The first one is 10 to the 5, and the second one is 90,000. Let's check whether we can reproduce this behavior on our local machine. So let's call our program with just two numbers, 10 to the 5 and 90,000. So indeed, as a result, instead of getting 9 billions as we would expect, we got some random number. So this usually happens when there is an integer overflow. And indeed, so we use the standard integer type for storing the result of multiplying two numbers, while 9 billion is too much for the integer type, so it doesn't fit into the integer type. So what we are supposed to do is actually to use the long C++ type. So let's do this and check whether this will fix our problem, our solution. So for this we need to change all the places where we compute the result, compute and store the result. So first of all, we change the declaration of this variable. We change also the type of the returned result. When computing the product of these two numbers, we first cast, for example, the first one to the long type. Okay, and also here. Great. Let's now compile it once again. Yes, and let's run it to check whether it correctly processes our previous data set. So 10 to the 5 and 90,000. Great. So it correctly outputs 9 billion. So now we must be completely sure that our solution is correct, because, well, first of all, to find the maximum pairwise product, we just go through all possible pairs and select the maximum product. So what can we do else? And also we now use the right type for storing the solution, for storing the result. So let's go ahead and submit our new solution to the grading system. Unfortunately, our solution is still incorrect. So in this particular case, the output of the grading system is the following: failed case 4, time limit exceeded. So it means that our solution is quite slow, that for large data sets it runs in more than 1 second. So let's try to understand why it so happens. First of all, the maximum size of a data set, the maximum size of a sequence for this problem in our case is roughly 10 to the 5. So what is the number of operations performed by our algorithm on such a sequence? So recall that in our algorithm we just go through all possible pairs of input numbers. So this is roughly n squared. So when n is equal to 10 to the 5, this is 10 to the 10. And this is more than 1 billion, and 1 billion is roughly the number of basic operations that modern computers can perform in 1 second. So we conclude that we need a faster algorithm to solve this problem. In particular, we realize that we need to find the maximum pairwise product without actually going through all possible pairs of numbers. So in search of an inspiration, let's take a look at the problem page. In particular, let's review the second sample case. In this case, our input consists of 10 integers. And the output in this case is 140. And why is that? Well, this is just because in our sequence there are two numbers, 14 and 10. And these two numbers are two maximal numbers, actually. So for any other two numbers, their product are less than 140. So this gives us an idea that to find the maximal product of two numbers from our sequence, it is actually enough to find two maximal numbers in our sequence. This is because all our integers in the sequence are non-negative. So let's just implement this idea in our C++ file. So this is already implemented, and it looks as follows. So the new function is called max pairwise product fast. So it already uses the long type for storing the result, and we do the following. Just by scanning the input array 2 times, we find two maximal numbers. So in the first block, we find the first maximum, and we store its index in the max index variable. And in the second block, we find the second maximal element. So the difference in the second block is that we also need to skip the first maximal element while scanning the array. So we do this in this check. Okay, and then in the end we just return the product of two maximum numbers in our array. Right? Let's as usual compile it and see that everything works correctly. So this is our new file, max pairwise product fast cpp. We compile it and we first run it on some small sequence, for example of size 3, for example 2, 3, 4. It gives us 12 as expected. Right, now let's do the following. Let's check what is the running time on a huge data set. So for this, let's, instead of reading the data from the standard input, let's just generate a huge array here. Let's use vector of int of size 10 to the 5. And let it be an array filled by zeros. Let's compile it and let's run it. So it outputs 0 immediately, which means that it is much faster than the previous algorithm. So now our solution just must be completely correct. So it is fast, it uses the right type for storing the solution, and it is also obviously correct because, well, it selects two maximal numbers, right, and multiplies them. No other product of two numbers can be larger because we selected two maximal numbers. However, unfortunately, even this solution is not correct. So you can submit it to the testing system and see that the output will be wrong answer for some test case. In the next video, Michael will tell you about stress testing and will show you how to fix this solution.
The previous video ended on an unsuccessful attempt to submit our solution to the max pairwise product problem. Even worse, we don't know what is the test on which our program fails because the system doesn't show it to us. This is actually a pretty standard situation when solving algorithmic programming assignments. In this and next few videos, you will learn how to overcome this situation and to even avoid it in the first place. I will explain to you and show you in action a powerful technique called stress testing. By the end, you will be able to implement a stress test for your solution of an algorithmic problem, use it to find a small and easy test on which your program fails, debug your program, and make sure it works correctly afterwards with high confidence. Also, you will be able to list and apply the set of standard testing techniques which should be always applied when solving algorithmic programming assignments. So, what is stress testing? In general, it is a program that generates random tests in an infinite loop, and for each test, it launches your solution on this test and an alternative solution on the same test and compares the results. This alternative solution you also have to invent and implement yourself, but it is usually easy because it can be any simple, slow brute force solution or just any other solution that you can come up with. The only requirement is that it should be significantly different from your main solution. Then you just wait until you find a test on which your solutions differ. If one of them is correct and another is wrong, then it is guaranteed to happen, because there is some test for which your wrong solution gives wrong answer and your correct solution gives correct answer, and so they differ. If, however, both of your solutions are wrong, which also happens often, they are still almost guaranteed to have some test on which one of them gives wrong answer and another one gives correct answer, because they are probably wrong in different places. When you find a test on which your solution's answers differ, you can determine which one of them returns wrong answer and debug it, fix it, and then repeat the stress testing. Now let's look at the practical implementation. I've already implemented the stress test for this problem. It is in the file called stresstest.cpp. Let's look into that. So it is almost the same as the solution that we've sent last in the previous video, but I've added some things. First, we add this include cstdlib, and this include file just allows us to use a part of standard library to generate some random numbers, and we'll use it to generate some random tests automatically. Then we have the same code of two functions, max pairwise product and max pairwise product fast, which we used in our last solution, which we submitted in the system. But now in the main function we have a whole additional while loop. Here it is. And this is where the stress test itself is. So what do we do in principle is we generate some random tests, then we launch both solutions, max pairs product and max pairwise product fast, on this random test, and we compare the results. And the idea is, if you have a correct solution and another correct solution, and the correct answer for your problem is the only correct answer, then any two correct solutions will give the same answers for any test. And if you have some wrong solution and some correct solution, then on some tests their answers will differ. And also, if you have two wrong solutions, then probably they are wrong in a different way. And then there will also be some test, hopefully, on which their answers differ. If you generate a lot of tests, then with some probability at some point you will generate a test for which the answers of the solutions differ. You can detect that situation and then look at the input test and at the answers. Then you can determine which of the algorithms was right and which was wrong. Maybe both were wrong, but anyway you will find at least one of the algorithms which are wrong, because if their answers are different, then at least one of them gives wrong answer. And then you will be able to debug that algorithm, fix the bug, and then run the stress test again. And either you will again find some difference, or you won't find any difference anymore, and then hopefully you fixed all the bugs in all the solutions, and you can submit it. So, how it works in practice? First, we need to generate the test for our problem. We start with generating number n, the number of numbers, and our solution, our problem states that n should be at least 2. So we first generate a big random number using function rand. Then we take it modulo 10, and it gives us some random number between 0 and 9, and then we add 2, and so we get a random number between 2 and 11. Why is it so small? Well, we first want both our solutions to work fast enough, and also if we create a big random test, it will be hard for us to debug it, so we start with some relatively small value of n. We immediately output it on the screen, so that if we find some test for which our solution is wrong, we immediately see it on the screen. After generating n, we should generate the array of numbers a itself. So we iterate n times, and we add random numbers from 0 to 99,999 to the end of array A. So these are the numbers in the range which is allowed. And then we also output all these numbers in one line separated by spaces and a new line character. So by this time we've already output the whole input test on the screen. Now what we need to do is actually to launch both our solutions on this input test and get two results, the results of the naive solution and the results of the fast solution. After that we compare those two results. If they are different, it means that at least one of the solutions was wrong. So we output words wrong answer on the screen, and we also output the first result, the space, and the second result, and a new line character. After that we break our loop. You can notice that our while loop is a so-called infinite loop, but we actually end it as soon as we find some test for which our solutions differ. If we don't find that they differ on some tests, we just output word OK on the screen to denote that actually both solutions have already computed the answers, but the answers are the same, and then we continue. So we continue our infinite loop in the search of the test that will save us, that we can use to debug our solution. And we wrote that code just in front of all the code to read the numbers from the input, to compute the answer, and to output it to the screen. So we basically inserted this code in our regular program, but instead of reading numbers from the input, it will first try to find the test for which our two solutions differ. And in the next video, we will launch the stress test to find a test on which our solutions differ, debug our fast solution, and fix it. In this video, we will launch the stress test to find a test on which our main solution and alternative solutions differ, use this test to debug our main solution, and fix it. So we save the file. Now we will compile this file because we will want to run it, and to compile this file we go to the section solving programming assignments. We look at the C++ flags, copy them, and then use them to compile our file. We also, of course, specify which file we want to compile, and also the name for the output file will be stress test without .cpp. So we compile our stress test and then we launch it and see what happens. So we see our screen was filled with a lot of lines. Actually, those lines were words OK and some numbers like number n from 2 to 11 and input numbers which are big. And there are a lot of tests for which our solutions didn't differ, and that all went pretty fast. And then in the end we have number 11, which is n, and then 11 big numbers, which is the input test, and then the words wrong answer, and two very big numbers which are different, which are the answers correspondingly of the first and the second solution we implemented. So now we already have a test on which at least one of our solution wrongs incorrectly. But it is very hard to work with this test because we have 11 numbers and they are very big, and the answer to this problem is even bigger. So let us try to find a smaller test on which our solution still fails. Usually we can create a very small test with this technique. So let's go back to our code, stresstest.cpp, and let's decrease the restrictions on n and on the numbers. So for example, we want our number n to be no more than 5. Then we first generate a random number modulo 4, so it will be from 0 to 3, and then after adding 2 it will be from 2 to 5. And also we want our numbers to be less than 10, so we just generate numbers modulo 10. And that's everything we change. Now we save the file, we recompile with the same options, and we again launch our stress test. Now we found a test on which solutions differ even faster. Only maybe 5 or 7 tests were okay, and now we have a test with 5 numbers, which are 2, 9, 3, 1 and 9, on which our solutions differ. And the answer of the first solution is 81, and the answer of the second solution is 27. Which one of those is correct? Of course, the first one is correct, because we have numbers 9 and second 9, which are the biggest in the input, and their product is 81. So our first naive solution gives a correct answer, but our second fast solution gives an incorrect answer. And let's think why that can be. Well, that can be if it multiplies wrong numbers from the array. So let's go back in the code and check which are those numbers. We again go into the code and we look into the code for function max pairwise product fast. It's very convenient that we have a separate function for this solution because the error should be localized somewhere here. So to simplify our goal of debugging, let's output the indices of the maximum number and of the second maximum number that at least this function thinks are two maximums in the array. So we output them to cout. First the first index, then a space to separate them, then the second index, and then new line character. So we save our program, we again recompile it, and we again launch the stress test. So note that although we generate random tests, it is safe to launch our stress test again, because those are pseudo-random. The sequence of generated random values is the same. So this is a reproducible test. So now again we have the same test on which two solutions differ with 5 numbers, the same 5 numbers. And now under the line with 5 numbers we have another line which says 1, 2. This is actually our debug output, which means that the index of the first number which is maximum is 1, and it corresponds to number 9 because we numerate our numbers from 0 in our C++ arrays. And the second number has index 2, and this is number 3, again because we numerate from 0. So our fast solution thinks that the second maximum number in the array is number 3 instead of number 9, which is in position 4. So let's go back to the code and see why it happens. Again, we open the file with the code, we go to the function max pairwise product fast, we ignore the code for the maximum index 1, and we're very interested in the code for maximum index 2. So now let's look at this complex if expression where we try to determine whether number at position j may be a new maximum which is different from the maximum we've already found. And let's look more closely at this particular first condition. So here what we do is we check that number at position number j is different from the maximum we've already found. But that's exactly the problem. What we need is instead that j is different from max index 1, because we don't want to find the same number, but we can find number which is equal to the first found maximum. So instead of this comparison, what we actually need is to compare j to max index 1. If we fix our code this way, then we will be at least able to find the second number 9 in our input array 29319, which we saw. So let's see how it goes after we fix this. So we save the file, we again recompile it with the same options, and we launch our stress test. So now what we see is a screen which is very quickly filling with some numbers and words OK, and then some numbers again and words OK. And we should wait for some time, for maybe 10 seconds or even 30 seconds to be sure that we cannot find a test on which our solutions differ, but by now it seems that that is the case. And in the next video we will do more testing and then submit our main solution to the system and see how it goes. In this video, we will do more testing first, and then submit our main solution to the system and see how it goes. By the end, you will be fully prepared to test your programming assignments in the future. For some small tests with a small n and small numbers, we cannot actually find any test in which our solutions differ. That doesn't yet mean that both our solutions work. Maybe they will break for bigger values of n or for bigger values of the input numbers. Let's check for that. So we stop our program with Ctrl+C. We go into the code again, and we increase back the restrictions on n and on the numbers. For example, n will be up to 100, and the numbers will be up to 100,000, the maximum value permitted in the problem statement. We save the code, recompile, launch the stress test again, and now we see that again our screen is filling with numbers and sometimes words OK, but there are many more numbers in each test, and the numbers are bigger, and still we're waiting and waiting, and nothing happens. Our program just proceeds filling the screen with OKs. So maybe it works, or maybe we can test for even bigger values of n, because the numbers we used for testing are already big, but n is not that big yet. So let's estimate what is the value of n for which we still can test. Our slow solution works in quadratic time, so testing on 100,000 numbers would be probably too long. So maybe we can test for a value of n up to 1000. Let's do that. Recompile, launch the stress test again. So now our screen is almost completely filled with numbers, but we will know if we find a test on which our program breaks, because it will then stop. And as soon as it doesn't stop and proceeds filling our screen with numbers, it means that for all those tests everything works correctly. So by now we're pretty sure that our solution should work correctly. We stop the stress test, and now we want to make it back a solution to the initial problem, not a stress test. And to do that, we go to the main function and we comment out the while loop, which implements the stress test. Okay, and now everything else in the main loop is the solution of the initial problem. So that's it. We can probably already submit this file. So let's save it, and just in case recompile it and test it on some simple test case. For example, we input number 2 as the two numbers, and then 3 and 5 as the input numbers. What we see is, instead of just number 15 on the screen, we also see some number 1 and 0. And what is that? Well, disregarding what is that, if we submitted this exact solution to the system, we would get an incorrect result on the first test we encounter in the system, because we only have to output the correct answer to the problem and nothing else to their output. And that is a very frequent mistake that people do in their first programming assignments, so please be aware of that. Please only output what is stated in the problem statement, and nothing more than that, nothing less than that. So in this case we only need to output number 15. So let's fix this additional output. Now we probably already guessed that this additional output is this debug output of indices, which our fast solution finds. So let's comment this also out, save the file, recompile, and launch our program again, and then input the same test. And now we see that it only output 15, which is the correct answer. So now we're pretty safe. We can try to submit that solution to Coursera, actually. So let's go and do that. So we create a new submission, and we upload the file. File is stresstest.cpp. That is the file with which we worked right now. We wait for it to upload, and then we submit. And now we have to wait for the grader to grade our solution. And great, it passed in the system. This illustrates the stress testing technique, but let us give you some additional advice. First, you noticed that the stress test magically gave us the test on which our main solution and alternative solution differed very quickly. But that's not always the case. For example, in this problem, max-pairwise product, the only test cases on which our main and alternative solution differed were the test cases where the two biggest numbers are the same. And that's a rare event, especially when you generate big random numbers from 0 to 100,000. So we were actually lucky to quickly generate such a test. And that's true in the general case. Often the cases when there are equal numbers are some kinds of corner cases. Also the same happens when you are working, for example, with strings of Latin letters, and the cases where the strings only contain one letter A, or only contain two different letters, for example A and B, as opposed to strings which can contain arbitrary Latin letters. Those cases with only few different letters are sometimes corner cases. So, when you want to do stress testing and you cannot find quickly a test on which your main solution and alternative solution differ, try to generate tests in a more focused subspace of all possible tests. For example, if you are working with graphs, try generating a disconnected graph, a full graph, a bipartite graph. Another important point is that if you found a test on which your solutions differ, don't hurry to debug something. First, try to generate the smallest and easiest test on which your solutions differ. This will simplify your debugging a lot. Don't expect stress testing to be a silver bullet. For example, it probably won't find out that your main solution is too slow, because your alternative solution will probably be even slower, some brute force solution, and you will have to generate only small random tests to compare them. Another case is integer overflow. Even if you generate random tests with big numbers, both of your solutions could potentially have integer overflow problems, and then you will not notice that your main solution has them in the stress test. So first, test for those cases and then apply stress testing. However, if you've done manual tests, integer overflow testing and max test, and then apply stress testing, you're almost guaranteed to have success with it, because the authors of the problem do basically the same when they make the test sets for you. They make some manual tests, they make tests with big numbers for integer overflow, they make big tests for checking time limit, and then they generate some random tests and maybe some focused random tests, but that's all. So you'll probably find all the traps they've set up for you with stress testing. In conclusion, know that it is very important to write programs that work on all the allowed test cases, not just on most of the allowed test cases. In practice, if you write programs with bugs that only rarely reveal themselves, still some of your users will encounter those bugs and their experience will deteriorate significantly. Also, sometimes in the start of the project you want to test some hypothesis and you write some code to check it. And then you get some results and base your decisions on that result, only to later learn that you had a bug in the code and all your decisions were wrong. That's why we've prepared thorough test suites to check all the aspects of your problems. And here, stress testing will be very helpful when your solution fails on some test and you don't even know what is the test on which your program fails. We hide the tests on purpose. In real life, you often also won't know what are the exact conditions under which your program fails. But now you are fully prepared to test your programs, debug them, and fix them.
Hello everybody, I'm Daniel Kane. Welcome to the Data Structures and Algorithms specialization. For this very first lecture, we're going to start at the very beginning and talk about why do you need to study algorithms in the first place. So the basic goal in this lecture is to sort of talk about what are the sorts of problems that we're going to be discussing in this algorithms class and why they're important. And in the context of doing this, we're also going to discuss some problems that you might run into when writing computer programs that might not actually require sophisticated techniques that we'll be discussing in this course. And on the other hand, we'll discuss some other sorts of problems that you might want to solve that go beyond the sort of material that we will be talking about here. So, to begin with, suppose that you're writing a computer program. There are a lot of tasks that you might want to perform that you don't really need to think about very hard. These are things like displaying a given text on the screen, or copying a file from one location to another, or searching a file for a given word. each of these algorithms has essentially a linear scan. You go through every word in the file one at a time, and you do the appropriate thing. And for each of these problems, there's essentially a linear scan that you really can't do much better than. In order to do whatever task it is you're doing, you have to go through all of the data one at a time and process it appropriately. And so when you do more or less the obvious thing, you have a program that works, it solves the problem that you need, and it does so approximately as efficiently as you could expect. So for these sorts of problems, you might not have to think very hard about what algorithm you are using. On the other hand, there are some other problems, actual algorithms problems, where it's not so clear what it is you need to do. For example, you might be given a map and need to find the shortest path between two locations on this map. Or you might be trying to find the best pairing between students in dorm rooms given some sort of list of preferences. Or you might be trying to measure the similarity of two different documents. Now, for these problems, it's a lot more complicated. It's not immediately clear how to solve these problems, and even when you do come up with solutions, often the simple solutions to these problems are going to be far too slow. You could end up with some simple algorithm. You could try all possible pairings between people in dorm rooms and return the one that optimizes some function that you're trying to deal with. On the other hand, if you did that, it would probably take a very, very, very long time. And you might not have enough time to wait, and so you might need to do something better. And then, even once you have a reasonably efficient algorithm for these problems, there's often a lot of room for further optimization. Improve things so that things run in an hour rather than a day, or a minute rather than an hour, or a second rather than a minute. And all of these improvements will have a large effect on how useful this program you've written is. Now, on the other hand, there are some things that you might want to try and do with your computer that go a little bit beyond the sort of things we're discussing in this course. We might want to call these artificial intelligence problems. And these are problems where it's sort of hard to clearly state what it is that you're trying to do. An example of this might be to try and write a computer program to understand natural language. That is, write a program where I can type something in, some English sentence, asking it, what's the price of milk at the local food store today? And you want the computer to then take this sentence that I wrote and figure out what it means, figure out some way to parse it, and then do an appropriate lookup and return a useful answer to me. And the problem with doing this isn't so much that anything involved here is actually difficult to perform, but the problem is that fundamentally we don't really understand what it means to interpret an English sentence. Now, we can all speak English, hopefully, if you're listening to this lecture, but we don't sort of really fundamentally understand what it means. It's hard to put it into precise enough language that you can actually write a computer program to do that. Now, you have similar problems, like if you want to identify objects in a photograph. If you've got a picture with maybe a dog and a tree and a cloud, and you want a computer to identify what's what, then once again, this is a thing that our brains have gotten very good at doing, and we understand what the question is. However, it's hard to really put into words how you identify that this thing's a dog and this thing's a tree, and this sort of business makes it very difficult to teach a computer to do the same thing. Another thing that you might want to do is teach a computer to play games well, like play chess effectively. And once again, this is a thing where we can sort of identify what it means to do this, but actually how you want to do it, there's a lot of sort of very vague, intuitive things that go on there. It's not a clearly defined problem that you're trying to solve. And so, for all of these problems, sort of the difficulty is not so much that it's hard to do things quickly, but it's hard to even state what it is that you're trying to do and figure out how to approach it. Now, these are problems that we're not going to really cover in this class. We're going to focus on algorithms, how to do things quickly and efficiently. But if you do want to get into AI and want to try and solve these problems, it will be very important that you have a solid grounding in algorithms so that once you have some idea of what does it mean to identify trees in pictures, you will have an idea of what sort of algorithms can actually support these ideas, which sort of ideas you can actually implement in a reasonable amount of time. And so what we're going to focus on these course are the algorithms problems. So we want problems that are cleanly formulated, like clear mathematical problems. And some of the things we looked at maybe aren't immediately clear, like if you want to find the shortest route between 2 points on a map, that's not immediately a math problem, but pretty quickly you can interpret it as such. You can say, well, I want some sequence of intersections I'm traveling between, such that each pair is connected by a road, and the sum of the lengths of the roads is as small as possible. And so pretty quickly this just becomes a problem where we can very clearly state what it is that we're trying to do, but for which it is still non-trivial to solve it. And so that's the sort of thing we're going to be talking about in this class, and hopefully by the end of it you will have a good idea of how to solve these problems, how to write programs that will solve them very quickly and very efficiently. And that's what we'll be talking about. I hope you enjoy the rest of the class. Hello everybody, welcome back to the Data Structures and Algorithms specialization. Here I just want to give you sort of a brief heads up about what we're going to be talking about in the next 2 lectures. So in the next 2 lectures we're going to dive right in and we're going to look into a couple of algorithms problems. In particular, we're going to talk about algorithms for computing Fibonacci numbers and algorithms for computing greatest common divisors. Now, these might feel a little bit weird for the very first algorithms that we're going to talk to you in a class. They're kind of number theoretic and numerical, and they won't actually be that similar to what we'll be talking about in the rest of the class. So you might wonder why we're looking at them and what you should be paying attention to. And that's really what I want to talk to you today about. In particular, these 2 topics were chosen because they were the clearest examples we could think of for why algorithms are critically important, why coming up with a good algorithm is really so important on so many problems. And in particular, both of these problems have the following very interesting properties. To begin with, both of these problems have a pretty straightforward algorithm. One where you sort of take the definition of the problem that you're trying to solve, and from that you more or less immediately extract an algorithm. You sort of take the words that you have and you sort of interpret them as an algorithm, and more or less immediately you have some code and it works and it computes the things that you want it to compute. Unfortunately, in both cases, these very straightforward algorithms are far, far too slow. You end up with algorithms that take thousands of years to run, even on very modest inputs. And this is not acceptable for practical purposes. You really don't have millennia to wait for your computation to finish, and so you need something better. And it turns out, in both of these cases, there is something better. There's going to be a slightly more complicated algorithm, something that maybe requires 1 or 2 bright ideas to get it to work. This slightly more complicated algorithm works fine and is actually incredibly fast. You can handle sort of any reasonable instance of these problems in the blink of an eye. And so the whole point of this is to really show with these very concrete examples that, at least in these instances and in many others that we'll see throughout the course, finding the right algorithm can make all the difference in the world. It's the difference between having an algorithm that takes more time than you will have in your life to finish, and an algorithm that is done before you even knew it started. And so really this is what you should be paying attention to, why it is so important that we find good algorithms. So that's what's coming up. I hope you enjoy the next couple of lectures. Hello everybody, welcome back. Today we're going to start talking about Fibonacci numbers and algorithms to compute them. In particular, in this lecture, we're just going to introduce the sequence of Fibonacci numbers and talk a little bit about their properties. So, to begin with, the Fibonacci numbers is a fairly classically studied sequence of natural numbers. The 0th element of the sequence is 0, the first element is 1, and from there on, each element is the sum of the previous 2. So 0 and 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and then the sequence continues, 8, 13, 21, 34, and so on. So it's a nice sequence of numbers defined by some pretty simple recursive rule. And it's interesting for a number of reasons. It has some interesting number theoretic properties. But originally, this sequence was developed by an Italian mathematician as a mathematical model. And it's a little bit weird. You might try and wonder what sorts of things this could be a model for. Well, it turns out that originally this was used as sort of a mathematical model for rabbit populations. There was some idea that if you had a pair of rabbits, it would take them one generation to mature, and every generation thereafter they'd produce a pair of offspring. And if you work out what this means, then you find out that the Fibonacci numbers tell you how many pairs of rabbits you have after n generations. Now, because rabbits are known for reproducing rather quickly, you might assume that this sequence therefore grows quickly. And in fact, it does. It's not hard to show that the nth Fibonacci number is at least 2 to the n over 2 for all n at least 6. And the proof can be made by induction. You prove this directly for n 6 or 7 just by computing the numbers and showing that they're big enough. And after that point, f of n is the sum of fn minus 1 and fn minus 2. By the inductive hypothesis, you bound that below and do a little bit of arithmetic, and it's bounded below by 2 to the n over 2. So that completes the proof. In fact, with a little bit more work, you can actually get a formula for the nth Fibonacci number as roughly 1 square root of 5 over 2 to the n. These things grow exponentially quickly. And to sort of drive that home a little bit more, we can look at some examples. The 20th Fibonacci number is 6,765. The 50th Fibonacci number is approximately 12 billion. The 100th Fibonacci number is much, much bigger than that. And the 500th Fibonacci number is this monster with something like 100 digits to it. So these numbers do get rather large quite quickly. So the problem that we're going to be looking into for the next couple of lectures is how do you compute Fibonacci numbers. So if you want to use them to model rabbit populations or because of some number theoretic interest, we'd like an algorithm that as input takes a non-negative integer n and returns the nth Fibonacci number. And we're going to talk about how you go about doing this. So come back next lecture and we'll talk about that. Hello everybody, welcome back. Today we'll talk a little bit more about how to compute Fibonacci numbers. And in particular today what we're going to do is we're going to show you how to produce a very simple algorithm that computes these things correctly. On the other hand, we're going to show that this algorithm is actually very slow and talk a little bit about how to analyze that. So let's take a look at the definition again. The 0th Fibonacci number is 0. The first Fibonacci number is 1. And from thereafter, each Fibonacci number is the sum of the previous two. Now, these grow pretty rapidly, and what we would like to do is have an algorithm to compute them. So let's take a look at how we might do this. Well, there's a pretty easy way to go about it, given the definition. So if n is 0, we're supposed to return 0, and if n is 1, we're supposed to return 1. So we can just start with a case that says if n is at most 1, we're going to return n. Otherwise, what are we supposed to do? Otherwise, we're supposed to return the sum of the n minus first and n minus second Fibonacci numbers. So we can just compute those two recursively, add them together, and return that. So this gives us a very simple algorithm, 4 lines long, that basically took the definition of our problem and turned it into an algorithm that correctly computes the thing it's supposed to. Good for us. We have an algorithm and it works. However, in this course, we care a lot more than just does our algorithm work. We also want to know if it's efficient. So we'd like to know how long this algorithm takes to run. And as sort of a rough approximation to this, we're going to let t of n denote the number of lines of code that are executed by this algorithm on input n. So to count this is actually not very hard. So if n is at most 1, the algorithm checks the if case, goes to the return statement, and that's 2 lines of code. Not so bad. If n is at least 2, we go to the if case, we go to the else condition, and then run a return statement. So that's 3 lines of code. However, in this case, we also need to recursively compute the n minus first and n minus second Fibonacci numbers. So we need to add to that however many lines of code those recursive calls take. So all in all, though, we have a nice recursive formula for t of n. It's 2 as long as n is at most 1. And otherwise, it's equal to t of n minus 1 plus t of n minus 2 plus 3. So a nice recursive formula. Now, if you look at this formula for a little bit, you'll notice that it looks very similar to the original formula we used to define the Fibonacci numbers. Each guy was more or less the sum of the previous two. And in fact, from this you can show pretty easily that t of n is at least the nth Fibonacci number for all n. And this should be ringing some warning bells, because we know that the Fibonacci numbers get very, very, very large. So t of n must as well. In fact, t of 100 is already 1.77 times 10 to the 21, 1.77 sextillion. This is a huge number. Now, suppose we were running this program on a computer that executed 1 billion lines of code a second. It ran at a gigahertz. It would still take us about 56,000 years to complete this computation. Now, I don't have 56,000 years to wait for my computer to finish. You probably don't either. So this really is somehow not acceptable if we want to compute Fibonacci numbers of any reasonable size. So what we'd really like is we'd like a better algorithm, and we'll get to that next lecture. But first, we should talk a little bit about why this algorithm is so slow. And to see that, maybe the clearest way to demonstrate it is to look at all of the recursive calls that this algorithm needs in order to compute its answer. So if we want to compute the nth Fibonacci number, we need to make recursive calls to compute the n minus first and n minus second Fibonacci numbers. To compute the n minus first, we need the n minus second and n minus third. To compute the n minus second, we need the n minus third and n minus fourth. And it just keeps going on and on from there, and we get this big tree of recursive calls. Now, if you'll look at this tree a little bit closer, it looks like we're doing something a little bit silly. We're computing fn minus 3 separate times in this tree. And the way that our algorithm works, every time we're asked to compute it, since it's a new recursive call, we compute the whole thing from scratch. We recompute fn minus 4 and fn minus 5 and then add them together and get our answer. And it's sort of this computing the same thing over and over again that's really slowing us down. And to make it even more extreme, let's blow up the tree a little bit more. Fn minus 4 actually gets computed these 5 separate times by the algorithm. And as you keep going down more and more and more times, are you just computing the same thing over and over again? And this is really the problem with this particular algorithm, but it's not clear immediately that we can do better. So come back next lecture and we'll talk about how to get around this difficulty and actually get a fairly efficient algorithm. Hello everybody, welcome back. We're still talking about algorithms to compute Fibonacci numbers. And in this lecture, we're going to see how to actually compute them reasonably efficiently. So, as you'll recall, the Fibonacci numbers was the sequence, 0, then 1, then a bunch of elements, each of which was the sum of the previous two. We had a very nice algorithm for them last time, which unfortunately was very, very slow, even to compute the 100th Fibonacci number, say. So, we'd like to do better, and maybe you need some idea for this new algorithm, and one way to think about it is, what do you do when you compute them by hand? And in particular, suppose we want to write down a list of all the Fibonacci numbers. Well, there's sort of an obvious way to do this. You start off by writing 0 and 1, because those are the first two. The next one is going to be 0 plus 1, which is 1. The next one is 1 plus 1, which is 2. And 1 plus 2, which is 3, and 2 plus 3, which is 5. And at each step, all I need to do is look at the last two elements of the list and add them together. So 3 and 5 are the last two, I add them together, and I get 8. And this way, since I have all of the previous numbers written down, I don't need to do these recursive calls that I was making in the last lecture that were really slowing us down. So let's see how this algorithm works. So what I need to do is I need to create an array in order to store all the numbers in this list that I'm writing down. The 0th element of the array gets set to 0. The first element gets set to 1. That's to set our initial conditions. Then as I runs from 2 to n, we need to set the ith element to be the sum of the I minus first and I minus second elements. That correctly computes the ith Fibonacci number. Then at the end of the day, once I've filled out the entire list, I'm going to return the last element, f of n. So now we can say this is another algorithm. It should work just as well. But how fast is it? Well, how many lines of code do we use? There are 3 lines of code at the beginning, and there's a return statement at the end, so that's 4 lines of code. Next up, we have this for statement that we run through n minus 1 times, and each time we have to execute 2 lines of code. So adding everything together, we find out that t of n is something like 2n plus 2. So if we wanted to run this program on input n equals 100, it would take us about 202 lines of code to run. And 202 is actually a pretty small number, even on a very modest computer these days. So essentially, this thing, it's going to be trivial to compute the 100th or the 1000th or the 10,000th Fibonacci number on any reasonable computer. And this is much better than the results that we were seeing in the last lecture. So in summary, what we've done in this last few lectures, we've talked about the Fibonacci numbers, we've introduced them. We've come up with this naive algorithm, this very simple algorithm that goes directly from the definition, that unfortunately takes thousands of years, even on very small examples, to finish. On the other hand, the algorithm we just saw is much better. It's incredibly fast, even on fairly large inputs, and it works quite well in practice. And so the moral of the story, the thing to really keep in mind, is that in this case and in many, many others, the right algorithm makes all the difference in the world. It's the difference between an algorithm that will never finish in your entire lifetime and one that finishes in the blink of an eye. And so that's the story with Fibonacci numbers. Next lecture, we're going to talk about a very similar story that comes with computing greatest common divisors. So I hope you come back for that. Until then, farewell. Hello everybody, welcome back. Today we're going to be talking about computing greatest common divisors. So, in particular, what we'd like to do this lecture is we're going to define the greatest common divisor problem, and we're going to talk about an inefficient way to compute them. And next lecture we'll talk about how to do better. So, okay, what are GCDs? So, suppose that you have a fraction, a over b, and you want to put it in simplest form. Now, the standard way of doing this is we want to divide the numerator and denominator both by some d to get some equivalent fraction, a over d divided by b over d. Fair enough. Now, what d do we want to use for this? Well, it needs to satisfy 2 properties. Firstly, d had better divide both a and b, such that the new numerator and denominator are both integers. But subject to that, we would like this d to be as large as possible, such that we can reduce the fraction as much as we possibly can. So, turning this into a definition, we say that for 2 integers a and b, their greatest common divisor, or GCD, is the largest integer d that divides both a and b. Okay, so this is a thing that you use to reduce fractions. However, it turns out that GCDs are a critically important concept in the field of number theory, the study of prime numbers and factorization and things like that. And because it's so important in number theory, it turns out that being able to compute GCDs is actually very important in cryptography. And the fact that you can, perform, secure online banking is in part due to the fact that we can efficiently compute GCDs of numbers in order for our cryptographic algorithms to work. So, because of this importance, we're going to want to be able to compute GCDs. So we'd like an algorithm that, given 2 integers, a and b, at say at least 0, we can compute the GCD of a and b. And just to be clear sort of what kinds of inputs we care about, we actually like to be able to run this on very large numbers. We don't just want something that works for, GCD of 5 and 12 or 11 and 73. We'd like to be able to do things like the GCD of 3,918,848 with 1,653,264. In fact, we'd also like to be able to compute much bigger numbers, 20, 50, 100, 1,000 digits. We'd still like to be able to get GCDs of numbers of those sizes pretty quickly. Well, let's get started. Let's start by just finding an algorithm that works. what we'd like is the largest number that divides both A and B. So one thing we can do is we can just check all of the numbers that are sort of candidates for this, figure out which ones divide A and B, and return the largest one. So there's an easy implementation for this. We create a variable called best and set it to 0. This just remembers the biggest thing we've seen so far. We then let D run from 1 to A plus B, since this is the range of numbers that are sort of valid. Now, if D divides A and D divides B, well, since D is increasing, this has to be the new best that we've seen. So we set best equal to D, and then at the end of the day, we return the best thing we've seen. So that's a perfectly good algorithm. It works. Unfortunately, it's a little bit slow, because we need to run through this for loop A plus B many times. And this means that even once A and B are, say, 20-digit numbers, it's already going to be taking us at least thousands of years in order to run this computation. And so that's not sufficient for the sorts of applications that we care about. We're going to need a better algorithm. So come back next lecture and we'll talk about how to find a better algorithm for this problem and what goes into that. Hello everybody, welcome back. Today we're going to be talking a little bit more about computing greatest common divisors. So in particular today we're going to be talking about a much more efficient algorithm than last time. This is known as the Euclidean algorithm. We'll talk about that and we'll talk a little bit about how its runtime works. So just to recall, for integers A and B, their greatest common divisor is the biggest integer D that divides both of them. And what we'd like to do is we'd like to be able to compute this. Given two integers, we want to compute their GCD. So we found a bad algorithm for this, and we'd like a better one. It turns out that in order to find a better algorithm, you need to know something interesting. There's this key lemma that we have, where suppose that we let A prime be the remainder when A is divided by B. Then the GCD of A and B is actually the same as the GCD of A prime and B, and also the same as the GCD of B with A prime. And the proof of this, once you know what to prove, is actually not very difficult. The idea is that because A prime is a remainder, this means A is equal to A prime plus some multiple of B, plus B times Q for some Q. Now, from that you can show that if D divides both A and B, that happens if and only if it divides both A prime and B. Because, for example, if D divides A prime and B, it divides A prime plus BQ, which is A. So, from this statement, we know that the common divisors of A and B are exactly the same as the common divisors of A prime and B. And therefore, the greatest common divisor of A and B is the greatest common divisor of A prime and B. And this is the idea for the algorithm. Basically, we have the GCD of A and B is the same as the GCD of B and A prime. But A prime is generally smaller than A, so if we compute that new GCD recursively, hopefully that will be an easier problem. Now, we do need a base case for this, so we're going to start off by saying if B is equal to 0, everything divides 0, so we just need the biggest thing that divides A. So we're going to return A in that case. Otherwise, we're going to let A prime be the remainder when A is divided by B. And we're going to return the GCD of B and A prime computed recursively. Now, by the lemma that we just gave, if this ever returns an answer, it will always give the correct answer. But at the moment, we don't even know that it will necessarily terminate, much less do so in any reasonable amount of time. So let's look at an example. Suppose that we want to compute the GCD of 3,918,848 with 1,653,264. So B here is not 0. We divide A by B, we get a remainder that's something like 612,000. And now we have a new GCD problem to solve. Once again, B is not 0. We divide A by B, we get a new remainder of 428,000 some. We repeat this process, get a remainder of 183,000 some, 61,000 some, divide again, we get a remainder of 0. And now B is 0, so we return the answer, 61,232. And this is the right answer. You'll note, though, that, this thing took us something like 6 steps to get to the right answer. Whereas if we'd used the algorithm from last time, we would have had to check something like 5 million different possible common divisors to find the best one. So this, it turns out, is a lot better. And to get a feel of how well this thing works, or why it works well, every time we take one of these remainders with division, we reduce the size of the number involved by a factor of about 2. And if every step we're reducing things by a factor of 2, after about log of a times b many steps, our numbers are now tiny or 0, and so basically after log of a times b many steps, this algorithm is going to terminate. Each of these, this means that suppose that we want to compute GCDs of 100-digit numbers, this is only going to take us about 600 steps to do it. Each of the steps that we've used here is a single division with remainder. 600 divisions with remainder is something you can do trivially on any reasonable computer. And so this algorithm will compute quite large GCDs very quickly. So in summary, once again, we had this computational problem. There was a naive algorithm, one that was very simple, came right from the definition, but it was far too slow for practical purposes. There's a correct algorithm, which is much, much better, very usable. Once again, finding the right algorithm makes all the difference in the world. But here there was this interesting thing that we found. In order to get the correct algorithm, it required that we actually know something interesting about the problem. We needed this key lemma that we saw today. And this is actually a theme that you'll see throughout this course and throughout your study of algorithms. Very often, in order to find a better algorithm for a problem, you need to understand something interesting about the structure of the solution. And that will allow you to simplify things a lot. In any case, that's all for today. Come back next lecture, we'll start talking about how to actually compute runtimes in a little bit more detail. But until then, goodbye. Hello everybody, welcome back to the Data Structures and Algorithms specialization. Today we're going to be talking about what really goes into computing runtimes and really understanding how long it takes a program to run. So in particular, today we're really going to dive in. Up till this point we're using this sort of rough number of lines of code executed count. And today we're going to talk about how accurate this is and what sorts of complications come in. And in particular, we'll see that if we actually want something that's sort of fundamentally an accurate measure of runtime, it's going to be a huge mess. We're going to have to bring in all sorts of extra data that aren't really convenient for us. And so we'll really sort of be talking about a problem that comes in with computing runtimes and algorithms, something that we're not going to resolve really until the next lecture. Okay, so to start with, let's look at this algorithm that we had for computing Fibonacci numbers. Remember, we created an array, we assigned the 0th element to 0, the first element to 1, then we had this big for loop where we set the ith element to be the sum of the I minus first and I minus second elements, and then at the end of the day, we returned the nth element of the array. So we determined that when we ran this program, we executed about 2n plus 2 lines of code, but we should really ask ourselves, is this number of lines of code executed really sort of an accurate description of the runtime of an algorithm? And, somehow, implicitly, this measure of lines of code assumes that sort of any two lines of code are sort of comparable to each other. They're sort of one basic operation. And so let's actually look at this program in some detail and see what goes into some of these lines of code and see how valid this assumption is. So to start with, we create this array. And what happens when you try to initialize an array? Well, this depends a lot on your memory management system. Fundamentally, all you have to do is you have to sort of find some space in memory and then get sort of a pointer to the first location. On the other hand, how exactly you find this, maybe you need to shuffle some other things around to make room for it. Maybe after you allocate the array, you then want to zero out all of the entries so that you don't have junk sitting in there. And so it's not entirely clear. It depends a little bit on how exactly your program is being interpreted. But it could be pretty fast. It could actually take a while depending on circumstances. Okay. Let's look at the next time. This is just a simple assignment. We set the 0th entry to 0. However, if you really look at this at the machine level, you're doing a bit more work. You need to load up the pointer to the 0th element of the array. You maybe then have to do some pointer arithmetic. You then need to store this literal 0 into that spot in memory. It could actually be not one operation, but a few operations. Similarly, when we set the first element to 1, you have to do sort of this very similar set of things. Next, there's this for loop. And with the for loop, again, every time you execute it, you have to do a few things. You need to increment the value of I. You then need to compare I to n to see if you need to break out of the loop. And if it is, you need to branch. You need to move to another instruction in your program after the for loop. Next up, there's this addition step. And here we have to do some things. We have to look up 2 values in the array. We have to write to a 3rd value in the array. All of this involves the same sort of pointer arithmetic and memory lookups and writes that we were talking about before. But we also have to do this addition. And if it were just a normal addition, maybe it wouldn't be such a big deal. However, this is an addition of 2 Fibonacci numbers. And if you'll recall from a couple of lectures ago, we found that Fibonacci numbers were pretty big. In fact, so big that they probably don't fit in a single machine word. So adding 2 of them together actually takes a non-trivial amount of time. So somehow, not only do we have to do all of these array arithmetic things, but the actual addition of the Fibonacci numbers is actually a pretty non-trivial operation. Okay, and then we do this return step, where we have to do an array lookup, which involves all the sorts of things we've talked about already, and then have to do a return, which sort of is going to operate with the program stack and sort of pop it up a level and return an answer. So, in conclusion, this program has 6 lines of code to it, but the amount of work being done in various lines of code is very, very different. Exactly what goes into each line of code is not sort of at all the same thing. Maybe we want to reconsider this count that the number of lines of code is sort of our runtime. Maybe we need to measure something else. So, what else should we do? Well, if you want to be totally correct about what we actually care about, what you need to say is, well, we're going to take this program, we're going to run it on some real-life computer, and we'd like to know how much actual time it will take for this program to finish. Right? That is fundamentally what we want to know. Unfortunately, in order to figure that out, we need to know all kinds of messy details. We need to know things like the speed of the computer that we're running it on. If you run it on a big supercomputer, it'll take a lot less time than if you run it on, your cell phone. The system architecture of the computer will matter. Exactly what operations your CPU supports and exactly how long they take relative to one another, those are all going to have an effect on your runtime. The compiler being used is also going to make a difference. In practice, what you'll do is you'll write this program in some high-level language in C or Java or Python or something, and then you'll run it through a compiler to turn it into machine code. And then the compiler, though, isn't just sort of doing something completely obvious. It's performing all kinds of interesting optimizations to your code. And which optimizations it performs and how they interact with exactly what you've written, that's all going to have an impact on the final runtime. Finally, you're going to care about details of the memory hierarchy. If your entire computation fits into cache, it will probably run pretty quickly. However, if you have to start doing lookups into RAM, things will be a lot slower. RAM lookups actually take a fair bit of time. If, on the other hand, you run out of memory in RAM and have to start doing, having to start writing some of these memory operations to disk, things are going to be a lot slower. Lookups to hard disks can take milliseconds, which are forever in computer time. And so exactly how much memory is stored in these various levels of the hierarchy, and exactly how long the lookups take, and how good the algorithms about to predict what things you're going to look up in the future are, those are all going to affect your runtime. And so putting it all together, we've found basically a problem. Figuring out accurate runtimes is a huge mess. You need to know all of these details, and you need to figure out how everything interacts. And we're going to be talking about a lot of algorithms in the class, and we're going to need to tell you about runtimes for all of them. And we don't want to have to do this huge mess every single time we have a new algorithm that we want to analyze. And this is an issue. And another issue is just that in practice, this is all assuming that you did know these details. In practice, you don't know a lot of these details because you're writing a program that's going to be run on somebody else's computer, and you've got no idea what their system architecture looks like on that computer because you don't know what the computer is. You don't know who's running it. In fact, there'll be several people running it on different computers with different architectures and different speeds, and it'll be a mess. And you really don't want to compute the runtime separately for every different client. So we've sort of got a big problem here, and we're not going to solve it today. But next lecture, we're going to talk about how we get around this. And what we really want is we want a new way to measure runtime that allows us to get some reasonable answer without knowing these sorts of details. And one of the key tricks that you should be looking at that we'll be using to solve this problem is we're going to be getting things that really give us results for very large inputs. They tell us sort of not necessarily how long it actually takes in sort of real seconds and minutes and hours, but tell us sort of how our runtime scales with input size. And in practice, this is sort of a very important thing because oftentimes we really do care what happens when we have huge inputs, millions of data points that we need to analyze. How long does it take? And so come back next lecture. We'll talk about how we resolve some of these issues and talk about some very useful notation that we will be using throughout the rest of this sequence. So I hope you come back then, and I'll see you there. Hello everybody, welcome back. Today we're going to start talking about asymptotic notation. So here we're going to sort of just introduce this whole idea of asymptotic notation and describe some of the advantages of using it. So last time we ran into this really interesting problem that computing runtimes is hard, in that if you really, really want to know how long a particular program will take to run on a particular computer, it's a huge mess. It depends on knowing all kinds of fine details about how the program works, and all kinds of fine details about how the computer works, how fast it is, what kind of system architecture it is. It's a huge mess. And we don't want to go through this huge mess every single time we try to analyze an algorithm. So we need something that's, maybe a little bit less precise, but much easier to work with. And we're going to talk about the basic idea behind that. And the basic idea is the following. That, yeah, there are lots of factors that have an effect on the final runtime, but most of them will only change the runtimes by a constant. If you're running on a computer that's 100 times faster, it will take 1/100th of the time, a constant multiple. If your system architecture has multiplications that take 3 times as long as additions, then if your program is heavy on multiplications instead of additions, it might take 3 times as long, but it's only a factor of 3. If your memory hierarchy is arranged in a different way, you might have to do disk lookups instead of RAM lookups, and those will be a lot slower, but only by a constant multiple. So the key idea is if we come up with a measure of runtime complexity that ignores all of these constant multiples, where running in time, n and running in time 100 times n are sort of considered to be the same thing, then we don't have to worry about all of these little bitty details that affect runtime. Of course, there's a problem with this idea if you look at it sort of by itself, that if you have runtimes of 1 second or 1 hour or 1 year, these only differ by constant multiples. A year is just something like 30 million seconds. And so if you don't care about factors of 30 million, you can't tell the difference between a runtime of a second and a runtime of a year. How do we get around this problem? Well, there's a sort of weird solution to this. we're not going to actually consider the runtimes of our programs on any particular input. We're going to look at what are known as asymptotic runtimes. These ask, how does the runtime scale with input size? As the input size n gets larger, does the output scale proportional to n? Maybe proportional to n squared? Is it exponential in n? All of these things are different. And in fact, they're sort of so different that as long as n is sufficiently large, the difference between n runtime and n squared runtime is going to be worse than any constant multiple. If you've got a constant multiple of 1,000, 1,000n might be pretty bad with that big number in front, but when n becomes big, it's still better than n squared. And so by sort of only caring about what happens in this sort of long scale behavior, we will be able to do this without seeing these constants, without having to care about these details. And in fact, this sort of asymptotic large scale behavior is actually what you care about a lot of the time, because you really want to know what happens when I run my program on very large inputs. And these different sorts of scalings do make a very large difference on that. So suppose that we have an algorithm whose runtime is roughly proportional to n, and we want to say we run it on a machine that runs at about 1 gigahertz. How large an input can we handle such that we will finish the computation in a second? Well, if it runs in about size n, you can handle about 1 billion sized inputs before it takes more than a second. If instead of n, it's n log n, it's a little bit slower. You can only handle inputs of size about 30 million. If it runs like n squared, it's a lot worse. You can only handle inputs of size about 30,000 before it starts taking more than a second. If the inputs are size 2 to the n, it's incredibly bad. You can only handle inputs of size about 30 in a second. Inputs of size 50 already take 2 weeks. Inputs of size 100 you'll never ever finish. And so the difference between n and n squared and 2 to the n is actually really, really significant. And it's often more significant than these factors of 5 or 100 that you're seeing from other things. Now, just to give you another feel of sort of how these sort of different types of runtimes behave, let's look at some sort of common times that you might see. There's log n, which is much smaller than root n, which is much smaller than n, which is much smaller than n log n, which is much smaller than n squared, which is much smaller than 2 to the n. So if we graph all of these, you can see that these sort of graphs sort of separate out from each other. If you just look at them at small inputs, it's maybe a little bit hard to tell which ones are bigger. There's a bit of jostling around between each other. But if we extend the graph outwards a bit, it becomes much more clear. 2 to the n starts after about 4 really taking off. Really, just 2 to the n just shoots up there. After n becomes 20 or 30, it just leaves everyone else in the dust. N squared keeps up a pretty sizable advantage, though, against everyone else. N log n and n also are pretty well separated from the others. In this graph, root n and log n seem to be roughly equal to each other, but if you kept extending, if you let n get larger and larger, they'd very quickly differentiate themselves. Square root of 1,000,000 is about 1,000. Log of 1,000,000 is about 20. And so, really, as you keep going out, very quickly, the further out you go, the further separated these things become from each other. And that's really the key idea behind sort of asymptotics. We don't care so much about the constants. We care about what happens as your inputs get very large. How do they scale? So that's it for today. Come back next lecture. We'll talk about in sort of detail what this actually means and how to actually get it to work. So until next time. Hello, everybody. Welcome back. Today we're going to be talking about big O notation, which is the specific sort of asymptotic notation that we will be using most frequently here. So the idea here is we're going to introduce the meaning of big O notation and describe some of its advantages and disadvantages. So to start with the definition, the idea is we want something that cares about what happens when the inputs get very large and sort of only care about things up to constants. So we're going to come up with the definition. If you have got two functions, f and g, f of n is big O of g of n. If there's two constants, capital N and little c, such that for all little n, at least capital N, f of little n is at most c times g of little n. And what this means is that at least for sufficiently large inputs, f is bounded above by some constant multiple of g, which is really sort of this idea that we had from before. Now, for example, 3n squared plus 5n plus 2 is O of n squared. Because if we take any n at least 1, 3n squared plus 5n plus 2 is at most 3n squared plus 5n squared plus 2n squared, which is 10n squared. Some multiple of n squared. So, and in particular, if you look at these two functions, they really, in some sense, do have the same growth rate. If you look at the ratio between them, sure, it's large, it's 10 when n equals 1, but as n gets large, it actually drops down to about 3. And once you're putting in inputs, at n equals 100, n squared is 1,000,000. 3n squared plus 5n plus 2 is a little bit more than 3 million. So they're not the same function. One of them is distinctly larger than the other, but it's not larger by much, not by more than a factor of about 3. So throughout this course, we're going to be using big O notation to report basically all of our algorithms' runtimes. And this has a bunch of advantages for us. The first thing that it does for us is it clarifies growth rate. As I've said before, often what we care about is how does our runtime scale with the input size. And this is sort of an artifact of the fact that we often really care about what happens when we put really, really, really big inputs to our algorithm. How big can we deal with before it starts breaking down? And if you gave me some sort of complicated expression in terms of the input with lots of terms, then it might be hard, given two algorithms, to really compare them. I mean, which one's bigger would depend on exactly which inputs I'm using. It would require some sort of annoying computation to determine where exactly one's better than the other. But if you look at things asymptotically, what happens as n gets large, it often becomes much more clear that, once n is very, very large, algorithm A is better than algorithm B. The second thing it does for us is it cleans up notation. We can write O of n squared instead of 3n squared plus 5n plus 2. And that's a lot cleaner and much easier to work with. We can write O of n instead of n plus log base 2 of n plus sine n. We can write O of n log n instead of 4n log base 2 of n plus 7. And note that in the big O, we don't actually need to specify the base of the logarithm that we used, because log base 2 of n and log base 3 of n and log base 10 of n and log base 7 of n, they only differ by constant multiples. And up to the constant multiples, this big O that we have really doesn't care. Another consequence of this is that because our notation is cleaner, because we have fewer lower order terms to deal with, this actually makes the algebra that we have to do easier. It makes it easier to manipulate big O expressions because they're not as messy. And the final thing this does is that this big O notation really does solve these problems we were talking about a couple lectures ago. In order to compute runtimes in terms of big O, we really don't need to know things like how fast the computer is, or what the memory hierarchy looks like, or what compiler we used. Because by and large, although these things will have a big impact on your final runtime, that impact will generally only be a constant multiple. And if two things are only off by a constant multiple, they've got the same big O. That's all there is. Now, I should say that there's a warning. Big O is incredibly useful. We are going to be using it for basically everything in this course. But it does lose a lot of information about your runtime. It forgets about any constant multiples. So if you have two algorithms and one of them's 100 times faster, they have the same big O. But in practice, if you want to make things fast, a factor of 100 is a big deal. Even a factor of 2 is a big deal. And so if you really want to make things fast, once you have a good asymptotic runtime, you then want to look into the nitty-gritty details. Can I save a factor of 2 here? Can I rearrange things to make things run a little bit smoother? Can I make it interact better with the memory hierarchy? Can I do X, Y, and Z to make it faster by these constant factors that we didn't see beforehand? The second thing that you should note, sort of along these lines, is that big O is only asymptotic. In some sense, all it tells you about are what happens when you put really, 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 really big inputs into the algorithm. And Well, if you actually want to run your algorithm on a specific input, Big O doesn't tell you anything about how long it takes in some sense. I mean, usually the constants hidden by the Big O are moderately small, and therefore you have something useful. But sometimes they're big. Sometimes an algorithm with worse Big O runtime, that's worse asymptotically on very large inputs, actually, for all practical sizes, is actually beaten by some other algorithm. And there are cases of this where you find two algorithms where A works better than B on really, really, really big inputs, but sometimes really, really, really big means more than you could ever store in your computer in the first place. And so for any practical input, you want to use algorithm B. In any case, though, despite these warnings, Big O is incredibly useful. We're going to be using it throughout this course. And so next lecture, we're going to be talking a little bit about how to deal with Big O expressions, how to manipulate them, how to use them to compute runtimes. But once you have that, you will really be sort of ready to do some algorithms. In any case, that's all for this lecture. Come back next time and we'll talk about that. Hello everybody, welcome back. Today we're going to be talking about using Big O notation. So the basic idea here, we're going to be talking about how to manipulate expressions involving Big O and other asymptotic notations. And in particular, we're going to talk about how to use Big O to compute algorithm runtimes in terms of this notation. So recall, we said that f of n was Big O of g of n if for all sufficiently large inputs, f of n was bounded above by some fixed constant times g of n. What this really says is that f is bounded above by some constant times g. Now, we'd like to manipulate expressions. We'd like to, given expressions, write them in terms of Big O in the simplest possible manner. So there are some common rules you need to know. The first rule is that multiplicative constants can be omitted. So 7n cubed is O of n cubed. N squared over 3 is O of n squared. This is sort of the basic premise that we had when building this idea, was that we wanted to have something that ignores multiplicative constants. The second thing to note is that you have two powers of n. The one with the larger exponent grows faster. So n grows asymptotically slower is Big O of n squared. Root n grows slower than n, so it's O of n. Hopefully this isn't too bad. What's more surprising is that if you have any polynomial and any exponential, the exponential always grows faster. So n to the fifth is O of root 2 to the n. N to the 100 is O of 1.1 to the n. And this latter thing is something that should surprise you a little bit, because n to the 100 is a terrible runtime. 2 to the 100 is already so big that you really can't expect to do it ever. On the other hand, 1.1 to the n grows pretty modestly. 1.1 to the 100 is a pretty reasonable sized number. On the other hand, what this really says is that once n gets large, maybe 100,000 or so, 1.1 eventually takes over and starts beating n to the 100, and does so by, in fact, quite a bit. But doesn't really happen until n gets pretty huge. In a similar vein, any power of log n grows slower than any power of n. So log n cubed is O of root n. N log n is O of n squared. Finally, if you have some sum of terms, smaller terms in the sum can be omitted. So n squared plus n has a smaller rate of growth. So this is O of n squared. 2 to the n plus n to the ninth. N to the ninth has a smaller rate of growth. So this is O of 2 to the n. So these are some common rules for manipulating these expressions. Basically, these are the only ones that you'll need most of the time to write anything in terms of Big O that you need. Okay, so let's see how this works in practice. If we actually want to compute runtimes using Big O notation. So let's look at this one algorithm again. So we created an array. We set the 0th element to 0 and the first element to 1. We then went through this loop where we sent each element to the sum of the previous two, and then returned the last element of the array. Let's try computing this runtime in terms of Big O notation. So we're just going to run through it operation by operation and ask how long it takes. First operation is we created an array. And let's for the moment ignore the memory management issues, assume that it's not too hard to allocate the memory. But let's suppose that what your compiler does is we actually want to zero out all of these cells in memory. And that's going to take us a little bit of work. Because for every cell, basically what we have to do is we need to zero out that cell. We then need to increment some counter to tell us which cell we're working on next. And then maybe we need to do a check to make sure that we're not at the end. And if we are at the end, to go to the next line. Now, for every cell, we have to do some amount of work. We have to do something like do a write and a comparison and an increment. And it's not entirely clear how many machine operations this is. But it's a constant amount of work per cell in the array. There are n plus 1 cells. This is O of n time. Some constant times n. Next, we set the 0th element of the array to 0. And this might just be a simple assignment. We might have to load a few things into registers or do some pointer arithmetic. But no matter whether this is one machine operation or 5 or 7, that's still going to be a constant number of machine operations, O of 1. Similar to setting the first element to 1, again, O of 1 time. Next, we run through this loop. For I running from 2 to n, we run through it n minus 1 times. That's O of n times. The main thing we do in the loop is this. We set the ith element of the array to the sum of the I minus first and I minus second. Now, the lookups and the store, those are all the sorts of things that we've looked at. Those should be O of 1. But the addition is a bit worse. And normally additions are constant time, but these are large numbers. Remember, the nth Fibonacci number has about n over 5 digits to it. They're very big, and they often won't fit in the machine word. Now, if you think about what happens if you add two very big numbers together, how long does that take? Well, I mean, you sort of add the tens digit and you carry, and you add the hundreds digit and you carry, and you add the thousands digit and you carry, and so on and so forth. And you sort of have to do work for each digit place. And so the amount of work that you do should be proportional to the number of digits. And in this case, the number of digits is proportional to n. So this should take O of n time to run that line of code. Finally, we have a return step, which is a pointer arithmetic, an array lookup, and maybe popping up the program stack. And it's not quite clear how much work that is, but it's pretty clear that it's a constant amount of work. It doesn't become worse as n gets larger. So that's O of 1 time. So now we just have to add this all together. O of n plus O of 1 plus O of 1 plus O of n times through the loop times O of n work per time through the loop plus O of 1. Add it all together. The dominant term here, which is the only one we need, is the O of n times O of n. That's O of n squared. So this algorithm runs in time O of n squared. Now, we don't know exactly what the constants are, but O of n squared means that if you want to finish this in a second, you can probably handle inputs of size maybe 30,000. Now, depending on the computer that you had and the compiler and all of these messy details, maybe you can only handle inputs of size 1,000 in a second. Maybe you can handle inputs of size 1,000,000 in a second. It's probably not going to be as low as 10 or as high as 1 billion, but, I mean, 30,000 is a good guess. And, well, it takes work to get anything better than that. And so this doesn't give us an exact answer, but it's pretty good. Okay, so that's how you use big O notation. It turns out that occasionally you want to say a few other things. Big O really just says that my runtime is sort of bounded above by some multiple of this thing. Sometimes you want to say the reverse. Sometimes you might want to say that I'm bounded below. And so there's different notation for that. If you want to say that f is bounded below by g, that it grows no slower than g, you say that f of n is omega of g of n. And that says that for some constant c, f of n is at least c times g of n for all large n. Now, instead of saying bounded above or bounded below, sometimes you actually want to say that they grow at the same rate. And for that, you'd say f of n is big theta of g of n, which means that f is both big O of g and big omega of g, which says up to constants that f and g grow at the same rate. Finally, sometimes instead of saying that f grows no faster than g, you'd actually like to say that it grows strictly slower than g. And for that, you say f of n is little o of g of n. And that says that not only is the ratio between f of n and g of n bounded above by some constant, but actually this constant can be made as small as you like. In particular, this means that the ratio f of n over g of n goes to 0 as n goes to infinity. So these are some other notations that you'll see now and then. You should keep them in mind. They're useful. Big O is the one that usually shows up, as we actually want to bound our runtimes above, is sort of the big important thing, but these guys are also useful. So, to summarize the stuff on asymptotic notation, what it lets us do is ignore these messy details in the runtime analysis that we saw before. It produces very clean answers that tell us a lot about the asymptotic runtime of things. And these together make it very useful. It means we're going to be using it extensively throughout the course, so you really ought to get used to it. But it does throw away a lot of practically useful information. So if you really want to make your program fast, you need to look at more than just the big O runtime. But beyond that, we're going to use it. With this lecture, we've basically finished the sort of introductory material that we need. Next lecture, I'll talk to you a little bit about sort of an overview of the rest of the course and some of our philosophy for it. But after that, we'll really get into the meat of the subject. We'll start talking about key important ways to design algorithms. So I hope you enjoy it. Hello, everybody. Welcome back to the Data Structures and Algorithms Specialization and the Algorithmic Toolbox course within it. This is the last lecture in the introductory unit, and here we're going to give sort of an overview of the course. And in particular, what we're going to do is we're going to talk about sort of the philosophy of the course and how it fits into what we're going to be teaching you within the rest of this course. So there's a problem. Algorithm design is hard, and in particular, it's hard to teach. And by this, I actually mean something pretty specific. Now, algorithms solve many, many different problems. You can use them to find paths between locations on a map, or find good matchings with some property, or identify images in a photograph. Many, many different sort of unrelated sounding problems can all be solved by algorithms. And because the sorts of things that an algorithm problem might ask you to do are so varied, there's no unified technique that allows you to solve all of them. And this is different from what you see in a lot of classes. When you're learning linear algebra, they talk about how do you solve systems of linear equations. And they teach you some technique like row reduction, and then you're sort of done. You just sort of need to practice it, and you can solve any system of linear equations. They give you a system of linear equations, you turn the crank on this row reduction technology, and out pops an answer. For algorithms, there isn't that sort of thing. There's no general procedure where I give you an algorithms problem and you sort of plug it into this machine and turn a crank and out pops a good algorithm for it. And this makes it hard to teach. If there was such a thing, we could just teach you, here's this thing that you do this, and you'll have a good algorithm for any problem you might run into. And it's harder than that. I mean, sometimes in order to find a good algorithm, it requires that you have a unique insight. You're working on some problem that no one's ever looked at before. In order to find a good algorithm for it, you need to come up with some clever idea that no one else has ever come up with before. This is why sort of algorithms are so well studied, why there's such an active field of research. There's still so many different new things yet to be discovered there. And I mean, we certainly can't teach you things that haven't been discovered yet. And we also can't teach you things custom tailored to the problems that you are going to run into in your life as a programmer. So since we can't teach you everything you need to know about how to solve all of your algorithms problems, what can we teach you? Well, there are sort of two things. One thing that we can definitely give you is practice designing algorithms. We're going to have lots of homework problems with sort of lots of things for you to work on. And this will give you practice. How do you, given a problem you haven't seen before, come up with a good algorithm for it? Once you have the algorithm, how do you implement it and make sure everything works and runs reasonably well? That's something you can practice. And it turns out that for the type of problems where they're sort of very general and can be many different things, I mean, it's possible to solve a lot of them, and one of the ways to be able to solve them is practice. But we're also going to do more. We're not just going to throw you in the deep end and say, try to swim, try to program all of these algorithms. There is something useful. We can't teach you a generic procedure that will solve any algorithms problem for you. But what we can do is we can give you some common tools, some very useful tools for algorithm design. And especially in this first course in our specialization, we're really going to focus on helping to build up your algorithmic toolbox. And in particular, this course is going to focus on 3 of the most common and most generally applicable algorithmic design techniques. The first of these is greedy algorithms. This is something where you're trying to construct some big object, and the way you do it is you sort of make one decision in the most greedy, locally optimal way you can. And once you've made that decision, you make another decision in the most greedy, locally optimal way you can. And you just keep making these decisions one at a time until you have an answer. And surprisingly, somehow making these locally optimal decisions gives you a globally optimal solution. And when this happens, it gives you very clean algorithms, and it's great. That's the first thing we'll talk about. Next, we'll talk about divide and conquer, which is a technique where you've got some big problem you're trying to solve. What you do is you break it into a bunch of little pieces, you solve all the pieces, and then you put their answers together to solve the original thing. Finally, we'll talk about dynamic programming. This is a little bit more subtle of a technique. This is what you get when you've got some sort of large problem that has sort of a lot of, not sub-problems, but sort of related problems to it. And this sort of whole family of related problems, their solutions sort of depend on one another in a particular type of way. And when you have this, there's this great trick that you have where you sort of start at the small problems at the bottom of the pile and you solve all of them, and you sort of keep track of all of your answers, and you use the answers to the small problems to build up to obtain answers to the larger and larger problems. So these are what we're going to talk about. Each of the techniques we're going to talk about: how do you recognize when it applies, how do you analyze it when it applies, and sort of some practical techniques about sort of how to implement, how to use them, all that good stuff. So there's one other thing before we let you go into the fun world of greedy algorithms that you should keep in mind throughout this course. And that's that there are these maybe different levels of algorithm design. There's sort of different levels of sophistication that go into it. At sort of the very lowest level, or the top of the slide, I guess, there is the naive algorithm. This is sort of a thing where you take the definition of the problem and you turn it into an algorithm. And we saw this for Fibonacci numbers and greatest common divisors. You sort of interpreted the definition of the thing you wanted to compute as an algorithm, and you were done. Now, these things are often very slow, as we saw. Often they look like, in order to find the best way of doing something, we enumerate all ways to do it and then figure out which one's the best. On the other hand, I mean, these are slow, but it's often a good idea to first come up with a naive algorithm. Just make sure you have some algorithm that it works. Sometimes this works well enough and you can just be done with it. Other times it's too slow, but at least you made sure that you understood what problem you were working on and have something that runs. But after that, the next thing that you want to do, if this naive algorithm is too slow, is you try and look at your toolbox. You say, are there any standard techniques that I know that apply here? Maybe there's a greedy algorithm that solves this problem. Or maybe I have to use a dynamic program. But if you can find one of these standard techniques that work, often that doesn't involve too much effort on your part and gives you something that works pretty well. Now, once you have something that works, you often want to optimize it. And there are lots of ways to improve an existing algorithm. Reduce the runtime from n cubed to n squared, or n squared to n. And to do this, there are sort of a bunch of things. Maybe sometimes you can sort of rearrange the order in which you do the operations to cut out some of the work that you do. Sometimes you have to introduce a data structure to speed things up. There are a bunch of ways to do this. We'll talk a little bit about how this works. And these 3 levels are things that you should be comfortable with and able to apply pretty well by the end of this course. However, sometimes these 3 are not enough. Sometimes the naive algorithm is just too slow, the standard tools don't apply, there's nothing that you can really optimize to improve things. sometimes in order to get a workable algorithm, what you need is magic. You need some unique insight that no one else has ever had before. You need some sort of clever new idea. And there's only so much we can do to teach you how to produce magic. I mean, we will show you some examples of things that really did have clever ideas that maybe you can't reproduce the thought process that how did you come up with this crazy idea that just happens to make this work? But you should at least be able to appreciate the sort of thought that maybe goes into this sort of thing. In any case, something to keep in mind when looking on it, when thinking about our problems and what sort of things are expected of you. In any case, that is basically it for the introductory segment. We've talked a lot about sort of why algorithms are important and given you some examples. We've talked about asymptotic notation, but now it's time to let you go to the rest of the course. The rest of the course will keep giving you exercises to, hone your skills, and each unit of this course will cover one of these major techniques. After I leave you at the end of the introduction, Michael will pick up and talk to you about greedy algorithms. Next off, Neil will talk to you about divide and conquer. Finally, Pavel will have a unit on dynamic programming. Each of these, they will talk to you about where the technique applies, how to analyze it, how to implement it, all that good stuff. But this is where I leave you. I hope you've enjoyed the introduction, and I will put you in Michael's very capable hands to start learning about greedy algorithms starting in the next lecture. So, until then, farewell.
Hi, I'm Michael Levin, and together we will study greedy algorithms. They are some of the simplest algorithms that exist, and they usually seem a pretty natural way to try solving a problem. We will start with a few examples of problems that can be solved by greedy algorithms, just to illustrate how they work. And our very first problem is a problem about largest number. And for this problem you will probably be able to come up with a greedy algorithm yourself, because that is really a very natural thing to do. So, imagine a situation. You are trying to get a job at a company, and you've already had a few interviews, and everything went well. And now you have your final interview with the boss. And he tells you that he will give you an offer, but instead of negotiating your salary with you, he will give you a few pieces of paper with digits written on them. And your task will be to arrange those digits in a row, so that when you read the number from left to right, that will be your salary. So basically you have a problem, given a few digits, to arrange them in the largest possible number. And there are a few examples of such numbers on the slide. So, what do you think will be the correct answer to this problem? And of course, the correct answer is 997531. And it's pretty obvious that you should arrange numbers from the largest to the smallest, from left to right. But let's look at how the greedy algorithm does that. So, the greedy strategy is start with a list of digits, then find the maximum digit in the list, append it to the number, and remove it from the list. And then repeat this process until there are no digits left in the list. So on the next step we will find the largest digit, which is again 9. We will append it to the number to the right and remove it from the list. Then we will find 7 as the largest digit, append it to the right and remove it from the list. And then we will continue with 5, 3, and 1. And then we get the correct answer, 997531. And in the next video, we will design an algorithm to find the minimum number of refills during a long journey by car. We will see similarities between these two problems, largest number problem and car refueling problem. And we will define how greedy algorithms work in general. Hi! In this video, we will consider the problem to find the minimum number of refills during a long journey by car. You will see the similarities between this problem and the largest number problem from the previous video. By the end, you will be able to describe how greedy algorithms work in general and define what is a safe move and a subproblem. Consider the following problem. You have a car such that if you fill it up to full tank, you can travel with it up to 400 kilometers without refilling it. And you need to get from point A to point B, and the distance between them is 950 kilometers. Of course, you need to refuel on your way, and luckily there are a few gas stations on your way from A to B. These are denoted by blue circles, and the numbers above them mean the distance from A to the corresponding gas station along the way from A to B. And you need to find the minimum number of refills to get from A to B. One example of such route is to get from point A to the first gas station, 200 kilometers, then to get from first station to the third gas station, 350 kilometers distance, then from third gas station to the fourth gas station, 200 kilometers, and then from the fourth gas station to B, 200 kilometers. But that's not optimal, we can do better. Here is another route which only uses 2 refills. We get from A to the second gas station, less than 400 kilometers, then we get from the second gas station to the fourth gas station, again less than 400 kilometers, and then from the fourth gas station to B, only 200 kilometers. And this route uses only 2 refills, and it turns out that in this problem the minimum number of refills is exactly 2. More formally, we have the following problem. As the input, we have a car which can travel at most L kilometers, where L is a parameter, if it's filled up to full tank. We have a source and destination A and B, and we have n gas stations at distances from x1 to xn in kilometers from A along the path from A to B. And we need to output the minimum number of refills to get from A to B, not counting the initial refill at A. We want to solve this problem using a greedy strategy. And greedy strategy in general is very easy. You first make some greedy choice, then you reduce your problem to a smaller subproblem, and then you iterate until there are no problems left. There are a few different ways to make a greedy choice in this particular problem. For example, you can always refill at the closest gas station to you. Another way is to refill at the farthest reachable gas station, and by reachable I mean that you can get from your current position to this gas station without refills. Another way is, for example, to go until there is no fuel and then just hope that there will be a gas station in the end. So what do you think is the correct strategy in this problem? And of course the third option is obviously wrong. The first option is also wrong if you think about it, but the second option is actually correct. It will give you the optimal number of refills. We'll prove it later. For now, let's define our greedy algorithm as the whole algorithm. So we start at A and we need to get to B with the minimum number of refills. We go from A to the farthest reachable gas station G, so that we can get from A to G with full tank without any refills in the middle. And now we try to reduce this problem to a similar problem. We make G the new A, and now our problem is to get from the new A to B again with the minimum number of refills. And by definition, a subproblem is a similar problem of smaller size. One example of subproblem is from the previous video. When we need to construct the largest number out of a list of digits, we first put the largest digits in front, and then we reduce our problem to the problem of building the largest number out of the digits which are left. In this problem, to find the minimum number of refills on the way from A to B, we first refill at the farthest reachable gas station G, and then solve a similar problem, which is a sub-problem, to get from G to B with the minimum number of refills. Another important term is safe move. We call a greedy choice a safe move if it is consistent with some optimal solution. In other words, if there exists some optimal solution in which first move is this greedy choice, then this greedy choice is called a safe move. And we will prove a lemma that to refill at the farthest reachable gas station is a safe move. Let us first prove it visually. Let's consider some optimal route from A to B, and let the first stop on this route to refill be at point G1, and let G be the farthest gas station reachable from A. If G1 and G coincide, then our lemma is proved already. Otherwise, G1 has to be closer to A than G, because G is the farthest reachable from A, and G1 is reachable from A. Now let's consider the next stop on the optimal route, and let it be G2. And the first case is that G is closer to A than G2. Then the root can look like this. In this case, we can actually refill at G instead of G1. And then we will have another optimal root, because it has the same number of refills, and G is reachable from A, and G2 is actually reachable from G, because it was reachable from G1, but G is closer to G2 than G1. So this is a correct root, and in this case our lemma is proved. And the second case is when G2 is actually closer to A than G. And then the root can look like this. But in this case we can avoid refilling at G1 at all, and refill at G2, or even refill at G in the first place. And then we'll reduce the number of refills of our optimal root, which is impossible. So this second case actually contradicts our statement that we were looking at an optimal root. And we've proved our lemma. To recap, we consider the optimal root R with a minimum number of refills. We denote by G1 the position of the first refill in R, and by G2 the next stop is R, which is either a refill or the destination B. And by G we denote the farthest refill reachable from A. And we consider two cases. In the first case, if G is closer than G2 to A, we can refill at G instead of G1, and it means that refill at G is a safe move. Otherwise, we can avoid refill at G1, so this case contradicts that the root R is the root with the minimum number of refills, so there is no such case. And we proved our lemma. And in the next lecture, we will implement this algorithm in pseudocode and analyze its running time. Hi! In this video, you will learn to implement the greedy algorithm from the previous video and to analyze its running time. Here we have the pseudocode for this algorithm, and the procedure is called min refills. And the main input to this procedure is array x. From the problem statement, we know that the positions of the gas stations are given by numbers from x1 to xn, and those are measured in kilometers in terms of distance from A to the corresponding gas station along the path from A to B. For convenience, we actually add to array x positions of point A, which is x0 and is the smallest value in the array, and point B, which is xn plus 1, and it is the largest value in the array x. Along our route from A to B, we will visit some points. Of course, we will start from point A, and then we'll probably go to some gas station, refill there, and then go to another gas station, and then to another gas station, and then to another, and then at some point we'll get to the point B or point xn plus 1. So we see that we only need to store the positions in the array x. We don't need to consider any positions between the elements of array x. And so we will store in the variable current refill the position in the array x where we are currently standing. And we will initialize it with 0, because we start from point A, which is the same as x0 and has index 0 in the array x. And later, current refill will store the index in the array x where we are currently standing. We will also store the answer to our problem in the variable num refills. At each point in the execution of the algorithm, it will contain the number of refills we have already made. And we initialize it with 0, because the problem statement asks us to count the minimum number of refills we need to do, not counting the initial refill at point A. So when we are standing at point A, we consider that we haven't made any refills yet. Then the main external while loop goes. And it goes on while we are still to the left from point B, because then we need to go right to reach our destination B. And we check this condition with this inequality that current refill is at most n. This means that the position or index in the array x is at most n, and so we're to the left from point B currently. In this case, we still need to go to the right. And first, we save our current position in the array x in the variable last refill. This means that we made our last refill in the position current refill. And now we need to go to the right from there and either get to destination B or get to the rightmost reachable gas station and refill there. And the next internal while loop does exactly that. It gradually increases our current refill position in the array X until it reaches the rightmost point in the array X, which is reachable from the last refill position. So first we check that current refill position is at most n, because if it is n+1 already, it means that we reached our destination B, and there is no point increasing it further. If it's still to the left from B, then we look at the next position to the right, X current refill +1. We need to check whether it is reachable from last refill position or not. And first we compute the distance from the last refill position to the current refill +1 position by subtracting the values of the array X. And if this distance is at most L, then it means that we can travel this distance with full tank without any refills. And of course, at the last refill position we could fill our tank up to the full capacity, and then we'll be able to travel for L kilometers. So this inequality checks if actually position current refill +1 is reachable from the last refill position. If it is, we increase the value of current refill and go on with our internal while loop. When we exit this internal while loop, we're already maybe in the point B, or we may be in some point which is the farthest reachable gas station. Now we compare it with our last refill position, and if it turns out that it is the same, it means that we couldn't go to the right. We don't have enough fuel even to get to the next gas station. And then we cannot return the minimum number of refills that we need to do on the way from A to B, because it is impossible to get from A to B at all. And so we return this result, impossible. Otherwise, we moved at least a bit to the right, and then we need to see if we are already in the point B, we don't need to do anything else. Otherwise, we need to refill there. So we check that we're to the left from point B with this inequality, and if it's true, then we're at some gas station and we need to refill. So we increase the num refills variable by 1. And then we return to the start of our external while loop. And there we again check if we're to the left from point B, we need another iteration. And if current refill is already n+1, then we've reached point B and we need to exit the external while loop. And in that case, we just return the answer, which is number of refills we've made so far. We've implemented the greedy algorithm from the previous lecture. Now let's analyze its running time. From the first look, it can seem that it works in n² time, because we have the external while loop, which can make n iterations, and internal loop, which can make n iterations. So n by n is n², but actually we will show that it only makes O of n actions for the whole algorithm. To prove that, let's first look at the current refill variable. We see that it only changes one by one here, and it starts from 0. And what is the largest value that it can attain? Well, of course, the largest value is n+1, because this is the largest index in the array X, and current refill is index in the array X. So variable current refill starts from 0, changes one by one, and the largest value it can have is n+1. It means that it is increased at most n+1 times, which is big O of n. But that's not all we do. Also, we increase variable num refills here. But we also increase it always one by one. It also starts from 0. And what is the largest number that this variable can attain? Well, of course, it is n, because we only have n gas stations. There is no point to refill twice at the same gas station, so we can refill at most n times. So variable num refills goes to from 0 to n and changes one by one. So it is only changed at most n times. And so it is also linear in terms of n. And so we have at most n+1 iterations of the external while loop. Everything but the internal while loop takes their constant time, this assignment, this if, and this if with assignment. And the external loop and internal loop combined also spend at most linear time of iterations, because they change variable current refill, and it changes at most linear number of times. So all in all, our algorithm works in big O of n time. Let's go through this proof once again. The lemma says that the running time of the whole algorithm is big O of n, and we prove this by first noticing that the current refill variable changes only from 0 to at most n plus 1, and it changes always one by one, that the num refills variable changes from 0 to at most n, and it also changes one by one, so both these variables are changed big O of n times, and everything else that happens is constant time each iteration of the external loop, and there are at most n plus 1 iterations of the external loop. Thus, our algorithm works in linear time. In the next video, we will review what we've learned about greedy algorithms in general. Hi! In this video, we will briefly review the main ingredients of greedy algorithm. And the first of them is reduction to a subproblem. Basically, when you have some problem, you make some first move and thus reduce your problem to a similar problem, but which is smaller. For example, you have fewer digits left or fewer gas stations left in front of you, and this similar problem, which is smaller, is called a subproblem. Another key ingredient is a safe move, and a move is called safe if it is consistent with some optimal solution. In other words, if there exists some optimal solution in which the first move is the same as your move, then your move is called a safe move. And not all first moves are actually safe. For example, to go until there is no fuel is not a safe move in the problem about car fueling. And often greedy moves are also not safe. For example, to get to the closest gas station and refill at it is not a safe move, while to get to the farthest gas station reachable from you and refill there is a safe move. Now, the general strategy of solving a problem goes like this. First, you analyze the problem and you come up with some greedy choice. And then the key thing is to prove that this greedy choice is a safe move. And you really have to prove it, because otherwise you can come up with some greedy choice and then come up with a greedy algorithm and then even implement it and test it and try to submit it in the system, only to learn that the algorithm is incorrect, because the first move is actually not a safe move, and there are cases in which this first move is not consistent with any optimal solution. And in that case, you will have to invent a new solution and implement it from scratch. All the work you've done before will be useless. So please prove your algorithms and prove that the first move is a safe move. When you prove that, you reduce your problem to a subproblem, and hopefully that is a similar problem of the same kind, and then you start solving this subproblem the same way. You make your greedy choice and you reduce it to subproblem and you iterate until there are no problems left, or until your problem is so simple that you can just solve it right away. And in the next lessons we will apply greedy algorithms to solve more difficult problems. Hi! In this lesson we will discuss the problem of organizing children into groups. And you will learn that if you use a naive algorithm to solve this problem, it will work very slowly, because the running time of this algorithm is exponential. But later, in the next lesson, we will be able to improve that running time significantly by coming up with a polynomial time algorithm. Let's consider the following situation. You've invited a lot of children to a celebration party, and you want to entertain them and also teach them something in the process. You are going to hire a few teachers and divide the children into groups and assign a teacher to each of the groups. This teacher will work with this group through the whole party. But you know that for a teacher to work with a group of children efficiently, children in that group should be of relatively the same age. More specifically, age of any two children in the same group should differ by at most 1 year. Also, you want to minimize the number of groups, because you want to hire fewer teachers and spend the money on presents and other kinds of entertainment for the children. So, you need to divide children into the minimum possible number of groups, such that the age of any two children in any group differs by at most 1 year. Now let's look at the pseudocode for the naive algorithm that solves this problem. Basically, this algorithm will consider every possible partition of the children into groups and find the partition which both satisfies the property that the ages of the children in any group should differ by at most 1 and contains the minimum number of groups. We start with assigning the initial value of the number of groups to the answer m, and this initial value is just the number of children, because we can always divide all the children into groups of 1, and then of course each group has only 1 child, so the condition is satisfied. Then we consider every possible partition of all children into groups. The number of groups can be variable, so this is denoted by a number k, and we have groups g1, g2 and up to gk. And then when we have a partition, we first need to check whether it's a good partition or not. So we have a variable good, which we assign to true initially, because we think that maybe this partition will be good, but then we need to check for each group whether it satisfies our condition or not. So we go in a for loop with index I of the group from 1 to k, and then we consider the particular group gi, and we need to determine whether all the children in this group differ by at most 1 year, or there are 2 children that differ more. To check that, it is sufficient to compare the youngest child with the oldest child. If their ages differ more than by 1, then the group is bad. Otherwise, every 2 children differ by at most 1 year, so the group is good. And so we go through all the groups in a for loop. If at least one of the groups is bad, then our variable good will contain value false by the end. Otherwise, all the groups are good, and the variable good will contain value true. So after this for loop, we check the value of the variable good, and if it's true, then we improve our answer, at least try to improve it, with the minimum of its current value and the number of the groups in the current partition. And so by the end of the outer for loop, which goes through all the partitions, our variable m will contain the minimum possible number of groups in a partition that satisfies all the conditions. It is obvious that this algorithm works correctly, because it basically considers all the possible variants and selects the best one from all the variants which satisfy our condition on the groups. Now let us estimate the running time of this algorithm. And I state that the number of operations that this algorithm makes is at least 2 to the power of n, where n is the number of children in C. Actually, this algorithm works much slower and makes much more operations than 2 to the power of n. But we will just prove this lower bound to show that this algorithm is very slow. To prove it, let's consider just partitions of the children in 2 groups. Of course, there are much more partitions than that. We can divide them into 3, 4, and so on, much more groups. But let's just consider partitions in 2 groups and prove that even the number of such partitions is already at least 2 to the power of n. Really, if C is a union of 2 groups, G1 and G2, then basically we can make such partition for any G1 which is a subset of such C of all children. For any G1, just make group G2 containing all the children which are not in the first group. And then all the children will be divided in these 2 groups. So now, the size of the set of all children is n, and if we want to compute the number of possible groups G1, then we should note that each item of the set, or each child, can be either included or excluded from the group G1. So there can be 2 to the power of n different groups G1. And so there are at least 2 to the power of n partitions of the set of all children into groups, and it means that our algorithm will do at least to the power of n operations, because it considers every partition, and among all the partitions, there are all the partitions into two groups. So, how long will it actually work? We see that the naive algorithm works in time omega of 2 to the power of n, so it makes at least 2 to the power of n operations. And for example, for just 50 children, this is at least 2 to the power of 50, or the large number which is on the slide. This is the number of operations that we will need to make. And I estimate that on a regular computer, this will take at least 2 weeks for you to compute this, if this was exactly the number of operations that you would need. So it works really, really slow. But in the next lesson, we will improve this significantly. Hi! In this lesson, you will learn how to solve the problem of organizing children into groups more efficiently. More specifically, we will come up with a polynomial time algorithm for this problem, as opposed to the exponential time algorithm from the previous lesson. But in order to do this, we first need to do a very important thing that you should probably do every time before solving an algorithmic problem. You should reformulate it in mathematical terms. For example, in this problem, we will consider points on a line instead of children. For example, if we have a child of age 3.5 years, we will instead consider a point on the line with coordinate 3.5. And if we have another child of age 6, we will instead consider a point with coordinate 6 on the line. Now, what the groups of children correspond to? If we have a group of children, it consists of several children, and several points on the line correspond to this group. And the fact that the age of any two children in the group differs by at most 1 means that there exists a segment of length 1 on this line that contains all those points. Now, the goal becomes to select the minimum possible number of segments of length 1 such that those segments cover all the points. Then, if we have such segments, we can just take all the points from that segment in the same group, and any two children in the group will differ by at most 1 year. Now, let's look at an example. So we have a line with a few points on it, and we want to cover all the points with segments of length 1. Here is one example of such covering. All the segments on the picture are of the same length, and we consider that this is length 1 of this line. This is not the optimal solution, because below there is another example of covering, and we have only three segments, and they still cover all the points. Now we want to find a way to find the minimum possible number of segments to cover all the points in any configuration. We want to do that using greedy algorithm. And you probably remember from the previous lessons that to come up with a greedy algorithm, you need to do a greedy choice, and to prove that this greedy choice is a safe move. I state that in this problem, safe move is to cover the leftmost point with a segment of length 1 which starts or has left end in this point. To prove that this is really a safe move, we need to prove that there exists an optimal solution with the minimum possible number of unit length segments, such that one of the segments has its left end in the leftmost point. Let's prove that. To do that, let's consider any optimal solution of a given problem with the given points. Let's consider the leftmost point, colored in green. It is covered by some segment, colored in red. Now, let's move this red segment to the right until its left end is in this leftmost point. I state that we didn't miss any of the points in the process, because this green point is the leftmost point, so there are no points to the left from it, and while we were moving the segment to the right, we didn't miss any of the points. It means that what we have now is still a correct covering, because all the points are still covered, and the number of segments in this covering is the same as in some optimal solution from which we started. And that means that it is also an optimal covering. So, we have just found an optimal solution in which there is a segment which starts in the leftmost point. So, we proved that covering the leftmost point with the segment which starts in it is a safe move. Now that we have a safe move, let's consider what happens after it. We have the leftmost point covered, and also maybe some other points covered, so we don't need to consider these points anymore. We're not interested in them, and we need to cover all the other points with the minimum possible number of unit length segments. So this is the same kind of problem that which we started with. So this is a sub-problem. Basically it means that we have a greedy algorithm. First make a safe move, add a segment to the solution with the left end starting in the leftmost point, then remove all the points which are already covered by this segment from the set, and if there are still points left, repeat the process. And repeat this process until there are no points left in the set. Now, let us consider the pseudocode that implements this algorithm. For the sake of simplicity, we assume that the points in the input are given in the sorted order, from smallest to largest. We start with an empty set of segments denoted by R, and we start with index I pointing at the first point, which is the leftmost because the points are sorted. Now, we go through the points, we find the leftmost point. Currently I is pointing to the leftmost point in the set, and at the start of the while loop I will always point to the leftmost point which is still in the set. Now we cover it with the segment from L to R which has unit length and the left end in the point xi. So this is a segment from xi to xi plus 1. We add this segment to the solution set, and then we need to remove all the points from the set which are already covered. Instead of removing the points, we will just move the pointer to the right and forget about the points which are to the left from the pointer. So the next while loop does exactly that. We know that for any I that is larger than the current I, xi is to the right from the left end of the segment because the points are sorted. So if xi is also to the left from R, then it is covered by the segment. So we just go to the right and to the right with pointer I, and while xi is less than or equal to R, we know that the point is covered, and as soon as we find some xi which is bigger than R, it means that this point is not covered and all the points further in the array are also not covered. So we stop. And then we repeat again the iteration of the outer while loop. Or maybe our pointer I is already out of the array of the input points, and then we stop and return R, which is the set of segments that we've built in the process. Now let's prove that this algorithm works in linear time. Indeed, index I changes just from 1 to n, and we always increase it by 1. For each value of I, we add at most one segment to the solution. So overall, we increase I at most n times and add at most n segments to the solution. And this leads to a solution which works in big O of n time. Now, we had an assumption that the points in the input are already sorted. What if we drop this assumption? Then we will have to sort the points first and then apply our algorithm points cover sorted. Later, in this module, you will learn how to sort points in time n log n. Combining that with our procedure points cover sorted will give you total running time of n log n. Now let's look at our improvement. We first implemented a straightforward solution which worked in time at least 2 to the power of n. And it worked very slowly, so that even for 50 children we would have to spend at least 2 weeks of computation to group them. Our new algorithm, however, works in n log n time, and that means that even if we had 10 million children coming to a party, we would spend only a few seconds grouping them optimally into several groups. So that's a huge improvement. Now, let's see how we went to this end. First, we've invented a naive solution, which worked in exponential time. It was too slow for us, so we wanted to improve it. But to improve it, the very first important step was to reformulate it in mathematical terms. And then we had an idea to solve it with a greedy algorithm, so we had to find some greedy choice and prove that it will be a safe move. In this case, the safe move turned out to be to add to the solution a segment with left end in the leftmost point. And then we proved that this is really a safe move. It is very important to prove your solutions before even trying to implement them, because otherwise it can turn out that you've implemented the solution, tried to submit it, got wrong answer or some other result different from accepted, and then you've made a few more changes, but it still didn't work. And then you understand that your solution was wrong completely from the start. And then you invent new solution and you will have to implement it from scratch. And that means that you've wasted all the time on implementation of the first wrong solution. To avoid that, you should always prove your solution first. So after we've proved the safe move, we basically got our greedy solution, which works in combination with the sorting algorithm in time n log n, which is not only polynomial, but is very close to linear time and works really fast in practice. Hello! In this lesson, you will learn an algorithm to determine which food items and in which amounts should you take with yourself on a really long hike so that to maximize their total energy value. So, you are planning a long hike. It will take a few days or maybe a few weeks, but you don't know exactly how long will it take. So to be safe, you need to get enough food with you. And you have a knapsack which can fit up to 15 kilograms of food in it. And you've already bought some cheese, some ham, some nuts and maybe some other food items. You want to feed them all in the knapsack so that to maximize the amount of calories that you can get from them. Of course, you can cut the cheese, you can cut the ham, you can select only some of the nuts and then fit all of that into your knapsack. To solve this maximization problem, we again need to first reformulate it in mathematical terms, and then it becomes an instance of a classical fractional knapsack problem, which goes like this. We have n items with weights w1 through wn and values v1 through vn, and a bag of capacity big W. And we want to maximize the total value of fractions of items that fit into this bag. In this case, weights are also weights in the real life, and values are the energy values of the food items that you've bought. So here's an example, and we will denote by dollars the value of the item and the weight just by numbers. So for example, the first item has value $20 and has weight 4. The second item has value $18 and weight 3. And the third item has value $14 and weight 2. And we have a knapsack of capacity 7. There are a few ways with which we can fill this knapsack. For example, one of them is put the whole first item and the whole second item in the knapsack. Then the total value is the sum of the values of the first item and second, which is $38. We can improve on that. For example, take the whole first item, the whole third item, and only 1/3 of the second item, for a total value of $40. We can do even better by taking the whole third item, the whole second item, and only half of the first item. And that will give us $42. And actually it turns out that this is the optimal thing to do. So now we want to create a greedy algorithm that will solve this maximization problem. And we need to get some greedy choice and make a safe move. And to do that, we have to look at the value per unit of weight. So for example, for the first item, value per unit of weight is $5. For the second item, it's $6 per unit, and for the third one, it's $7 per unit. So although the first item is most valuable, the third item has the maximum value per unit. And of course there is an intuition that we should probably fit first the items with the maximum value per unit. And really, the safe move is to first try to fit the item with the maximum value per unit. And there's the lemma that says that there always exists some optimal solution to our problem that uses as much as possible of an item with the maximum value per unit of weight. And what do we mean by as much as possible? Well, either use the whole item if it fits into the knapsack, or if the capacity of the knapsack is less than how much we have of this item, then just fill the whole knapsack only with this item. Let's prove that this is really a safe move. We will prove looking at this example. So first, let's suppose we have some optimal solution. And let's suppose that in this optimal solution, we don't use as much as possible of the best item with the highest value per unit of weight. Then take some item which we use in this solution and separate its usage into two parts. One part of the same size of how much we have of the best item, and the second part is everything else. Then we can substitute the first part with the best item. So for example, in this case, we substitute half of the first item with second item. Of course, in this part, the total value will increase because the value per unit of weight is better for the best item than for the item currently used. And in the general case, this will also work. So either we will be able to replace some part of the item already used by the whole best item, or we can replace the whole item that is already used by some part of the best item. And in any case, if we can make such a substitution, of course the total value will increase because the best item just has better value per unit of weight, so for each unit of weight we will have more value. So this gives us a greedy algorithm to solve our problem. What we'll do is, while knapsack is still not full, we will do a greedy choice. We'll choose the item number I, which has the maximum value of Vi over Wi, which is the value per unit of weight. And then, if this item fits into knapsack fully, then take all of this item. Otherwise, if there is only a few space left in the knapsack, take so much of this item as to fill the knapsack to the end. And then, in the end, we return the total value of the items that we took and how much did we take of each item. Hi! In this lesson, you will learn how to implement the greedy algorithm for the fractional knapsack, how to estimate its running time, and how to improve its asymptotics. Here is the description of the greedy algorithm from the previous lesson. While knapsack is still not full, we select the best item left, the one with the highest value per unit of weight, and either fit all of this item in the knapsack, or if there's only a few space left in the knapsack, cut this item and fit as much as you can in what's left in the knapsack. And then repeat this process until the knapsack is full. In the end, we return the total value of the items taken and the amounts taken. We've proven that the selection of best item is a safe move, and then after we've selected the best item, what we've got left is a knapsack with a capacity which is less. But the problem is the same. You have some items and you have a knapsack of some capacity, and you should fill it optimally so as to maximize the total value of the items that fit. So this greedy algorithm really works. Now let's implement it. Here we have a procedure called knapsack. It starts with filling the array A with amounts of items taken with zeros, and the total value we also initialize to 0. And then, as we said on the slide, we repeat for n times the following iterations. If the knapsack is already full, then in the variable w we will have 0, because in the start we have in the variable w the total capacity of the knapsack, but each time we will put something in the knapsack, we will update w, we will decrease it by the amount of weight that we put already in, and so in the end, when the knapsack is full, w will be 0. If w became 0, it means that we should just return the total value and the amounts of the items that we took. Otherwise, we should select the best item. The best item is the item which is still left, so wi is more than 0. And out of all such items, it's the item with the maximum value per weight, so the one which maximizes vi over wi. When we've selected the I, we determine the amount which will we take. It is either the whole wi, the whole of this item, if it fits in the knapsack. Otherwise, if the capacity of the knapsack is already less, then we just fill it up to the end. So A is minimum of wi and big W. After we've selected the amount, we just update all the variables. So we update wi by decreasing it by A, because we took already A of this item. We also increase the amount A of I corresponding to the item number I by the value A. And we also decrease the capacity left because we just decreased it by A by putting an A of item I. Also, we increase value V by this formula A multiplied by VI and divided by WI. Why is that? Because we took A of item number I, we took A units, and 1 unit brings us amount of value equal to VI over WI. So if you take A units, the total value by this item is A multiplied by VI and divided by WI. After we do n iterations, or maybe less if the knapsack is full before we do all n iterations, we return the total value and the amounts in the array. Now, the running time of this algorithm is big O of n squared. Why is that? Well, first we have the inner selection of best item, which works in linear time, because basically we have to go through all the items to select the best one. And we have the main loop, for loop, which is executed n times, at most, maybe less. So in each iteration we do some linear time computation, and we do this at most n times. That means that the total running time is big O of n squared. Now we can improve on that, because if we sort the items by decreasing value of Vi over Wi, then it will be easier to select the best item which is still left. Let's look at this pseudocode. Let's assume that we've already sorted the input items such that V1 over W1 is more than or equal to V2 over W2, and that is greater or equal to the fraction for the next item and up to Vn over Wn. Then we again start with the same array of amounts and the same total value filled with zeros, but then we make a for loop for I going from 1 to n, and on each iteration I will be the best unit which is still left. So in the start of the iteration we check whether we still have some capacity in the knapsack. If it is already filled, we just return the answer. Otherwise, we know that I is the best item because we didn't consider it previously, and it is the item with the maximum value per unit out of those which we didn't consider before. So we determine the amount of this item with the same formula, and we update the weights, the amounts, the capacity and the total value in the same way as we did in the previous pseudocode. The only change is that we change the order in which we consider the items, and this allows us to make each iteration in constant time instead of linear time. So this new algorithm now works in linear time because it has at most n iteration, and each iteration works at most in a constant time. So if we apply first some sorting algorithm to sort items by decreasing value of vi over wi, and then apply this new knapsack procedure, total running time will be n log n, because sorting will work in n log n, and the knapsack itself will work in linear time. Hi! In this lesson, we will review what we saw in this module about greedy algorithms and specify what is common and important to all greedy algorithms. Main ingredients of any greedy algorithm are greedy choice and reduction to a subproblem. You have to prove that your greedy choice is a safe move. And also, you have to check that the problem that is left after your safe move is really a subproblem, that is a problem of the same kind but with fewer parameters. After you have both, you have a greedy algorithm. Then you need to estimate its running time and check that it's good enough for you. Safe moves in different problems are different. Basically, you have to invent something each time you have a new problem. In the first problem it was select the maximum digit and put it first, and the last problem it was select the item with the maximum total value per weight. And you see that in every safe move there is something like maximum or minimum or first or leftmost or rightmost. So always safe move is greedy, but not all greedy moves are safe. So you really have to prove every time that the move that you invented is really safe. Also, you can notice that sometimes we can optimize our initial greedy algorithm if we sort our objects somehow. So you can maybe try to solve problem assuming that everything is sorted in some convenient order, and if you see that because of that your greedy algorithm can be implemented asymptotically faster, then you can just apply sorting first and then your greedy algorithm. The general strategy is, when you have a problem, you can try to come up with some greedy choices, and then for some of them you'll be able to prove that they're really safe moves. And if you've proven that this is a safe move, then you've reduced your problem to something, and then you have to check that this something is a subproblem, that is the problem about the same thing, optimizing the same thing with the same restrictions, and then this is a subproblem. And then you can solve it in the same way that you solved your initial problem. And you have this loop from problem to subproblem and back to the problem, always reducing it by the number of parameters. And in the end of this loop, you will have a problem so simple that you can solve it right away for one object or zero objects, and then you have your greedy algorithm.
Hi, I'm Neil Rhodes. Welcome to the Divide and Conquer module. In the last module, you learned about how to use greedy algorithms to solve particular classes of problems. In this module, you'll learn about ways of solving problems using divide and conquer algorithms. The term divide and conquer is quite old, and when applied to war, suggests that it's easier to defeat several smaller groups of opponents than to try and defeat one large group. In a similar fashion, divide and conquer algorithms take advantage of breaking a problem down into one or more subproblems that can then be solved independently. Just as not all problems can be solved with a greedy algorithm, not all problems can be solved using divide and conquer. Instead, these are both techniques that are part of a toolbox of strategies to solve problems. As you're designing an algorithm, you'll need to consider whether or not a greedy algorithm might work. If not, would a divide and conquer algorithm work? Let's look at the general structure of a divide and conquer algorithm. Here we have a problem to be solved, represented abstractly as a blue rectangle. We break the problem down into a set of non-overlapping subproblems, represented here by colored rectangles. It's important that these subproblems be of the same type as the original. For example, here's a way to break down the original rectangle problem into a set of subproblems that are not of the same type. These subproblems are triangles. Thus, this does not represent a divide and conquer algorithm. In this case, we've broken down the original rectangle problem into a set of subproblems that are themselves rectangles. The difficulty is that these subproblems overlap with one another. Thus, it too does not represent a divide and conquer algorithm. We return now to breaking down our problem into a set of non-overlapping subproblems of the same original type. We break it apart. Then we go ahead and solve each subproblem independently. We solve the first problem, represented by a check mark. We then continue, solving each problem in turn. Once we've successfully solved each of the subproblems, we combine the results into a solution to the original problem. One question that comes up: how do we solve each subproblem? Since each subproblem is of the same type as the original, we can recursively solve the subproblem using the same divide and conquer strategy. Thus, divide and conquer algorithms naturally lead to a recursive solution. In practice, while you can program a divide and conquer algorithm recursively, it's not uncommon to rewrite the recursive program into an iterative one. This is often done, both because some programmers aren't as comfortable with recursion as they are with iteration, as well as because of the additional space that a recursive implementation may take, in terms of additional stack space. This can be language and implementation dependent. In summary, the divide and conquer algorithm consists of 1. Breaking a problem into non-overlapping subproblems of the same type, 2. Recursively solving those subproblems, and 3. Combining the results. In the next video, we'll see an extremely simple example of divide and conquer. We're going to start our divide and conquer algorithms with what might be considered a degenerate form of divide and conquer, searching in an unsorted array using linear search. Here's an example of an array. To find a particular element of the array, we look at the first element. If it's not there, we look at the second element. We continue until we either find the element we're interested in or until we reach the end of the array. This same type of search is also used if your elements are stored in a linked list. Let me describe a real-life use of linear search. 20 years ago, I did consulting for a company developing software for one of the first handheld computers, the Apple Newton. The application translated words between any two of the languages English, French, Italian, German, or Spanish. Its data was stored in 5 parallel arrays. So for example, car was in English at the second position. In Spanish, car is auto, so the second position of the Spanish array contained auto. The program would take the user's input word, along with from and 2 languages. Then it'd search through the corresponding from array, English for example, if trying to translate car from English to Spanish. If it found a match, it would return the element at the same index location in the target language. For a small dictionary of 3 words, as in this example, this linear search was quick. However, I was brought in as a consultant to speed up the application. When the user clicked on the translate button, it'd take 7 to 10 seconds to retrieve the translated word, an eternity as far as the user was concerned. There were about 50,000 words in the dictionary, so on average, it took 25,000 word checks in order to find a match. In the next video, I'll show you how we sped up this application using binary search. The problem statement for linear search is as follows. Given an unsorted array with n elements in it and a key k, find an index I of the array element that's equal to k. If no element in the array is equal to k, the output should be not found. Note that we say an index rather than the index to account for the fact that there may be duplicates in the array. This might seem pedantic, but it's important to be as careful as possible in specifying our problem statement. The well-known solution to this problem is a linear search. Iterate through the array until you find the chosen element. If you reach the end of the array and haven't yet found the element, return not found. We can construct a divide and conquer recursive algorithm to solve this problem. Our recursive function will take 4 parameters. A, the array of values. Low, the lower bound of the array in which to search. High, the upper bound of the array in which to search. And k, the key for which to search. It'll return either an index in the range low to high, if it finds a matching value, or not found, if it finds no such match. As with all recursive solutions, we'll need to accurately handle a base case. In particular, base cases for this problem will be either being given an empty array, or finding a match in the first element. The subproblem is to search through the subarray constructed by skipping the first element. We'll recursively search through that smaller subarray, and then just return the result of the recursive search. Although this is a recursive routine that breaks the problem into smaller problems, some would argue that this shouldn't be called divide and conquer. They would claim that a divide and conquer algorithm should divide the problem into a smaller subproblem, where the smaller subproblem is some constant fraction of the original problem. In this case, the subproblem isn't 50% or 80% or even 95% of the original problem size. Instead, it's just one smaller than the original problem size. I don't know. Maybe we should call this algorithm subtract and conquer rather than divide and conquer. In order to examine the runtime of a recursive algorithm, it's often useful to define the time that the algorithm takes in the form of a recurrence relation. A recurrence relation defines a sequence of values in terms of a recursive formula. The example here shows the recursive definition of the values in the Fibonacci sequence. You can see that we define the value for the nth Fibonacci as the sum of the preceding two values. As with any recursive definition, we'll need one or more base cases. Here, we define base cases when evaluating f of 0 and f of 1. From this recursive definition, we've defined values for evaluating f of n for any non-negative integer n. The sequence starts with 0, 1, 1, 2, 3, 5, 8, and continues on. When we're doing runtime analysis for divide and conquer algorithms, we usually define a recurrence relation for t of n, where t stands for the worst case time taken for the algorithm, and n is the size of the problem. For this algorithm, the worst case time is when an element isn't found, because we must check every element of the array. In this case, we have a recursion for a problem of size n, which consists of a subproblem of size n minus 1, plus a constant amount of work. The constant amount of work includes checking high versus low, checking a at low equals key, preparing the parameters for the recursive call, and then returning the result of that call. Thus the recurrence is t of n equals t of n minus 1 plus c, where c is some constant. The base case of the recursion is that in an empty array, there's a constant amount of work, checking high less than low, and then returning not found. Thus t of 0 equals c. Let's look at a recursion tree in order to determine how much total time the algorithm takes. As is normal, we're looking at worst case runtime, which will occur when no matching element is found. In a recursion tree, we show the problem along with the size of the problem. We see that we have an original problem of size n, which then generates a subproblem of size n minus 1, and so on, all the way down to a subproblem of size 0, an empty array. The work column shows the amount of work that's done at each level. We have a constant amount of work at each level, which we represent by c, a constant. Alternatively, we could have represented this constant amount of work with big theta of 1. The total work is just the sum of the work done at each level. That's a summation from 0 to n of a constant c, which is n plus 1 times c, or just big theta of n. This analysis seems overly complicated for such a simple result. We already know that searching through n elements of the array will take big theta of n time. However, this method of recurrence analysis will become more useful as we analyze more complicated divide and conquer algorithms. Many times a recursive algorithm is translated into an iterative one. Here we've done that for the linear search. We search through the elements of array A from index low to index high. If we find a match, we return the associated index. If not, we return not found. To summarize, what we've done is 1. Create a recursive solution. 2. Define a corresponding recurrence relation t. 3. Solved t of n to determine the worst case runtime. And 4. Created an iterative solution from the recursive one. What you've seen in this video then is an example of a trivial use of our divide and conquer technique in order to do linear search. In our next video, we'll look at a non-trivial use of the divide and conquer technique for searching in a sorted array, the well-known binary search. Hi, so let's talk now about binary search. A dictionary is a good example of a ordered list, okay, basically where every word is in order, and that makes finding words much easier. You can imagine how difficult it would be to search in a dictionary if the order of the words was random, right? You'd have to just search through every single page, and in fact every word on every page. That would take quite a long time. So let's look at the problem statement for searching the sorted array. So what we have coming in is an array, along with a low and upper bound that specify the bounds within the array in which to search. What's important about the array is that it's in sorted order. What we mean by that if we look at any index I at an element, and then the next element, that this first element is no more than the next element. We don't say less than, because we want to allow for arrays that have repeated elements. So officially this is called a monotonic, non-decreasing array. The other input is the key to look for. The output for this is an index such that the element at that index in the array is equal to the key. We say an element and not the element, just as we did in linear search, because of the fact that there may be more than one element that matches, because there may be duplicates in the array. If we don't have a match, instead of returning not found, as we did in the linear search case, we're going to actually return somewhat more useful information, which is where in the array would you actually insert the element if you wanted to insert it? Or where would it have been, okay, if it were there? So what we're going to return is the greatest index such that a sub I is less than k. That is, if the key is not in the array, we're returning an index such that if you look at the element at that index, it's less than the key, but the next element is greater than the key. And we do have to take account of the fact that what if every element in the array is greater than the key? In that case, we're going to go ahead and return low minus 1. So let's look at an example. We've got this array with 7 elements in it, and the element 20 is repeated in it. So if we search in this array for 2, we want to go ahead and return 0, saying that every element in the array is larger than this. If on the other hand we look for 3, we're going to return 1. If we look for 4, we're also going to be returning 1, which really signifies between 1 and 2. That is, it's bigger than 3, but it's less than 5. If we search for 20, we'll return 4, or we might also return 5. Either one of those is valid because 20 is present at each of those indexes. And if we search for 60, we'll return 7, but if we search for 70, we'll also return 7. So let's look at our implementation of binary search. So we're going to write a recursive routine taking in A, low, high, and key, just as we specified in the problem statement. First, our base case, right? If we have an empty array, that is if high is less than low, so no elements, then we're going to return low minus 1. Otherwise, we're going to calculate the midpoint. So we want something halfway between low and high. So what we're going to do is figure the width, which is high minus low, cut it in half, so divide by 2, and then add that to low. That might not be an integer because of the fact that high minus low divided by 2 may give us a fractional portion. So we're going to take the floor of that. For example, in the previous case where we had 1 to 7, it'll be 7 minus 1 is 6, divided by 2 is 3, plus our low is 1 is 4, so the midpoint would be 4. We'll see an example of this shortly. And now we check and see, is the element at that midpoint equal to our key? If so, we're done, we return it. If not, the good news is, of course, is we don't have to check all the other elements. We've ruled out half of them. So if the key is less than the midpoint element, then all the upper ones we can ignore. So we're going to go ahead and now return the binary search in A from low to mid minus 1, completely ignoring all this stuff over here. Otherwise, the key is greater than the midpoint, and again we can throw away the lower stuff and go from midpoint plus 1 all the way to high. Let's look at an example. So let's say we're searching for the key 50 in this array with 11 elements. So we'll do a binary search on this array from 1 to 11, looking for 50. Low is 1, high is 11. We'll calculate the midpoint. The midpoint will be 11 minus 1 is 10, divided by 2 is 5. Add that to 1, the midpoint 6. And now we check and see, is the midpoint element equal to 50? Well, no, the midpoint element's 15, and the element we're looking for, the key we're looking for, is 50. So we're going to go ahead and ignore the lower half of the array and now call binary search again with the low equal to 7, so one more than the midpoint. So now I've got a smaller version of the problem. We're looking for 50 within the elements 7 to 11. We'll calculate the midpoint. 11 minus 7 is 4, divided by 2 is 2. So we'll add that to 7 to get a midpoint of 9. We check, is the element at index 9 equal to our key? The element at index 9 is 20, our key is 50, they're not equal. However, 50 is greater than 20, so we're going to go ahead and make a new recursive call with midpoint plus 1, which is 10. So again, we do our binary search from 10 to 11, we calculate the midpoint. High minus low, 11 minus 10 is 1, divided by 2 is 1/2. plus 10 is 10.5. We take the floor of that, we get 10.5. So our midpoint is 10.5. I'm sorry, our midpoint's 10. And now we check, is the value at element 10 equal to our key? Well, the value at element 10 is 50, our key is 50, so yes. So we're going to go ahead and return that midpoint, which is 10. In summary then, what we've done is broken our problem into non-overlapping subproblems of the same type. We've recursively solved the subproblems, and then we're going to combine the results of those subproblems. Okay? We broke the problem into a problem of size half, even slightly less than half. We recursively solved that single subproblem, and then we combine the result very simply just by returning the result. In the next video, we're going to go ahead and look at the runtime for binary search, along with an iterative version. And we'll get back to actually discussing that problem that I discussed with the dictionary translation problem. We'll see you shortly. Hi. In this video, we're going to be looking at the runtime of binary search, along with looking at the iterative version of it. So here's our binary search algorithm again. We look in the middle. If it's not found, then we either look in the lower half or the upper half. So what's our recurrence relation for the worst case runtime? Well, the worst case is if we don't find an element. So we're going to look at t of n is equal to t of roughly n over 2 plus c. We have a floor there of n over 2, because if n is odd, like let's say there are 5 elements, then the question is how big is the problem size on the next call. So if we have 5 elements, we're going to either end up looking in the upper half of the array, those 2 elements, or the lower half of the array, those 2 elements, because we skipped the midpoint. We already checked that one. Plus some constant amount of work to add together, calculate the midpoint, as well as checking the midpoint against the key. And then our base case is when we have an empty array, and that's just a constant amount of time to check. So what's the runtime look like? We got our original size n, and we're going to break it down, n over 2, n over 4, all the way down. How many of these problems are there? Well, if we're cutting something in 2 over and over again, it's going to take log base 2 such iterations until we get down to 1. So the total here is actually log base 2 of n plus 1. The amount of work we're doing is c. So at each level, we're doing c work. So the total amount of work, if we sum it, is just the sum from I equals 0 to log base 2 of n of c. That is just log base 2 of n plus 1. That is log base 2 of n, that quantity, plus 1 times c. And that is just theta of log base 2 of n. Or really what we'd normally say is theta of log n, because the base doesn't matter. That's just a constant multiplicative factor. All right, what's the iterative version look like? The iterative version has the same parameters, low, high, and key, and we have a while loop that goes through similar to the base case. So in the base case of the recursive version, we were stopping if high is less than low. Here we have a while loop where the while loop stops if high is less than low. We calculate the midpoint, and then, again, check the key. If it matches the element at the midpoint, we return the midpoint. Otherwise, if the key is less than the element, we know we're in the first half of the array, and so instead of making a new recursive call, like we did in the recursive version, we have the original array, and we want to look at the first half of it, so we're going to change the value of high, and then it'll be mid minus 1, because we already checked mid. Otherwise, we want to look in the upper half of the array, so we move low up. If we reach the end of the while loop, that is, if we drop out of the while loop because high is less than low, that meant we have nothing more to search. We have an empty array. And therefore, we didn't find the element in the array. We're going to return low minus 1. So the same result as the recursive version. The difference is we won't be using the stack space that the recursive version uses. You remember we talked 2 videos ago about this real-life example where we had 5 languages, and we were translating words between any 2 of those languages. The way we had that represented was parallel arrays, so that at any given index, each of the elements of the arrays represented words that were the same in all those languages. So for instance, chair in English is at index 2, and in Spanish that's silla, and in Italian it's sedia. The problem was it took a long time to look, right? We had 50,000 elements in our arrays, and it took like 10 seconds for searching because we had to really search through all of them. If it wasn't there, on average, half of them, which is 25,000. So one question might be, why didn't we use a sorted array, right? You can imagine, for instance, sorting these arrays. Here they're sorted. The good part is it's easy to find a particular word in a particular language. So I can find house in English, for instance, and find what index that is at very quickly using a binary search. The problem is I no longer have this correspondence because the order of the words that are sorted in English is different from the order of the words sorted in Spanish. So if I look at chair, for instance, in English, it no longer maps to silla. So instead, if I look at chair, it maps to casa. So although we can find a particular word in our source language, we don't know the corresponding word in the target language. So the solution was to try and find some way we could do sorting and yet still preserve this relationship where everything at an index meant really the same translated word. And the way to do that was an augmented array, or set of arrays. So what we really did was keep this augmented arrays which were pointers back into the original arrays in sorted order. Okay, so we're having kind of a level of indirection here. So if I look at English, for example, the order of the words in English is chair, house, pimple. Well, what order is that in the original array? It is first element 2, and then element 1, and then element 3. So if you want to do a binary search, you can use this sorted array. But whenever you want to look at what's the element that is in that represented sorted array, so for instance, if we looked at the middle element, so which in the sorted array is 2, it has the value 1, and that says go find house. So we basically say house is sort of at element 2, and chair is at element 1, and pimple is at element 3. The Spanish, of course, has different mapping. So in Spanish, the first sorted word happens to be the first word in the array. The second sorted word is the third word in the Spanish array, and the third sorted word, silla, is the second element. So what happened when we ran this? Well, what happened, we had a space-time trade-off, right? We had to pay extra space. And there were, of course, not only just English and Spanish sorted, but also French, Italian, and German. So 5 arrays, extra arrays. Each array had 50,000 entries in it. And what was the size of each element of the array? Well, it represented a number from 1 to 50,000. That can be represented in 16 bits, which is 2 bytes. So we had 50,000 elements times 2 bytes. So that is 100,000 bytes. Times 5 is 500,000 bytes, so about a half a megabyte, which today is almost nothing, and even then was certainly doable 20 years ago. That's the cost we have in sort of space. What is the benefit that we get? Well, instead of having to do, let's say, 50,000 lookups in the worst case, instead we have to do log base 2 of 50,000 lookups. So log base 2 of 50,000 is about, let's see, log base 2 of 1,000 is about 10, goes 2 to the 10th equals 1024. So we have another factor of 50 to go. Log base 2 of 50 is around, let's say, 6, because I know that 2 to the 5th is equal to 32, 2 to the 6th is 64. So what that means is we have 16 references we have to do to the array instead of 50,000. That's almost a factor of 1,000. So what that ended up meaning is that when the user clicked translate, instead of taking 10 seconds, it was what appeared to be instantaneous. It was well under a tenth of a second. So in summary, what we've seen is that the runtime in binary search is big theta of log n, substantially quicker than the big theta of n that linear search takes. So sorted arrays really help. In the next lesson, we're going to be looking at a more complicated application of divide and conquer, where we actually have multiple subproblems instead of just one subproblem. In this lecture, we're going to talk about a more complicated divide and conquer algorithm to solve polynomial multiplication. So first, we'll talk about what polynomial multiplication is. So polynomial multiplication is basically just taking 2 polynomials and multiplying them together. It's used in a variety of ways in computer science. Error correcting codes. If you want to multiply large integers together, right? So if you've got 1,000-digit integers and you want to multiply them together, there's a quicker way than doing it the normal way you learned in elementary school. and that uses the idea of multiplying polynomials. It's used for generating functions, for convolution. Let's look at an example. So let's say you have polynomial A, which is 3x squared plus 2x plus 5, and polynomial B, which is 5x squared plus x plus 2. If you multiply them together, you get 15x to the fourth plus 13x cubed plus 33x squared plus 9x plus 10. Why is that? Well, let's look. For instance, the 15x to the fourth comes from multiplying 3x squared times 5x squared. That's 15x squared. The 10 comes from multiplying 5 by 2. The 13x cubed comes from 3x squared times x, which is 3x cubed, plus 2x times 5x squared, which is 10x cubed, for a total of 13x cubed. So let's look at the problem statement. So we're going to have two n minus 1 degree polynomials, right? A sub n minus 1 is the coefficient of the x to the n minus 1, all the way down to a0, which is the coefficient of the x to the 0 term, or the 1 term. And then we similarly have b polynomial as well. Now, first you may wonder, what happens if you actually want to multiply polynomials that don't happen to have the same degree? What if you want to multiply a degree 3 polynomial times a degree 2 polynomial, right? And where the degree is just the exponent of the highest term. Well, in that case, what you can do is just pad out the smaller polynomial, the lower degree polynomial, to have zeros for its earlier coefficients. I'll give you an example of that in just a second. And then the product polynomial is the result that we want to come up with. So that's a higher degree polynomial, right? If our incoming polynomials are of degree n minus 1, then we're going to get a term of the x to the n minus 1 in A times x to the n minus 1 in B, and that's going to give us an x to the 2n minus 2 in the C term. Right? So the C to the 2n minus C sub 2n minus 2 term comes about from multiplying the A sub n minus 1 term and the B sub n minus 1 term. The C sub 2n minus 3 term comes from the A sub n minus 1, B sub n minus 2, and A sub n minus 2, B sub n minus 1. So it's got two terms that multiply together. The C sub 2n minus 4 term would have 3 terms that multiply together. And we have more and more terms that get multiplied and summed together, and then fewer and fewer back down. So C sub 2 has 3 pairs which get added together. C sub 1 has 2 pairs, and C sub 0 has 1 pair. So here's an example. This is actually the same example we had before. So n is 3, and all we need, notice, are the coefficients. We don't actually need to have the x's written out. So 3, 2, and 5 means 3x squared plus 2x plus 5. 5, 1, 2 means 5x squared plus x plus 2. What if b were only a degree 1 polynomial? It was just x plus 2. Well, then we would set b equal 0, 1, 2. That is, b's x squared term is 0x squared. Okay. So a of x is this, b of x is that. When we multiply them together, we get the same result we got before. And now we just pluck off the coefficients here. So the 15, the 13, the 33, the 9, and the 10. And that's our resulting answer, those coefficients. So let's look at a naive algorithm to solve this. Naive algorithm basically just says, well, first off, let's create a product array. This is basically going to be the C, the result. And it's going to be of highest degree 2n minus 2. So it's going to have 2n minus 1 terms, all the way from the 0 term up to the 2n minus 2 term. So we'll initialize it to 0, and then we'll have a nested for loop for I equals 0 to n minus 1, for j equals 0 to n minus 1, and at every time what we'll do is we will calculate a particular pair. So we'll calculate the a sub I, b sub j pair, multiply them together, and add them into the appropriate product. Right? Which is the appropriate product to put it in? It's the I plus j case. As an example, when I is 0 and j is 0, we calculate a at 0 times b at 0, and we add that to product at 0. So that says the two 0 degree terms in A and B get multiplied together to the 0 degree term in C. At the other extreme, if I is n minus 1 and j is n minus 1, we take A at n minus 1 times B at n minus 1, and we store that into product of 2n minus 2. As you can see, the intermediate values in product are going to have more terms added to them than the edges. And of course, then we return the product. How long does this take? Well, this takes order n squared. Clearly, like, we've got two for loops, one smaller for loop that's from 0 to 2n minus 2, so that's order n, and then a nested for loop where I goes from 0 to n minus 1, j goes from 0 to n minus 1, so those each go through the first one n times, the second one n squared times, so our runtime is order n squared. In the next video, we're going to look at a divide and conquer algorithm to solve this problem, although we'll see that it too will be somewhat naive. So in this video, let's look at a naive divide and conquer algorithm to solve polynomial multiplication problem. The idea is we're going to take our long polynomial and we're going to break it into two parts, the upper half and the lower half. So a sub x is going to be d sub 1 of x times x of n over 2 plus d sub 0 of x, which is the bottom half. D sub 1 of x, since we've pulled out x sub n over 2 terms, its lowest term is actually just a sub n over 2. So we have two parallel subpolynomials, the high and the low. We do the same thing for b, so we break that into e sub 1 of x and e sub 0 of x. Again, where e sub 1 of x is the high terms, e sub 0 of x is the low terms. When we do our multiplication, then we just multiply together d1 x sub n over 2 plus d0 and e1 times x sub n over 2 plus e0. And that then yields four terms. d sub 1 e sub 1 times x sub n, d sub 1 e sub 0 plus d sub 0 e sub 1 times x sub n over 2 plus d sub 0 e sub 0. The key here is that we now just need to calculate d1 e1, d1 e0, d0 e1, and d0 e0. Those are all polynomials of degree n over 2. And so now we can go ahead and use our recursive solution to solve this problem. So this gives us a divide and conquer problem. Its runtime is t of n equals 4 t of n over 2. Why 4? 4 because we're breaking into 4 subproblems. Each of them takes time t of n over 2 because the problem has been broken in half. Plus then, in order to take the results and do our addition, that's going to take order n time. So some constant k times n. Let's look at an example. So we have n is 4, so we have degree 3 polynomials, and we're going to break up a of x into the top half, 4x plus 3, and the bottom half, 2x plus 1. Similarly, we're going to break up the top half of b of x cubed plus 2x squared just becomes x plus 2, and 3x plus 4 stays at 3x plus 4. Now we compute d1 e1, so multiplying together 4x plus 3 times x plus 2 gives us 4x squared plus 11x plus 6. Similarly, we calculate d1 e0, d0 e1, and d0 e0. Now we've done all four of those computations. B is just d1 e1, 4x squared plus 11x plus 6, times x to the fourth, plus the sum of d1 e0 and d0 e1 times x squared, plus finally d0 e0. If we sum this all together, we get 4x to the sixth plus 11x to the fifth plus 20x to the fourth plus 30x cubed plus 20x squared plus 11x plus 4, which is the correct solution. Now, how long does this take to run? We're going to look at that in a moment. Let's look at the actual code for it. So we're going to compute a resulting array from 0 to 2 to the n minus 2. So those are all the result coefficients. And our base case is that if n is of size 1, we're going to multiply together a at a sub l plus b at b sub l. Let's look at those parameters again. So a and b are our arrays of coefficients. N is the size of the problem. A sub l is the first coefficient that we're interested in, and b sub l is the coefficient in b that we're interested in. So we're going to be going from a sub l plus 1, a sub l plus 2, etc., n for n times. First thing we'll do is multiply together the d sub 1 and e sub 1. So basically what we're doing, the d sub 0 and e sub 0. So what we're doing is taking a and b, we're reducing the problem size by 2, and we're starting with those same coefficients. And we're going to assign those to the lower half of the elements in R. Then we're going to do something similar where we take the upper halves of each of A and B. So again, the problem size becomes n over 2, but now we're moving the low coefficient we're interested in from A sub L to A sub L plus n over 2, and B sub L to B sub L plus n over 2. And we're going to assign those to the high coefficients in our result. Then what we have to do is calculate d sub 0 E1 and d1 E0, and then sum those together. When we sum those together, we're going to assign those to the middle elements of the resulting array. And we'll then return that result. Now the question comes up, how long does it take? So we have an original problem of size n. We break it into 4 problems of size n over 2. So level 0, we have size n. Level 1, we have size n over 2. At level I, our problems are of size n over 2 to the I. And all the way down to the bottom of the tree is at log base 2 of n, and each of the problems are of size 1. How many problems do we have? At level 0, we have 1 problem. We have then 4 problems. If we go to the ith level, we have 4 to the I problems. And at the very bottom, then, we have 4 to the log base 2 of n problems. How much work is there? Well, we just need to multiply together the number of problems times the amount of work. So we have kn here. And then we have 4 times 4, because there are 4 problems, kn over 2. Because the problem size is n over 2, and the amount of work we're doing at each level is k times n over 2 per problem. So 4k n over 2 just equals k times 2n. At the ith level, 4 to the I problems. Each problem takes k times n over 2 to the I to deal with. We multiply together k 2 to the I times n. And at the very bottom, we have k amount of work. We have a problem size of 1 times 4 to the log base 2 of n. Well, 4 to the log base 2 of n is just n squared. So we have kn squared. Our total, as we sum up all the work, is going to be the summation from I equals 0 to log base 2 of n of 4 to the I, k times n over 2 to the I. And that just gets dominated by the very bottom term, which is theta, big theta of n squared. So that's what our runtime takes. This is kind of weird. We went through all this work to create a divide and conquer algorithm, and yet the runtime is the same runtime as it was with our naive original algorithm. We're going to see in the next video a way to redo our divide and conquer algorithm so we have less work to do at each level, and so we actually get a better final runtime. In this video, we'll look at creating a faster divide and conquer algorithm in order to solve the polynomial multiplication problem. This approach was invented by Karatsuba in the early 1960s. So he was a graduate student of Kolmogorov, a famous Russian mathematician. And Kolmogorov theorized that n squared was the best that one could do, so that there was a lower bound of n squared on doing polynomial multiplication. Karatsuba, a grad student, heard the problem, went away, came back a week later with a solution. So let's look at what is involved. So if we look at a of x, let's look at just a very simple polynomial. a1x plus a0, and bx is b1x plus b0, and then cx is what we'd imagine there, a1b1x squared plus a1b0 plus a0b1 plus a0b0. So we'll notice here we need 4 multiplications. We need to multiply a1 times b1, we need to multiply a1 times b0, a0 times b1, and a0 times b0. This is how we did the divide and conquer, in fact, in our last video. So we need 4 multiplications. Karatsuba's insight was that there was a way to rewrite c of x so that you only needed to do 3 multiplications. So basically what he did is he rewrote that inner term, a1b0 plus a0b1, as something slightly more complicated. So he added together a1 and a0 times b1 plus b0. So a1 plus a0 times b1 plus b0 is just a1b1 plus a0b1 plus a1b0 plus a0b0. And then he subtracted out the a1b1 and the a0b0. So he's left with a1b0 plus a0b1, which is exactly what's there to begin with. The key here, though, is how many multiplications are needed. It only needs 3 multiplications. We need to compute a1b1, even though we use it twice. We need to compute a0b0, even again though we need we use it only twice. And then we need to multiply together a1 plus a0 and b1 plus b0. So we do have some extra additions, but the key is we only have 3 multiplications instead of 4. Why does this matter? Well, why it matters is because we are reducing the number of problems at each level. But let's first look at an example. So here we've got a of x, we're going to have 4x cubed plus 3x squared plus 2x plus 1, b of x, x cubed plus 2x squared plus 3x plus 4. We're going to go ahead and pull out d1 and d0 like we did before, right, in our divide and conquer. The key is what we're going to actually do in terms of these subproblems. So we have d1 and we have d0, we have e1 and we have e0. We're going to compute d1, e1, again, just like we did before. We're going to compute d0, e0, again, just like we did before, but now we won't compute d1, e0 and d0, e1. Instead, we're going to sum together d1 and d0, sum together e1 and e0. Okay. So d1 plus d0 is going to be 6x plus 4, e1 plus e0 is going to be 4x plus 6, and then we multiply those two polynomials together, yielding 24x squared plus 52x plus 24. So far, how many multiplications have we done? 3. And then our final result for a of x times b of x is d1 e1 times x to the 4th plus, now what do we do here? We take that d1 plus d0 times e1 plus e0, 24x squared plus 52x plus 24, okay, add that in the second term, and then subtract out d1 e1, subtract out d0 e0, and then our final term will be d0 e0. If we simplify that middle portion and all of it, we just end up with 4x6 plus 11x to the 5th plus 20x to the 4th plus 30x cubed plus 20x squared plus 11x plus 4, which is the exact same result we got doing it in the more naive divide and conquer. And also the same way we do it if we did a straight naive problem. Okay. So we get the same result, 3 multiplications instead of 4 multiplications. That extra multiplication makes a big difference. Let's look at our runtime. So our initial problem is of size n. When we break it down, we have 3 problems of size n over 2, again, rather than 4. So level 0, problem of size n. Level 1, a problem of size n over 2. At level I, our problems are of size n over 2 to the I, just like they were in the other divide and conquer problem. And we have the same number of leaves. So at log base 2 of n level, all the problems are of size 1. And the number of problems that we have, 1 at the level 0, 3 instead of 4 at level 1, 3 to the I instead of 4 to the I at level I, and 3 to the log base 2 of n instead of 4 to the log base 2 of n at the bottom level. How much work? We'll multiply together. So we'll figure out for each problem how much it takes. In this case, at level 0, it's kn. At level 1, each problem takes kn over 2 work, and there are 3 of them, so it's k times 3 halves n. At the ith level, we end up with k times 3 halves to the in. And at the bottom level, k times 3 to the log base 2 of n. A to the log base b of c is the same thing as c to the log base b of a. So therefore, this is the same as k n to the log base 2 of 3. We sum those. Summation from I equals 0 to log base 2 of n of 3i, 3 to the I, times k, times n over 2 to the I. This is bounded, this geometric series bounded by the last term, which is big theta of n to the log base 2 of 3. Log base 2 of 3 is about 1.58, so we now have a problem where our solution is big theta of n to the 1.58. Compared to our original problem, which had a big theta of n squared solution. So this makes a huge difference as n gets large in terms of our final runtime. It's not uncommon for divide and conquer algorithms sometimes to require sort of a way of looking at it in terms of breaking up a problem so that you have fewer subproblems. And because of the compounding of the fact that the more subproblems at a level, you have more and more and more, reducing the number of subproblems reduces the final runtime. Today we're going to talk about the master theorem. We'll describe what the master theorem is and how to use it, and we'll reserve to the next video a proof. So we've had many occasions where we have had to write a recurrence relation for a divide and conquer problem. This is an example of one for binary search. We break a problem down into a problem half as big, and we do a constant amount of work at each level, and this gives us a solution, t of n equals big O of log n. The problem is, for each one of these, we have to create a recurrence tree, figure out how much work is done at each level, sum up that work. That's a lot to do to solve each recurrence relation. Here's an example that we used for the polynomial multiplication. So we broke our problem into 4 subproblems, each half the size, and did a linear amount of work. And the solution was t of n equals big O of n squared. When we had the more efficient algorithm, where we had only 3 subproblems instead of 4, we then got a solution of big O of n to the log base 2 of 3. Sometimes we break a problem into only 2 subproblems, and there the solution's big O of n log n. So wouldn't it be nice if there was a way that we just had a formula to tell us what the solution is, rather than having to create this recurrence tree each time? And that's what the master theorem basically does. So the master theorem says, if you have a recurrence relation, t of n equals a, some constant, times t of the ceiling of n divided by b, plus a polynomial in n with degree d. And that ceiling, by the way, could just as well be a floor or not be there at all if n were a power of b. In any case, the a is a constant greater than 0, b is greater than 1 because we want to actually make sure the problem size gets smaller, and d is greater than or equal to 0. Well, in that case, we have a solution for t of n. There are 3 subcases. Case number 1, and all these cases depend on the relationship between d, a, and b. In particular, is d greater than log base b of a? If so, the solution is just this polynomial in n, big O of n to the d. If d is exactly equal log base b of a, then the solution is big O of n to the d with an extra factor of log n. And finally, if d is less than log base b of a, then this solution is big O of n to the log base b of a. So let's look at some applications of this theorem. So here's one where we go back to the polynomial multiplication. Here, a is 4, b is 2, and d is 1, because big O of n is just big O of n to the 1. And we look at the relationship between d, which is 1, and log base b of a, which is log base 2 of 4, or 2. Well, clearly d is less than log base b of a, so we're in case 3. Therefore, t of n equals big O of n to the log base b of a, or just big O of n squared. If now we change the 4 to a 3, a is 3, b is 2, d is 1, now d is still less than log base b of a, because log base 2 of 3 is greater than 1. And so, again, we're in case 3. T of n equals big O of n to the log base b of a, which equals big O of n to the log base 2 of 3. If we reduce the 3 down to a 2, what happens? Well, here, a is 2, b is 2, d is 1. Log base b of a is log base 2 of 2, which is just 1. So now d is equal log base b of a. We're in case 2 now. And so t of n equals big O of n log n. And now this shows an example also of case 2. So this is the binary search example. A is 1, b is 2, d is 0. Well, the log base 2 of 1, log base b of a, is equal to 0. So d is equal log base b of a. We're in case 2. T of n equals big O of n to the d log n, which is in the 0 log n, which is just big O of log n. And a final example where we're actually in case 1. So here, a is 2, b is 2, and d is 2. So log base b of a is log base 2 of 2, which is 1. So d is now greater than log base b of a. We're now in case 1. T of n equals big O of n to the d, which is big O of n squared. So what we've seen now is that we have this master theorem that allows us, for most recurrences having to do with divide and conquer, which fit into this general formula, allows us to easily figure out which case we are based on the relationships between a, b, and d, and then figure out the result quite quickly. In our next video, we'll look at a proof of why the master theorem works. In this video, we'll look at a proof of how the master theorem works. So a reminder, the master theorem states that if t of n equals a of t of the ceiling of n over b plus a polynomial, then we have these 3 cases. So let's do as we normally do with a recurrence relation. Let's create a recurrence tree. So we'll have our recurrence at the top, just to remind ourselves what that is. let's assume for the sake of argument that n is a power of b. That's a reasonable assumption since we can always just pad n to be larger, right? If we increase it by no more than b, we can get to the next closest power of b. And then this will be a simpler analysis. So we have our problem n. At the next level, we break the problem down into a copies of a problem n over b large. So level 0, we have a problem of size n. Level 1, we have problems of size n over b. At the general level I, we have problems of size n over b to the I. And at the bottom level, which is level log base b of n, we have problems of size 1. All right, how many problems are there? At level 0, there's, of course, one problem. At level 1, a problems. And in general, at the ith level, a to the I problems. At the log base b of n level, it's a to the log base b of n. How much work do we have to do? Well, work is just a function of how many problems we have and the amount of work for each problem. So at level 0, we have just big O of n to the d work. There's one problem, and it takes big O of n to the d time. At level 1, we have a problems, and each of them take big O of n over b to the d work. Okay, we can pull out the a and the b and the d to be all together, and that's just big O of n to the d times a over b to the d. At the ith level, we have a to the I problems, and each one is big O of n over b to the I to the d. Okay. Again, we can pull out the a to the I, the b to the I, and we're left with big O of n to the d times a over b to the d to the I. And finally, at the bottom level, it's just a to the log base b of n, because the problems are all size 1, which is just big O of n to the log base b of a. Okay. So the total amount of work is the summation from 0 to the log base b of n, big O of n to the d, times the quantity a over b to the d, all that to the I. So let's look at what seems like a slight digression, and that is geometric series. So a geometric series is a series of numbers that progresses by some multiplicative factor. I'll give you an example. If we take 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, that's a geometric series, okay, where our factor is a factor of 2 at each time. Just as well, we could have a geometric series that goes down. So we could have, for instance, let's say 10,000, 1,000, 100, 10, 1, where we're going down by a constant factor of 10 at each point. Now it turns out our multiplicative factor, let's call that r, as long as r is not equal to 1, we have a simple closed form for this. This is just a times the 1 minus r to the n over 1 minus r. And it turns out that in big O notation, what happens is we care about the largest term, okay? So our sum is going to be bounded by a constant times our largest term. So if r is less than 1, then our largest term is the first element, a, and therefore our solution is big O of a, okay? Because that's our largest term, it gets smaller, 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 smaller. And as long as it's by this multiplicative factor, then all that really matters is this first term, because the rest of it sums to no more than a constant times that first term. If, on the other hand, r is greater than 1, then what matters is the very last term, because that's the biggest term, and all the previous ones are smaller and smaller. So it's smallest, larger, 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 largest. Okay? And so that largest term is a r to the n minus 1. So in a geometric series, we care about either the first term or the last term, whichever one's bigger. Now, if we take that back to the case of our recurrence tree, we notice our summation here. This is the same summation we had from our recurrence tree. And we see that we have a geometric series. Okay? A is taking the place of big O of n to the d, and r is taking the place of a over b to the d. Okay, so our multiplicative factor is a over b to the d. And there are 3 cases. We remember, as we stated the solution of the master theorem, Case 1 is d is greater than log base b of a. Well, it's equivalent to saying a over b to the d is less than 1. So now we have our multiplicative term is less than 1, so it's getting smaller and smaller and smaller. That means that the largest term is the first term, and that's the one that we have an order of. So this is big O of, officially big O of n to the d, which is just the same as big O of n to the d. Case 2, where d equals log base b of a, and equivalently, a over b to the d is equal to 1. Well, if a over b to the d is equal to 1, remember our geometric series formula didn't hold. All right? So we're going to just have to calculate this. But if a over b to the d is 1, then a over b to the d to any power is still 1. So that means that our summation is just the summation from I equals 0 to log base b of n of big O of n to the d. And that's just 1 plus log base b of n, because that's the number of terms in our summation, times big O of n to the d. Well, the 1 is a lower order term we don't care about, and the log base b of n can just be treated as log n, because a base change is just some multiplicative factor, and that disappears in our big O notation. So we end up with, as we stated in the theorem, big O of n to the d times log n. And then our final case is d is less than log base b of a, which is equivalent to saying a over b to the d is greater than 1. So here, our multiplicative factor is greater than 1, so our smallest term is the first term, and our largest term is the last term. So in this case, this is big O of, our last term is big O of n to the d times a over b to the d log base b of n. So I is log base b of n. Well, this is a bit of a mess. Let's see whether we can fix this a little bit. So let's go ahead and apply the log base b of n power separately to a and b to the d. So we have in the numerator a to the log base b of n, and then the denominator b to the d times log base b of n. Well, b to the log base b of n is just n, so that's going to disappear down to n to the d in the denominator. In the numerator, a to the log base b of n, by logarithmic identity, is equal to n to the log base b of a. So we can swap those outer two. And now if we compare big O of n to the d and n to the d, we know big O of n to the d is bounded by some constant, k times n to the d. So we have k n to the d divided by n to the d, which is just some k. And that constant can go away because we're still talking about big O notation. So we're left just with big O of n to the log base b of a, which is what we have for the final case. So the master theorem is a shortcut. Our master theorem, again, as a restatement, is here. I have a secret to tell you, however. I do not remember the master theorem, and I don't actually even look up the master theorem. Here's what I do. When I have a recurrence of this rough form, I look at the amount of work done at the first level and at the second level, which is a very easy calculation. And then I just say to myself, is that the same amount of work? If it's the same amount of work, it's going to be the same amount of work all the way down, and so we're going to be in case 2. So it's going to be the amount of work at the first level, which we know is big O of n to the d, times log n, because there are that many levels. On the other hand, if the first term is larger than the second term, I know the first term is going to dwarf all the other terms, and so we're left with just big O of n to the d. And finally, if the first term is less than the second term, I know they're going to keep increasing, and it's the bottom term that I need. And that is just going to be the number of leaves, which is n to the log base b of a. The master theorem is really handy to use, whether you memorize it, or you have it written down and use it, or, in my case, you sort of recreate it every time you need it. Thanks.
Hello, and welcome to the sorting problem lesson. As usual, we start with a problem overview. So sorting is a fundamental computational problem. Your input in this problem consists of a sequence of n elements, and your goal is to output these elements in, for example, non-decreasing order. The formal statement of this problem is as follows. You are given a sequence of n elements. We will usually denote the sequence by a throughout this lesson. And your goal is to output these n elements in non-decreasing order. Once again, sorting is an important computational task used in many efficient algorithms. For some algorithms, it is just important to process given elements in non-decreasing order, going from smaller ones to larger ones. In some other algorithms, just by sorting your input data, you gain a possibility to perform your queries much more efficiently. A canonical example of such situation is a search problem. In this problem, you are given a sequence of n elements, and your goal is to check whether a particular element is present in your sequence. A simple way to solve this problem is, of course, just to scan your input sequence from left to right and to check whether your element is present in this sequence. This gives you a linear time algorithm. And you know already that if your input data, if your input sequence is sorted, then you can do this much more faster, basically in time, in logarithmic time in the size of your input sequence. So you first compare your element to the middle element. If it is just your element, then you are done. If it is not, you continue with either the left half of your sequence or the right half of your sequence. So in logarithmic number of comparison, on the worst case, you will be able to say whether your element is present in the sequence or not. So if you are given a sequence and you are expecting many such queries, I mean, you are expecting to be asked to check whether a given object is present or not for many such objects, then it just makes sense to first sort your input data and only then perform all these queries. This will give you a much more efficient algorithm in general. Right? And this is only a small example. We will see many other situations where sorting your data first helps to perform queries much more efficiently. So in the subsequent videos of this lesson, we will study many efficient sorting algorithms. In this video, we will study one of the simplest sorting algorithms called selection sort. So its main idea is quite simple. So we just keep growing the sorted part of our array. So let me illustrate this on a toy example. Assume we are given a sequence of lengths 5 consisting of 5 integers, 8, 4, 2, 5, and 2. So we start just by finding one of the minimum elements in this array. So in this case it is 2. Now let's do the following. Let's just swap it with the first element of our array. After swapping, 2 stays in its final position. So 2 is the minimum value of our array, and it is already in its first position. Now let's do the following. Let's just forget about this element. It is already in its final position. And let's repeat the same procedure with the remaining part of our array. Namely, we again first find the minimum value. It is again 2. We swap it with the first element of the remaining part, and then we just forget about this element. So again, we find the minimum value, which is now 4. We swap it with the first element of the remaining part, which is now the third element of our array. And then we just forget about first 3 elements, and we continue with only remaining part. So once again, we just keep growing the sorted part of our array. In the end, what we have is that the whole array is sorted. The pseudocode shown here on the slide directly implements the idea of the selection sort algorithm that we just discussed. So here we have a loop where I ranges from 1 to n. Initially I is equal to 1. Inside this loop, we compute the index of a minimal value in the array with indices from I to n. Namely, we do this as follows. So we create a variable min index, which is initially equal to I, and then we go through all the remaining elements inside this part, I mean through elements from I plus 1 to n, and if we find a smaller element, we update the variable min index. So in the end of this for loop, what we have is that min index is the position of a minimal element inside the array with indices from I to n. Then we swap this element with the element AI. Namely, when I is equal to 1, what we've done, we've found the minimal element in the whole array, and we swapped it with the first element. So now the first element of our array is in its final position. Then on the second iteration of outer loop, we do the same actually. We find the minimum value, the position of a minimal value inside the remaining part of our array and put it on the second place. On the third loop, we find the minimum value in this remaining part and put it on the third place, and so on. So we keep growing the sorted part of our array. So, and it would be useful to check the online visualization to see how it goes. So let's do this. This visualization shows how selection sort algorithm performs on a few different data sets, namely on the random data sets, on a data set, on a sequence which is nearly sorted, also on a sequence which is sorted in reversed order, and on a sequence which contains just a few unique elements. So let's run this algorithm and see what happens. So you can see that indeed this algorithm just grows the sorted region, the sorted initial region of our array. So another interesting property that is revealed by this visualization is the following. So the running time of this algorithm actually does not depend on input data. So it only depends on the size of our initial sequence. The total running time of our algorithm is quadratic, and this is not difficult to see, right? So what we have is two nested loops. In the outer loop, I ranges from 1 to n. In the inner loop, j ranges from I plus 1 to n to find a minimum inside the remaining part of our array. So in total, we have a quadratic number of iterations. At this point, however, we should ask ourselves whether our estimate for the running time of the selection sort algorithm was too pessimistic. And this is what I mean by this. So recall that we have two nested loops. In the outer loop, I ranges from 1 to n. In the inner loop, j ranges from I plus 1 to n. So when I is equal to 1, the number of iterations of the inner loop is n minus 1. However, when I is equal to 2, the number of iterations of the inner loop is n minus 2, and so on. So when I increases, the number of iterations of the inner loop decreases. So a more accurate estimate for the total number of iterations of the inner loop would be the following: n minus 1 plus n minus 2 plus n minus 3, and so on. So it is definitely less than n squared, right? However, we will show that asymptotically it is equal to n squared. Namely, this is set of n squared, and it is roughly equal n squared divided by 2. The sum that we need to estimate is called an arithmetic series, and there is a known formula for this sum. Namely, 1 plus 2 plus 3 plus and so on n is equal to n multiplied by n plus 1 divided by 2. And this is how we can prove this formula. Let's just write all our n integers in a row. So 1, 2, and so on n. Below them, let's write the same set of integers, but in the reversed order. So n, then n minus 1, and so on, 2, and 1. Then what we get is a row of size 2 by n, having n columns, and in each column the sum of the corresponding two integers is equal to n plus 1. Right? So in the first column we have n and 1, in the second column we have 2 and n minus 1, and so on. In the last column we have n and 1. So the sum in each column is equal to n plus 1. And there are n columns, which means that the sum of all the numbers in our table is equal to n multiplied by n plus 1. So since this table contains our sum, the sum of the integers from 1 to n twice, we conclude that the sum of all the numbers from 1 to n is equal to n times n plus 1 divided by 2. Another possibility to find this formula, to see why this formula is correct, is to take a rectangle of size n, of dimensions n multiplied by n plus 1, so its area is equal to n multiplied by n plus 1, and to cut it into two parts, such that as shown on the slide, such that the area of each of these two parts is equal to 1 plus 2 plus and so on n. We are now ready to conclude. So we've just discussed the selection sort algorithm. This algorithm is easy to implement, easy to analyze, and its running time is n squared, where n is the size of the input sequence. So it sorts the input sequence or an array in place meaning that it requires almost no extra memory. I mean, all extra memory which is required by this algorithm is only for storing indices like I, j, and min index. There are many other quadratic algorithms like insertion sort and bubble sort. We are not going to cover them here, and instead, in the next video, we will proceed to a faster, asymptotically faster merge sort algorithm. In this video, we will study the so-called merge sort algorithm. It is based on the divide and conquer technique, which main idea is the following. To solve a given computational problem, you first split it into two or more disjoint subproblems. Then you solve each of these subproblems recursively. And finally, you combine the results that you get from the recursive calls to get a result for your initial subproblem. And this is exactly what we're going to do in the merge sort algorithm. So let's show a toy example. We are given an array of size 8 and we are going to sort it. First, we just split this array into two halves of size 4, just the left half and the right half. Then we make two recursive calls to sort both these parts. These are two resulting arrays. Now what remains to be done is to merge these two arrays into these two arrays of size 4 into one array of size 8. Well, let's think how this can be done. First of all, I claim that it is easy to find the minimal value in the resulting array. Indeed, we know that the minimum value in this case in the first array is 2 and the minimum value in the second array is 1, which means that the minimum value in the resulting merged array must be 1. Right? So let's take 1 from the right subarray, put it in the resulting array and forget about it. It is already in its right place. Right? What remains is an array of size 4 and an array of size 3 that still need to be merged. Well, again, it is easy to find the minimum value of the result of merging these two arrays. In this case, it is 2, because the minimum value in the array of size 4 is 2, and the minimum value in the arrays of size 3 is 6. So 2 is smaller than 6, so we get 2 out of our left array, put it into the resulting array after 1, and proceed. Right? In the end, we get the following sorted array. Again, the pseudocode of the merge sort algorithm directly implements this idea. So this pseudocode takes an input array A of size n as an input, and if n is equal to 1, then in this case just nothing needs to be done. We can just return the array A itself. If n is greater than 1, on the other hand, then we split the array A into two roughly equal parts and sort them recursively. We call them B and C here. Then the only thing that needs to be done is to merge these two sorted arrays. So this is done in the procedure merge, which we will present on the next slide. And finally, we just return the result of this merging procedure. The pseudocode of the merging procedure is also straightforward. Assume that we are given two sorted arrays B and C of size P and Q respectively, and we would like to merge them into a sorted array of size P plus Q. So the first thing we do is create an array of size P plus Q, an array D. It is initially empty. Then we keep doing the following thing. So what is the minimum value among all the values stored in the arrays B and C? Well, it is easy to find. We know that the first element in the array B is its smallest element, and the first element in the array C is its smallest element. So the smallest one among these two is the smallest element inside the union of these two arrays, right? So we just find the minimum of these first elements and move it from one of these arrays to the resulting array D, and forget about this element completely. Now what is left is essentially the same problem. We are left with two sorted arrays and we still need to merge them. So we do exactly the same. We take the first two elements, we compare them, and move the smaller one to the resulting array. And we keep doing this while both of these arrays are empty. I mean, we need this to be able to take the first elements. When one of them becomes empty, we just copy the rest of the other array to the resulting array D. I mean, we append this rest to the resulting array D. Well, it is not difficult to see that this procedure is correct, and its running time is p plus q, namely the size of the array b plus the size of the array q. And this is just because we just scan both of these arrays from left to right in the run of this merging procedure. This is how sorting our initial array of size 8 by the merge sort algorithm looks like. So the merge sort algorithm first splits the initial array of size 8 into two arrays of size 4. Each of these arrays of size 4 in turn is split into two arrays of size 2, and each of them is split into two arrays of size 1. Then merge procedure starts merging these arrays of size 1 into arrays of size 2, then these arrays of size 2 into arrays of size 4, and finally it merges the result into arrays of size 4 into the resulting array of size 8. We are now going to prove that the running time of the merge sort algorithm on a sequence containing n elements is big O of n log n. Note that this is significantly faster than a quadratic selection sort algorithm. For example, it is perfectly okay to sort a sequence of size 1 million, for example 10 to the 6, on your laptop using merge sort algorithm. While for the quadratic time selection sort algorithm, sorting a sequence of size 10 to the 6, 1 million, will take roughly 10 to the 12 operations, which is too much for modern computers. Okay, so to prove this lemma, to prove the upper bound on the running time of the merge sort algorithm, first note that to merge two parts of size n over 2 of our initial array takes the linear time, namely big O of n. Right, because, well, the left part has size n over 2, the right part has size n over 2, and for merging, we basically just scan both these parts from left to right. So it takes just a linear amount of work to do this. Which in turn means that if we denote by t of n the running time of our merge sort algorithm, then it satisfies the following recurrence. T of n is at most 2t of n over 2 plus big O of n. Here 2t of n over 2 corresponds to two recursive calls. Right, so we denoted by t of n the running time of our algorithm on input of size n. So when we sort two sequences of size n over 2, we spend time twice t of n over 2. So the big O of n term corresponds to what we do before we make recursive calls and what we do after recursive calls. So what we do before is just split the input array into two halves. What we do after is merging the results of two arrays into one array of size n. So all of this it is not difficult to see that all of this can be done in linear time. Right? So we get this recurrence, and on the next slide we're going to show that this recurrence implies that the running time of our algorithm is bounded from above by n log n. To estimate the running time of this algorithm, let's consider its recursion tree. Namely, at the top of this tree we have one array of size n. So for this array of size n we make two recursive calls for arrays of size n over 2. Each of these arrays of size n over 2 in turn is split into two arrays of size n over 4. So we get 4 arrays of size n over 4 and so on. So in this tree we have log n levels, right? Now let's estimate the work done at each of the levels of this tree separately. Namely, once again, to solve a problem of size n, to sort an array of size n, we first prepare to make recursive calls. In this case, we just split an input array into two halves of size n over 2. Then we do make recursive calls, and then we need to combine their results. So all the work done inside recursive calls will be accounted for on the lower levels of this tree. So now what we're going to do is to account for only the work done before the recursive calls and after the recursive calls at each separate level. And we know already that it takes linear time to do this. I mean, if we have an array of size n, it takes linear time to split it into two halves, and then it takes linear time to combine the results of recursive calls into one array. Okay, so let's just denote this time by Cn. I mean, let's denote the hidden constant inside big O by C. Then what we can say is that on the top level we spend time Cn. Then on the next level, for each subarray, we spend time C times n over 2, because the size of array is n over 2. However, we have two arrays, so the total work that we do at this level is 2 multiplied by C multiplied by n over 2, which is again just Cn. On the next level we spend time 4, because we have 4 arrays, multiplied by C multiplied by n over 4, because the size of the array is now n over 4. This is Cn again, and so on. So we have log n levels. At each level we do roughly Cn operations, so the total number of operations in our algorithm is Cn log n, which proves our lemma. So again, what we've just proved is that the running time of the merge sort algorithm is big O of n log n. So in the next video we will show that actually no algorithm, no comparison-based algorithms, to be completely formal, can sort a given sequence of n elements asymptotically faster than in n log n time, which actually means that the merge sort algorithm is asymptotically optimal. In the previous video, we proved that the running time of the merge sort algorithm on a sequence consisting of n elements is big O of n log n. In this video, we will show that this bound is essentially optimal. We will do this by showing that any correct sorting algorithm that sorts n objects by comparing pairs of them must make at least n log n operations asymptotically in the worst case. Once again, we say that a sorting algorithm is comparison-based if it sorts the given objects just by comparing pairs of them. We can imagine the following situation. We have n objects that look the same, for example n balls, but have different weights. And we also have pen balance. And this pen balance is our only way to compare pairs of these balls. And our goal is to rearrange these balls in order of increasing weights. So, for example, the two sorting algorithms that we already considered, namely the selection sort algorithm and the merge sort algorithm, are both comparison-based algorithms. So, for example, the selection sort algorithm at each iteration finds the minimum object, the minimum value in the remaining part of the array. And it does so exactly by comparing pairs of objects, right? Also, the merge sort algorithm is also comparison-based algorithm. So it first splits an array into two halves, and then it needs to merge the two resulting arrays. And when merging the resulting arrays, it also uses comparisons, right? So we take the first two elements of two sorted arrays, we compare them, and based on this comparison, we take one of these elements out of one of these two arrays and put it to the resulting array. So this is a formal statement that we are going to prove. It says that any comparison-based algorithm that sorts n objects has running time at least big omega of n log n in the worst case. So put it otherwise, we can say the following. Assume that you have an algorithm that sorts n objects by comparing pairs of them. It can be the case that for some input sequences of n objects, your algorithm performs less than n log n operations, say linear number of operations. However, it cannot be the case that your algorithm always sorts in time asymptotically less than n log n, meaning that there must exist sequence of objects on which your algorithm will perform at least big omega of n log n comparisons to sort such sequences. Any comparison-based algorithm can be shown as a huge tree that contains all possible sequences of comparisons that can be made by this algorithm. For example, here on the slide, we show a simple algorithm that sorts three objects. So it starts by comparing A1 and A2. If A1 happens to be smaller than A2, then we proceed to comparing A2 and A3. If A2 is smaller than A3, then we already know the permutation of the input 3 objects in non-decreasing order. Namely, we know that A1 is smaller than A2, and we know that A2 is smaller than A3. So we can just output the following permutation. Right? If, on the other hand, A2 happened to be at least A3, then at this point we only know that A2 is greater than A1 and A2 is no smaller than A3. So at this point we know that A2 is the maximal element among our 3 elements. However, we still need to compare A1 and A3. So we do this comparison, and based on its result we output either this permutation or this permutation. Well, this was the case when A1 happened to be smaller than A2. However, we need also to consider the case when A1 happened to be at least A2. So we proceed similarly in this case. So this is just a toy example for an algorithm, for a comparison-based algorithm comparing 3 objects, sorting 3 objects. However, such a huge tree can be drawn for any comparison-based algorithm. So at the top of this, at the root of this tree, we have the first comparison. At its children, we will label just the next comparison that is made based on the result of the first comparison, and so on. So each internal node is labeled with some comparison, and each leaf is labeled with a permutation of n input objects. A simple but crucial for this argument observation is that in this tree we must have at least n factorial leaves. And this is because we have n factorial different permutations of n input objects, where n factorial is defined to be the product of n, n-1, n-2, and so on. So, and why is that? Why we must have any possible permutation as a leaf in our tree? Well, this is just because it is possible that this permutation is a valid output, is the right output of our algorithm. So, for example, on our previous slide, on our toy example, we have 3 objects and there are 6 possible permutations of these 3 objects, and there are 6 leaves in our tree. For example, one of them is 2, 1, 3, and it says that the second element is the smallest one, then goes the first element, and then goes the third element. And indeed, there are cases when this is the right answer. Right? So when the input data consists of 3 objects, such as the second element is the smallest one, the first one is the next one, and the third element is the largest one. Right? So once again, in our huge tree, which corresponds to our comparison-based algorithm, there must be at least n factorial leaves, because each possible permutation must be present as a leaf in our tree. Okay, so on the other hand, the maximal number of comparisons made by our algorithm corresponds to the depth of our tree. So the depth is defined as the maximal number of edges on the way from the root to the leaf, to some leaf of our tree. So when this is exactly the maximal possible number of comparisons which our algorithm makes. So now we would like to show that D must be large in our case, must be at least big omega of n log n. And we know already that our tree contains many leaves. I mean, n factorial is a function that grows extremely fast. Okay, so intuitively we would like to show that if a tree has many leaves, then it has a large depth. And at least intuitively it is clear. If you have a tree of very small depth, then it must have just a few leaves, right? But we know that it has many leaves, at least n factorial leaves. To formally show this, we need the following estimate. The depth of a binary tree is at least the binary logarithm of its number of leaves, or equivalently 2 to the depth is at least its number of leaves. Well, this can be proved formally, but let me just show you this informally. Let's consider a tree, for example, of depth 1. So in this case, D is equal to 1, and it is clear that the maximal possible number of leaves in a tree of depth 1 is equal to 2. right? So now let's try to understand what is the maximal possible number of leaves in a tree of depth 2. For example, this is a tree of depth 2. This is another tree of depth 2. It has 3 leaves. And this is a tree of depth 2 that has maximal possible number of leaves. In this case, it is 4. It is 2 to the d indeed. And intuitively, it is clear that to have a tree of depth d that has maximal possible number of leaves, we need to take a tree which is a full binary tree of depth d, right? And this tree has exactly 2 to the d leaves. So the maximal number of leaves in a tree of depth d is 2 to the d, which proves that 2 to the d is at least L. Okay, so the last step that we need to show is that if we have n factorial leaves, then the depth of our tree is at least big omega of n log n. And we will show this on the next slide. It remains to estimate log of n factorial. We're going to show here that log of n factorial is at least c times n log n, which means, in other words, that log of n factorial is big omega of n log n. To do this, we express n factorial as a product of 1, 2, 3, and so on, n minus 1, and then write logarithm of product of these numbers as a sum of their logarithms. So log of n factorial is equal to log of 1 plus log of 2 plus log of 3 and so on plus log of n. So this is the sum of n objects. Let's just throw away the first half of these n elements and leave only the second half. So in this second half we have n over 2 elements, and each of them is at least log of n over 2, right? So these are logarithms of numbers which are at least n over 2. So we have n over 2 elements. Each of them is at least logarithm of n over 2. This allows us to conclude that the whole sum is at least n over 2 times log of n over 2. And this is in turn big omega of n log n for a simple reason. So log n over 2 is equal to log n minus 1. Well, this grows like log n, right? Because log n is a growing function and 1 is a constant. So log n minus 1 grows as log n. N over 2 grows as n, right? So this is up to a constant factor, this is just n. So n over 2 times log n over 2 grows like n log n. Okay, so this concludes our proof. And this concludes the proof of a fact that any comparison-based algorithm must make at least n log n operations in the worst case. Once again, another conclusion is that our merge sort algorithm that we considered in the previous lecture is asymptotically optimal. In the next video, we will see an algorithm that actually sorts n given objects in time less than n log n. Actually, in time, just in linear time, in time big O of n. However, it will sort the n given objects knowing something about these objects. It only sorts n given objects if these objects are small integers, and we will sort them without actually comparing them to each other. In this last video, we will show that there are cases when we can sort the n given objects without actually comparing them to each other. And for such algorithms, our lower bound n log n does not apply. Well, probably the most natural case when we can sort the n given objects without comparing them to each other is the case when our input sequence consists of small integers. We will illustrate it with a toy example. So consider an array of size 12, which consists of just 3 different digits. I mean, each element of our array is equal to either 1, 2, or 3. Then we can do the following. Let's just go through this array from left to right, I mean by a simple scan, and count the number of occurrences of 1, 2, and 3. Just by scanning this array, we find out that 1 appears 2 times, 2 appears 7 times, and 3 appears 3 times. And this information is enough for us to sort these objects. So we can use this information to fill in the resulting array A prime. So we put 1 2 times, then we put then we put 2 7 times, and then we put 3 3 times. And this gives us the resulting sorted array A prime, right? So what just happened is that we sorted this array, these n objects, without comparing these objects to each other. We just counted the number of occurrences of each number, and for this we used essentially the information that this array contains small integers. The algorithm that we just saw is called counting sort algorithm. Its main ideas are the following. Assume that we are given an array A of size n, and we know that all its elements are integers in the range from 1 to m. Then we do the following. We create an array count of size m, and by scanning the initial array A just once from left to right, we count the number of occurrences of each I from 1 to m, and we store this value in the cell count of I. So we scan the array A from left to right, and whenever we see an element equal to I, we increment the value stored in the cell count of I. Then, when this array is filled, we can use this information to fill in the resulting array A prime, as we did in our toy example. So this is the pseudocode of the counting sort algorithm. Here we are given an array A of size n, and we assume that all the elements of this array are integers from 1 to m. So we introduce the array count of size m, which is initially filled in by zeros. Then by scanning our initial array, we fill in this array. Namely, whenever we see an element k in our initial array, we increase the cell count of k. So after the first loop of this algorithm, we know exactly the total number of occurrences of each number k from 1 to m in our initial array. So, for example, in our toy example 2 slides before, we counted that the number 1 appears 2 times in our initial array, the number 2 appears 7 times in our initial array, and number 3 appears 3 times. So at this point, we know that in the resulting array, the first 2 elements will be occupied by the number 1, the next 7 elements will be occupied by the number 2, and the next 3 elements will be occupied by the number 3. Now we would like, instead of having just the lengths of these 3 intervals, we would like to compute the starting point of each interval. So we do this in a new loop, and for this we introduce a new array pos. So pos of 1 is equal to 1, meaning that the number 1 will occupy a range starting from the first index, and the starting point for each subsequent range is computed as a starting point of each previous range plus the length of this previous range, right? So pos of j is computed as pos of j minus 1 plus count of j minus 1. So at this point we know the starting point for each range. Namely, k in the resulting array, number k will occupy a range starting from pos k. Then we just scan our initial array, and whenever we see an element, we always know where to put it in the initial array. So let me remind you that we do not just fill in the array with numbers from 1 to m, but we copy elements from our initial array. This is because what we are looking for in the sorting problem is a permutation of our initial and given objects. Because what we have is probably not just integers from 1 to n, but these numbers are keys of some probably complex objects. Okay, so the running time of this algorithm can be easily seen to be big O of n plus m. This is just because here we have 3 loops. So the first loop has n iterations, the second loop has m iterations, and the last loop also has n iterations. Well, so this is the formal statement. The running time of counting sort algorithm is just n plus m. And the final remark about this algorithm is that if m grows no faster than n, namely, for example, if our array is filled by integers from 1 to n, or if this array is filled just by integers which are upper bounded by some constant, then the running time of our counting sort algorithm is just linear in n. We now summarize the last 3 videos. So we first covered the merge sort algorithm. So this is a divide and conquer based algorithm that proceeds as follows. Given an array of size n, it first splits it into 2 halves of roughly equal size, then it sorts them recursively, and then it merges them into the resulting array. We showed that the running time of this algorithm is big O of n log n, which is quite fast actually, almost linear. We then showed that no other comparison-based algorithm can sort n given objects asymptotically faster than n log n. So we did this by showing that any comparison-based algorithm must distinguish between too many cases, between n factorial possible permutations. For this, in the worst case, a comparison-based algorithm must perform at least big omega of n log n comparisons. We then showed that it can be actually done faster. I mean, sorting problem can be solved in time less than n log n in some cases. For example, in the case when our input array contains small valued integers. Hello and welcome to the next lesson in the divide and conquer model. This lesson is going to be devoted to the quicksort algorithm, which is one of the most efficient and commonly used in practice sorting algorithms. Well, as usual, we start with the overview of this algorithm. The algorithm is comparison-based, meaning that it sorts the n given elements by comparing pairs of them. Its running time is also asymptotically n log n, but not in the worst case, as was with the merge sort algorithm, for example, but on the average case. This is because this algorithm is randomized, so it uses random numbers to sort the given n objects. Well, we will explain later in this lesson what this means. Finally, as I said before, this algorithm is very efficient in practice, and at the same time not so difficult to implement. This is a toy example explaining the main idea of the quicksort algorithm. So given an array, in this case of size 11, let's take its first element. In this case it is 6. And let's do the following. Let's rearrange all the elements in this array such that the element 6 stays in its final position. All the elements that go before it are actually at most 6. And all the elements that go after 6, after this element, are greater than 6. Well, we will show that this can be done by a single scan of the initial array. This is how the resulting array looks like. So once again, 6 stays in its final position. All the elements before it are at most 6. All the elements after it are greater than 6. So we do not need to move 6 anymore. It is already in its final position. So what remains to be done is to sort all the elements that go before 6 and all the elements that go after 6. And this can be done just with 2 recursive calls to the same algorithm, to the quicksort algorithm. So we do this, and immediately after these 2 recursive calls, we have a sorted array. Well, in the next video, we will explain all the details of this algorithm. In this video, we provide the full pseudocode of the quicksort algorithm. So as you remember, the algorithm is recursive. For this reason, we pass to this procedure, to the quicksort procedure, the array A, and also 2 indices L and R in this array for left and right. And this procedure sorts the subarray inside R with indices from L to R. Well, we first check whether L is at least R. And if yes, then this means that the corresponding subarray contains at most 1 element. And this in turn means that nothing needs to be done, so we just return. Otherwise, we call the partition procedure with the same parameters. It returns an index M between L and R. So it rearranges all the elements inside this subarray with the following property. After the call to this procedure, A of M stays in its final position, meaning that all the elements to the left of an element A of M are at most A of M. And all the elements to the right are greater than A of M. Well, once again, after the call to the partition procedure, A of m stays in its final position. So what remains to be done is to sort all the elements that are at most A to the m, they stay to the left of A of m, and all the elements that stay to the right. So we do this just by making two recursive calls. So this is how the whole algorithm looks pictorially. Again, we are given an array A with two indices L and R, and we are going to sort a subarray inside R with indices from L to R. So we first call the partition procedure with parameters A, L, and R, and it gives us an index M between L and R with the following property. All the elements to the left of M are at most the element A of M. All the elements to the right are greater than A of M. Then we make two recursive calls to sort the left part with indices from L to M minus 1 and to sort the right part with indices from M plus 1 to R. And immediately after these two recursive calls, we have a sorted array. So before showing the actual pseudocode of the partition procedure, we explain its main ideas again on a toy example. So first of all, we will take the element A of L and denote it by X. This will be called our pivot element. So a pivot is exactly the element with respect to which we are going to partition our subarray. So X will be placed in its final position. So our goal now is to rearrange all the elements inside our current subarray so that X stay in its final position and all the elements to the left of X are at most X and all the elements to the right of X are greater than X. So we will do this gradually increasing the region of already discovered elements. So for this we will use a counter I, and we will maintain the following invariant. So I will go from L plus 1 to R, and at each point of time when we already read I elements, we will keep two regions inside this region from L plus 1 to I. In the first region from L plus Y to J, we will keep all elements that are at most X. In the second adjacent region with indices from J plus 1 to I, we will have all elements that are greater than X. Okay, let's see a toy example. So I assume that we are somewhere in the middle of this process. In this case, X is equal to 6, and we need to partition all the elements with respect to X. We already have two subregions. So in the red region, we keep all elements that are at most X, that are at most 6. In the blue region, we have all the elements that are greater than 6. Okay, now we move I to the next position, and we discover the element 9. So this element is greater than 6, so we just need to extend the second region, the blue region, the region of elements that are greater than 6, right? So in this case, we just do nothing. Well, the next case is more interesting. We move I to the next position, and we discover the element 4, and in this case we need to somehow move this element to the red region, to the region of elements which are at most 6, right? So to do this, we just swap it to the currently first element of the blue region, in this case with 9, right? So if we do this, 4 will be the last element of currently red region, and 9 will go to the blue region. So we do this, and now we increase also the value of G just to reflect the fact that our red region has just been extended, right? Then we move I to the next element, so we discover element 7, which is greater than 6, which means that we can just extend the blue region. Then we discover another element, which is 6. 6 is at most 6, and this is actually equal to 6, so we need to move it to the red region. Again, we swap it with the first element of the blue region, and then we extend the red region. I mean, we increase G to reflect the fact that the red region has just been extended. Then we discover another element which is at most 6. We move it to the end of the red region. And finally, what we also need to do in the very end is to move the pivot element, which is 6 in this case, to its final position. And its final position actually can be easily found in this case. So we have red region and we have blue region. In red region, all the elements are at most 6, and in blue region, all the elements are greater than 6. So we can just swap 6 with the last element of the red region, right? In this case, it is 1. So if we swap these two elements, then you can see that all the elements in the blue region are indeed greater than 6. All the elements in the red region are smaller than 6. So we are done with this partition procedure. We are now ready to present the pseudocode of the partition procedure. Recall that what we're going to do is to place some element x, which is called the pivot, into its final place so that all the elements before x are at most x and all the elements after x is greater than x. So as the pivot element in this procedure, we are going to use just the first element of the corresponding subarray. So x is assigned A of L. We are also going to maintain the following two subregions. So first of all, we will gradually increase the region of discovered elements. So I goes from L+1 to R, and inside this region of already discovered elements, we will maintain two subregions. In the first region, with indices from L+1 to J, we will keep all the elements that are at most x. In the second region, with indices from J+1 to I, we will keep all the elements that are greater than x. And we will gradually increase the value of I. So when I is increased, so assume that I has just been increased. So we discovered a new element A of I. So if A of I is greater than x, then just the second region of elements that are greater than x is extended automatically, and we do not need to do anything in this case. However, if the newly discovered element is at most x, then we need to move it to the first region, right? So we do this as follows. So we just increase the value of j to indicate the fact that, well, the first region has just been increased, and then swap the elements aj and ai, okay? So this way we just maintain our invariant each time when I is increased. So in the very end, when I reaches the value of R, we also need to place our initial element that stays at the beginning, our pivot, between our two regions. So for this we just swap elements A of L, so this is our pivot, with element A of J. And we then return the value j as an index of our pivot element. Now, when the algorithm is presented, we need to estimate the running time. For the quicksort algorithm, the running time analysis is a little bit tricky. So before stating and proving the theorem about its running time, let's build our intuition. First of all, let's consider a pathological case when somehow it always happens that we select the minimum value of our current subarray as our pivot element. Well, in this case, well, let's see what happens. We have a current subarray, say of size n, and we select its minimum value and as a pivot and partition the subarray with respect to this element. Since this is the minimum value, its final position is just the first position in the resulting array, right? Which means that we partition into two parts. The first part is just empty. We have no elements smaller than our pivot. And the second part contains n-1 elements, because all the remaining elements are greater than our current element. Okay, so in this case, and if this happens at each iteration, I mean at each call to partition procedure, then we can write that the running time of our quicksort algorithm satisfies the following relation. T of n is equal to n plus t of n minus 1. The term n here corresponds to the running time of the partition procedure. Well, it is actually big O of n, but just to simplify, let's put n here. Well, let me also recall you that, well, if we have an array of size n, then the partition procedure indeed works in time big O of n, because it just scans the subarray, right? So now let's see what is the solution for this recurrence relation. Well, we can just unwind this recurrence relation term by term. So we have n plus t of n minus 1. Let's replace t of n minus 1 by n minus 1 plus t of n minus 2. Then we replace t of n minus 2 by n minus 2 plus t of n minus 3. And we keep doing so. So what is left is the following sum: n plus n minus 1 plus n minus 2 and so on. So when we know this sum already, so this is an arithmetic series, and we know that it grows quadratically, which gives us something strange. I mean, our quick sort algorithm works in quadratic time, which means that it is not quick actually, right? Well, we will resolve this issue later. Now let's consider a slightly different case. Assume that somehow we always partition into two parts such that one of them has size, for example, n minus 5, and the other one has the size 4. Well, I claim that even in this case, first of all, note that both these cases correspond to very unbalanced partitions. In the first case, we have two parts, one of size 0 and one of size n minus 1. In the second case, we have two parts, one of size 5 and one of size 4 and one of size n minus 5. So the sizes of parts are very unbalanced. They are very different. Okay, so I claim that in this case, the running time is also going to be quadratic. And this can also be shown just by unwinding this recurrence relation. So let's just throw away this t of 4 and leave only t of n minus 5. And okay, so t of n is equal to n plus t of n minus 5. Let's replace t of n minus 5 with n minus 5 plus t of n minus 10. Let's then replace t of n minus 10 with n minus 10 plus t of n minus 15 and so on. So this leaves us with the following sum: n plus n minus 5 plus n minus 10 and so on. And this is also an arithmetic progression. The only difference with the previous arithmetic progression is that now we have step 5. The difference between neighbors is 5 but not 1. Well, still this arithmetic progression has a linear number of terms, which means that its sum grows quadratically, with the only difference that the hidden constant inside this theta is smaller than in the previous case. Now let's consider another pathological case. Assume that it somehow so happens, for some unknown reasons, that at each iteration, at each call to the partition procedure, it partitions the array into roughly equal sizes. Well, in this case, we can write the following recurrence relation on the running time of our algorithm. T of n is equal to t of n over 2 plus a linear term. And we know this recurrence already. It is exactly the recurrence that the running time of the merge sort algorithm satisfies, right? And we proved that in this case, t of n grows as n log n asymptotically. And let me remind you how we proved this. We analyzed the recursion tree of our algorithm. So in this tree, at the root, we have one array of size n. At the next level, we have two arrays of size n over 2. At the next level, we have 4 arrays of size n over 4, and so on. So the height of this tree is log base 2. Well, it is basically logarithmic. And at each level, the sum of the sizes of all arrays is equal to n. So we have one array of size n at the top, two arrays of size n over 2 at the next level, the sum is n. The 4 arrays of size n over 4 at the next level, the size is still n, and so on. And at each level, we spend a linear amount of work. And this is essential. So we spend a linear amount of work at each level, and we have a logarithmic number of levels, which means that we spend an n log n time in total. Okay, now let's consider another, again, very pathological case. Assume that we always split an array of size n into two parts, one of size n over 2, n over 10, one of size 9n over 10. So in this case, the recurrence is the following. T of n is equal to T of n over 10 plus T of 9n over 10 plus a linear term. I claim that even in this case, we can prove an upper bound n log n on the running time of our algorithm. And this is how we can do this. Well, let's again consider the recursion tree of our algorithm. In this case, it is not balanced, right? Because when we go to the left branch, we reduce the size of the current subproblem by 10, and when we go to the right branch, we reduce the size of the current subproblem only by a factor of 10 divided by 9. Which means that in our tree, well, the size of the left branch is, of the leftmost branch is actually log base 10 of n, while the size of the rightmost branch is log base 10 over 9 over n. Well, still the height of this tree is logarithmic. The only difference with the previous case is that now the base of the logarithm is different, but it's still constant. It is log base 10 over 9 of n. And also, but the previous property is true. I mean, the sum of the sizes of all arrays at each level is still equal to n. It is at most n, actually. At the root, we have one array of size n. At the next level, we have two arrays, one of size n over 10, and the other one is of size 9n over 10. Right? So the size is still n. At the next level, it is the same, and so on. So we have a logarithmic number of levels, and at each level, we spend a linear amount of work, which gives us an n log n upper bound once again. Okay, all this analysis was about only pathological cases. If we always split in a balanced way or in an unbalanced way. In reality, or just when we run a quicksort algorithm on some array, well, some of the partitions are going to be balanced, some of the partitions are going to be unbalanced. So we still do not know what is the actual running time of the quicksort algorithm. We still need to determine this. However, we already get an important message. So the running time of our algorithm, of the quicksort algorithm, depends on how balanced our partitions, right? What we know now is the following. If all our partitions are balanced, then we can prove that the running time is at most n log n, asymptotically. At the same time, if all our partitions are unbalanced, then the running time is quadratic. This means that we would like to have a way of selecting a pivot element such that it always guarantees a balanced partition. At the same time, it is not clear at all how to do this, how to guarantee that we can always pick quickly the pivot element so that with respect to this pivot, the array is partitioned in a balanced way. So instead of this, we will use the following elegant solution. So let's just select the pivot element from the current subarray randomly. To implement this solution, we do the following. Before calling the partition procedure, we just select a random index between L and M, and we swap elements A of L and this random element. Okay, then we call partition, and then we proceed in a usual way. Let me explain intuitively why selecting a random partition is going to help us to prove a good upper bound on the running time of the quicksort algorithm. Well, for this, consider our array A that we are going to partition with respect to random pivot, and consider its sorted version. Assume for the moment that all the elements inside our array are different. In the sorted version, consider the middle half elements. Well, we consider n over 2 elements that stay exactly in the middle. Well, an important property of all these elements is the following. For each of these n over 2 elements, there are at least n over 4 elements that are greater than them, and at least n over 4 elements that are smaller. Well, this means that if we select any of these elements inside our array A, then the partition with respect to this element is going to be balanced. Right? In both parts, there will be at least n over 4 elements. Well, these n over 2 elements stay somewhere in the initial array. So they stay in the middle in the sorted array, and they stay somewhere in the initial array. It doesn't matter for us. What is important for us is that there are at least n over 2 elements with respect to which the partition is going to be balanced, which means that with probability 1/2, we will have a balanced partition. And this happens to be enough to prove a good upper bound. So we are going to show that the randomized quicksort algorithm is actually very fast. Well, first of all, it is fast in practice, and also we will prove a theoretical n log n asymptotically upper bound on its running time. This is the formal statement of an upper bound on the running time of the quicksort algorithm that we are going to prove in the next video. So assume that we're given array A, and assume for the moment that all the elements of this array are pairwise different. Then the average running time of the quicksort algorithm on this array consisting of n elements is big O of n log n, while the worst case running time of this algorithm is n squared. Well, let me explain the word on average here. Well, this means that for any fixed array, so if we are very unlucky with the random bits, the running time potentially could be higher than n log n. However, on average, and averaging is over all possible random bits, the running time of the quicksort algorithm is n log n. And this is true for any input. So this theorem doesn't say us that, well, for quicksort algorithm, for some arrays the running time is large, for some arrays the running time is low, but on average the running time is good enough. So it says that for any fixed array, the average running time is n log n. Okay, so we are going to prove this theorem in the next video. In this video, we are going to prove formally an upper bound on the running time of the randomized quicksort algorithm. Namely, we're going to prove that the running time on average of the randomized quicksort algorithm is n log n asymptotically. That is, it is at most big O of n log n. And that in the worst case, the running time is big O of n squared. Well, before going into the details of the proof, let's again build our intuition. First of all, let's know that what we need to estimate is the number of comparisons. Why is that? Well, because the quicksort algorithm contains of first the call to the partition procedure and then two recursive calls. Each of these two recursive calls is going to be unwinded into the call to partition procedure and another two small recursive calls. So what is going on inside the quicksort algorithm is essentially many calls to the partition procedure. While inside the partition procedure, what we do actually is to compare all the elements of the current subarray with the pivot element. Right? So what we need to estimate is the total number of comparisons, which is not surprising because the quicksort algorithm is a comparison-based algorithm. Right? Well, now let me also explain why balanced partitions are better for us. I will explain this intuitively. So consider this toy example, this array of size 7. Assume that we selected 1 as the pivot element. So we partitioned the array as shown here on the left. Now let's see what we now know. We compared all the elements in this array to the pivot element, which is 1 in this case. So now we know that that the final position of the pivot element is just the first position in the array. So we know that 1 is the minimum value. However, we know nothing about pairs of other elements, right? So we only learned that 1 is the minimum value. Now consider another possibility. Consider the following balanced partition shown on the right. So assume that we selected 4 as the pivot element. I claim that in this case, this partition is much better for us because we saved many subsequent comparisons. So look, in this case, in the subsequent runs of the partition procedure, we are not going to compare elements 3, 1, 2 with elements 6, 5, 7. Because we already know that all the elements to the left of 4 are smaller than all the elements to the right of 4, right? And also, the left part will stay in a separate recursive call and the right part will stay in a separate recursive call. So once again, balanced partitions save us a lot of comparisons that we do not need to make in the subsequent calls to partition procedure. Another thing I would like to discuss with you before going into the details of the proof is the following. Our algorithm is randomized. So its running time and its number of comparisons depends on the random bits used inside the algorithm. In particular, for any two elements, there is some probability that they are going to be compared. And using this toy example shown on the slide, I would like to just to build an intuition on how to estimate this probability, or on which factors this probability depends. So consider this small example. So this is an array of size 9 containing all the digits, and I would like to estimate the probability that elements 1 and 9 are going to be compared if we call randomized quicksort for this array. So let's see what happens. Assume that in the very first call to the partition procedure we select the element 3, for example, as the pivot element. So what happens? In this case, 1 will go to the left of 3 and 9 will go to the right sub 3. To the right of 3, I'm sorry. So in this case, 1 and 9 will be in different parts, and they will never be compared in further calls to the partition procedure, just because they are already in different parts. Okay, put it otherwise, it means that we already know that 1 is smaller than 9, because 1 is smaller than 3, and 3 is smaller than 9. Right? We do not need to compare them. Well, and this happens if we select as our pivot element any of the elements 2, 3, 4, 5, 6, 7, or 9, or 8, I'm sorry. If, on the other hand, we select 1 or 9 as our first pivot element, then 1 and 9 will be compared. Just because, well, if we select, for example, 9 as the pivot element, we compare it with all the elements of our array, in particular with 1. So there are two cases when 1 and 9 are compared. And these are exactly the cases when either 1 or 9 are selected as a first pivot. In all other 7 cases, they are not compared. This means that the probability that they are compared are 2 over 9. Okay, makes sense? Now let's try to estimate the probability that the elements 3 and 4 are compared. Well, I claim that in this case, this probability is equal to 1. And the explanation is the following. There is no element inside our array that can help the randomized quicksort algorithm to understand that 3 is smaller than 4 without comparing them. I mean, for 1 and 9, there are 7 such elements, all the other elements. I mean, if we partition with respect to any other elements, we already know that 1 is smaller than 9 because they go to other parts, to different parts with respect to this pivot. For 3 and 4, there is no such element. So algorithm just must compare these two elements to be sure that 3 is smaller than 4. So in this case, the probability is 1. Well, this shows that the probability of comparing two elements depends on how close they are in the sorted array. In particular, if they are very far apart of each other, then the probability is small. And if they are close to each other, then the probability is high. We will use this observation in the formal proof of our statement. We now start to formally prove an upper bound on the running time of the randomized quicksort algorithm. For this, we introduce the following random variable. Let I and j be different indices from 1 to n. We define xi of ij to be equal to 1 if two elements a prime of I and a prime of j are compared in the run of our quicksort algorithm, and to be equal to 0 otherwise. Once again, to estimate the running time of the quicksort algorithm, we would like to estimate the total number of comparisons made. So we would like to estimate for any pair of elements what is the probability that they are compared. As we discussed on the previous slide, the probability that two elements are compared depends on how close they are in the sorted version of our array. For this reason, we define xi of ij depending on the sorted array. We do not have this sorted array, right? We are only constructing this in the quicksort algorithm, but we use it just for the analysis. Okay? The next thing to note is the following. For any two elements of our initial array or sorted array, it doesn't matter. So for any two elements, they are either compared just once or they are not compared at all. So why is that? Why is just once? Well, if two elements are compared at some point, this means that at this point, one of these elements is the pivot element. Because in the partition procedure, we compare pivot with all other elements of the current subarray. So if two elements are compared, that one of them is the pivot. This also means that right after the call of this partition procedure, we are not going to use this pivot element. We will put the pivot element into its final place, and we are not going to touch it in any of the subsequent calls. This immediately implies the upper bound, the quadratic upper bound on the worst case running time of our algorithm. Once again, we have quadratic number of possible pairs of elements. And each pair of elements is either compared once or not compared at all. Right? So the running time in the worst case is quadratic. Now comes the most important observation of this proof. I claim that the elements A' of I and A' of j are compared if and only if the first pivot selected in the sub-range of the sorted array A' from index I to index j is either A' of I or A' of j. Well, let's see why. First of all, when we select a pivot, a random pivot, which is not in this sub-range, then all the elements from this sub-range in the sorted element go either to the left of this pivot or to the right. So they all stay together in the same branch of the recursion tree. Okay? So before we select a pivot which stays inside this range, all these elements stay together in the same subarray. Now, assume that we selected a pivot from this subrange, and assume that it is not A' of A or A' of j, for example. In this case, A' of A and A' of j will be split apart. They will go into different parts with respect to this pivot, right? At this point, I'm assuming that all the elements in my subarray are different, and in the wall array are different. Okay? So once again, if the first selected element from this subrange is not A' of A or A' of j, then these two elements are not going to be compared, because right after the partition procedure uses this pivot from this range, A' of A and A' of j will go to different parts, right? If, on the other hand, the first selected pivot from this subrange is either A' of A or A' of j, then these two elements are going to be compared, right? So this is the most important observation in this proof. Everything else is just calculation. So if this is clear, let's then estimate the probability that the corresponding two elements are compared. So we know that they are compared if and only if the first selected pivot in this subrange is one of these two elements. This helps us to estimate the probability of the fact that Xi of ij is equal to 1. Well, this is equal to 2, because we have only two choices, either A' of A or A' of j, divided by the total number of choices, the total number of elements in this subrange. And this is j minus I plus 1. So the probability that Xi of ij is equal to 1 equals 2 divided by g minus I plus 1. For example, if j and I differ by 1, so j is equal to y plus 1, so these are neighboring elements in the sorted array, then this probability is equal to 2 divided by 1 plus 1. This is 2 by 2, this is 1. So when this reflects the fact that if there are two neighboring elements inside the sorted array, then the algorithm just must compare them to understand that one of them is smaller. There is no other element that can help our algorithm to realize that one of these elements is smaller than the other one. Okay? This in turn helps us to estimate the expected value of this random variable. So recall that if we have a random variable which takes only values 0 and 1, then its expected value is 1 multiplied by the probability that it takes value 1 plus 0 multiplied by the probability that it takes the value 0. Well, 0 multiplied by something is 0, so what is left is just probability that it takes value 1 multiplied by 1. So the expected value of Xi ij is equal to 2 divided by g minus I plus 1. The final step in our proof is estimating the sum of all the random variables Xi ij for all possible I and j. So once again, the expected value or the average value of the sum of the number of comparisons made is the expected value of the sum of all possible xij's, I mean for all ij's. So the expected value of the sum is the sum of the expected values. So we can write the following, that the average running time is equal to the sum over all possible different ij of the expected values of Cij, and we know this expected value already. So this is the sum over all possible different ij, I mean where j is greater than I, of 2 divided by g minus I plus 1. Well, we can take this constant 2 out and consider all possible and consider a fixed I. For this I, what we have j ranges from I plus 1 to n. So what we have for this specified I in this sum is a subset of the following sum, 1 over 2 plus 1 over 3 plus 1 over 4 and so on. And this is actually a known sum. This is called harmonic series, and it is known that it grows logarithmically. Once again, 1 over 2 plus 1 over 3 plus and so on 1 over n is set of logarithm of n. Well, this means that for each fixed I, this grows, well, the corresponding sum, which ranges over all j from I plus 1 to n, grows at most logarithmically. This means, since we have n choices for I from 1 to n, that the whole sum grows asymptotically as n log n. Okay, and this concludes our proof. In this video, we address the issue of equal elements in the input array. So recall that we proved the upper bound on the running time of the randomized quicksort algorithm in the assumption that all the elements inside the given array, are pairwise different. And actually we used essentially this assumption. So recall that we estimated the probability that two elements A prime of I and A prime of j are compared. And we argued that if any element between them is selected as the pivot, that they will not be compared. However, if they are equal, so if A prime of A is equal to A prime of j, this means actually that all the elements in this range are equal. So if we select any element inside this range, in the middle of this range, as the pivot, then it is not true that these two elements will go into different parts with respect to this element. This is just because all the elements inside this range are equal, which means that if we partition with respect to this element, all the elements in this range will be at most this element, so they all will be in the left part with respect to this element. Okay? So our analysis doesn't work for equal elements, but let's see what happens in real life. What happens if we run the quicksort algorithm for the array in which there are equal elements. For this, let's use the following online visualization. This visualization shows how different sorting algorithms perform on different data sets. So there are 8 sorting algorithms here where we are now interested in this quicksort algorithm, and there are 4 different types of data sets. So the first data set is just random sequence. The next one is a nearly sorted sequence. The next one is a reversed sequence, and the next one, which is most interesting to us at the moment, is a sequence that contains a few unique elements. So let's see how the quicksort algorithm performs on the last data set. So for this, let's just run all the algorithms on all data sets. So let's see what happens here. So you may notice now that, for example, merge sort have already sorted everything, and while quicksort have just finished to sort the last data set. So quicksort is not so fast on data sets that contain few unique elements. And this is why. So just consider a data set that consists of elements that are all equal to each other. So all elements are equal to x. This means that the partition procedure always partition partitions the array with respect to the element x, right? And in this case, one of the parts, namely the part of the elements that are greater than x, is just empty, it has size 0, and the other part has size n-1. So the recurrence inequality, the recurrence equality on the running time of our algorithm on such a data set always satisfies the following relation. T of n is equal to T of n-1 plus a linear term plus T of 0. And we know already, so this is an unbalanced partition. We know that this corresponds to the quadratic running time. So, which means that the running time of the quick sort algorithm on a very simple array, so it contains all the elements of this array are equal, which means that actually this array is already sorted. And on this array, our quick sort algorithm spends a quadratic time to sort it. To overcome this difficulty, we do the following. Instead of partitioning our array into two regions, namely the region that contains all elements that are at most x and region that contains all elements that are greater than x, we are going to partition into three parts. The corresponding partition procedure is usually called three-way partition. Formally, it returns two indices, m1 and m2, such that all the elements inside the region from m1 to m2 are equal to x. All the elements to the left of this region are smaller than x. All the elements that are to the right of this region are greater than x. Okay, so this is how it looks pictorially. We have three regions. So from L1 to M1 minus, from L to M1 minus 1, we have all elements that are smaller than x. In the region from M1 to M2, we have all elements that are equal to x. In the region from M2 plus 1 to R, we have all elements that are greater than x. This procedure actually can be implemented in a similar way to the original partition procedure. It can be implemented either with a single scan of the array with maintaining three regions, or it can be implemented with two scans. So we first split our array into regions which contain elements at most x and greater than x, and then we split the first region into two parts. Well, this is how the modified randomized quicksort algorithm is going to look like. So we just replaced the call to partition procedure by a call to partition 3 procedure. Now we have three regions, and actually the middle region is already in its final place, so we do not touch it after the partition procedure. We make two recursive calls to the first region and to the last region. So let's see whether the resulting algorithm is indeed quick. And for this, let's use the same visualization. The resulting algorithm is shown here in the last column. Let's once again run all the algorithms and see what happens in the last column. Well, we see that now the resulting quick sort algorithm is indeed quick. In this last video of the quick sort lesson, I would like to address two implementation issues. So the first issue is about space complexity of the quicksort algorithm. So on one hand, when sorting an array by a quicksort algorithm, we do not use any additional space. We just partition the array and we swap elements inside the array. On the other hand, the quicksort algorithm is a recursive algorithm. And when we make a recursive call, we store some information on the stack, right? So on one hand, it is possible to show that the average recursion depth is logarithmic, meaning that we need only a logarithmic additional space. On the other hand, there is a very nice and elegant trick that allows to re-implement the quicksort algorithm such that its worst case space complexity is at most logarithmic. So for this, let's recall that the quicksort algorithm contains of the call to the partition procedure and then of two recursive calls, right? So the situation when we have a recursive call in the end of the procedure is called tail recursion. And there is a known way to eliminate such a recursive call. Namely, instead of making this recursive call, let's just update well, in the second recursive call, we sort the right part of our array. I mean, the part from index m+1 to index r. Instead of making this recursive call, let's replace the whole body just with a while loop. Then we make, inside this while loop, we call the partition procedure as shown on the slide. Then we make a recursive call to the left part, but instead of making the recursive call for the right part, we just update the value of L to be equal to m+1. So this just makes and then we go to the beginning of this while loop, and this essentially mimics our recursive call. So far, so good. We've just realized that we can eliminate the last recursive call. At the same time, let's also realize the following thing. In our quicksort algorithm, we first call the partition procedure, and then we make two recursive calls. And these two recursive calls are in a sense independent. Well, it doesn't matter which comes first, right? So they do not depend on each other. This means that we can as well eliminate a recursive call to the first part. Well, and this in turn means that we can always select which one to eliminate. And for us, it is better to remove a recursive call to a longer part. And this is why. If we always make a recursive call to an array which is shorter, then we make a recursive call to an array which is at least twice shorter than the initial array, right? And this in turn means that the depth of our recursion will be at most logarithmic, because, well, the first recursive call is made for an array of size at most n/2, then at most n/4, and so on. So the depth is logarithmic, which is good. And this can be implemented as follows. So we first call the partition procedure. It gives us the value. It gives us the value of m. At this point, we know the lengths of two parts, and we just compare them. If, for example, the length of the first part is shorter, then we make a recursive call to this part, and instead of making the recursive call for the second part, we just update the value of L. In the other case, when the right part is shorter, we make the recursive call for this part, and instead of making the recursive call for this part, we just update the value of R, right? So overall, this gives us an implementation of the quicksort algorithm, which uses, in the worst case, an additional logarithmic space. So the next implementation issue concerns the random bits used by our algorithm. So assume that we would like to have a deterministic version of our randomized quicksort. And this is a reasonable thing to want, because in practice we would like to have such a thing as reproducibility, which is, for example, essential for debugging. So we would like our program to always output the same on the same data set. And this is why we probably would not like to use random numbers. Okay? Then we can do the following. The following algorithm is known as intrasort and is used in many practical implementation of quicksort. So instead of selecting the pivot element randomly, let's select it as follows, using, for example, the following simple heuristic. Each time when we are given a subarray and we need to partition it with respect to some pivot, so for this we need to select pivot, and let's select it as follows. We take the first element of this subarray, the last element, and the middle element, for example. Then we have three elements and we sort them. We just compare them and we select the minimum or the medium value of this. And we use this element as our pivot element. So this is a very simple heuristic, right? It can be implemented very efficiently. We just need like 3 comparisons to select this median. And in many cases, this is enough for the quicksort algorithm to work efficiently. However, this is not what we want, right? We are not happy with the statement that this algorithm works well in many cases. We would like our algorithm to work well just on every possible input. Unfortunately, there are pathological cases in which this heuristics works badly. But we can overcome this in the following way. Let's, while running our quicksort algorithm, let's count what is the current depth of our recursion tree. And at some point, when it exceeds some value c log n for some constant c, then we just stop the current algorithm and switch to some other algorithm. For example, for the heap sort algorithm. This is another efficient algorithm, which is asymptotically as good as quicksort and merge sort. I mean, it has asymptotic running time n log n. However, quicksort is usually faster in practice. So at this point, we switch to the quicksort algorithm, which means that for these pathological bad instances, for the quicksort with this simple heuristic of selecting the pivot element, we still work in the worst case in time n log n. Because before we exceeded the depth c log n, we spent time n log n. And after this, we stop this algorithm immediately and we run the heap sort algorithm. So overall, we spend time n log n. So this gives us an algorithm which in many cases performs like the quicksort algorithm, and in any case, just in the worst case, its running time is bounded above by n log n. So to conclude, the quicksort algorithm is a comparison-based algorithm whose running time is big O of n log n in the average case and big O of n squared in the worst case. What is important in this algorithm is that it is very efficient in practice. It is more efficient than the merge sort algorithm, for example. For this reason, it is commonly used in practice, and for this reason, it is called quicksort.
Before recording this lecture, I stopped by in a coffee shop. This cappuccino is good. And as soon as I gave $5 to the cashier, she faced an algorithmic problem with which coins to select to give me the change. And cashiers all over the world use an algorithmic approach called greedy algorithms to solve this problem. Today, we will learn how cashiers and computer scientists use greedy algorithms for solving many practical problems. So the change problem is finding the minimum number of coins needed to make change. More formally, input for the problem is an integer money and positive integers coin 1, coin 2, coin d that represents coin denominations. For example, in the US, coin 1 will be 1 cent, coin 2 will be 5 cents, 10 cents, 25 cents, and 50 cents. And the output is the minimum number of coins with its denominations coin 1, coin 2, coin d that changes money exactly. So today in the morning, when cashier had to return me 40 cents, she most likely used the following algorithm. First, finding the largest coin denomination that is smaller than 40 cents. It will be 25 cents. So she gave me 25, 15 cents left, and then the next challenge is how to change 15 cents. The next step is she probably found the largest coin smaller than 15 cents. It is 10 cents. She gave me 10 cents, and finally she returned 5 cents. As a result, she changed 40 cents as 25 plus 10 plus 5. Do you think it's the minimum number of coins she could possibly return? It is the minimum number of coins in the United States. But if you travel to Tanzania, it won't be the minimum number of coins because there is a 20 cents coin in Tanzania. And therefore, this greedy approach to solving the change problem will fail in Tanzania because there is a better way to change 40 cents, simply as 20 cents plus 20 cents, using Tanzanian 20 cents coin. Since the greedy approach to solving the change problem failed, let's try something different. Let's try the recursive algorithm for solving the same problem. Suppose we want to change 9 cents and our denominations are 1 cent, 5 cents, and 6 cents. What would be the optimal way to change 9 cents? Well, if we only knew what are the optimal ways to change 9 minus 6 cents, 9 minus 5 cents, and 9 minus 1 cent, then we would know what is the optimal way to change 9 cents. Or in other words, To change 9 cents, we need to know how to change smaller number of cents, in our case 3 cents, 4 cents, and 8 cents. And therefore, an approach to solving this problem would be to use this recurrence to write the recursive program. This idea is implemented in the program recursive change. To change money cents using coins coin 1, coin 2, coin D, we do the following. We first recursively call recursive change with the amount of money minus coin 1, money minus coin 2, and money minus coin D, and find the minimum amount of money for these D choices. We add plus 1 because there is one more coin to add, and return this value. This looks like the right approach to solve the problem, but let's check how fast the resulting program is. So when we're changing 76 coins, there are actually 3 choices. We need to recursively call recursive change for 70 cents, 71 cents, and 75 cents. But for each of these values, we need once again to call 3 choices. And we will continue growing this tree, and very quickly it will turn into a gigantic tree. Let's check how many times we have already tried to change 70 cents. 3 times, and we only started expanding this tree. In fact, if we continue further, we will see that there were 6 times when we needed to compute recursive change for 70. How many times do you think we will need to run recursive calls when we compute the minimum number of coins for 30 cents? It turns out that we will need to call it trillions of times, which means that our seemingly very elegant recursive change program will not finish before the end of your lifetime. So as simple as the change problem looks like, neither greedy approach nor the recursive approach solve it in a reasonable time. 60 years ago, a brilliant mathematician, Richard Bellman, had a different idea. Wouldn't it be nice to know all the answers for changing money minus coin I by the time we need to compute an optimal way of changing money? And instead of the time-consuming calls to recursive change money minus coin I that may require to be repeated trillions of times, we would simply look up these values. This idea resulted in dynamic programming approach that is applied in thousands of diverse practical applications in a myriad of different fields. And the key idea of dynamic programming is to start filling this matrix not from the right to the left, as we did before in the recursive change, but instead from the left to the right. So we will first ask the trivial question, what is the minimum number of coins needed to change 0 cents? And of course it is 0. What is the minimum number of coins to change 1 cent? Obviously it is 1, but we can compute this number by finding what is the minimum number of coins to change 0 cents and adding 1 coin. We will proceed in a similar fashion to compute the minimum number of coins to change 2 cents, 3 cents, and 4 cents. There is only one possibility to derive this number from the previous number, and for 5 cents, actually there are 2 possibilities, green and blue. For green one, you can derive it from 0 cents by adding 5 coin, and for blue possibility, we can derive it from 4 cents by adding 1 penny. Which possibility would you select? Of course, the one that gives you the minimum change for 5 coins. We can continue further and applying it to 6 cents. There are now 3 possibilities. And once again, we select the optimal choice that corresponds to minimum number of coins. Let's say it may be 0 coins plus 6 cents. we continue for 7 cents, continue for 8 cents, and finally, very quickly, we actually found the correct answer for 9 cents. We need 4 coins to change 9 cents. And it results in DP change algorithm that simply fills up the table that I just showed you from left to right. DP change is the first dynamic programming algorithm that you saw in this course, and there will be thousands more. You may be wondering why this algorithm called dynamic programming and what it has to do with programming. Well, in fact, programming in dynamic programming has nothing to do with programming. Amazingly enough, dynamic programming is one of the most practical algorithms computer scientists use. But when Richard Berman was developing this idea for Air Force project he was working on, it looked completely impractical. And he wanted to hide that he is really doing mathematics from the Secretary of Defense rather than working on Air Force project. Therefore, he invented a name that basically has nothing to do with what dynamic programming algorithms do. In his own word, he said, "What name could I choose? I was interested in planning, but planning is not a good word for various reasons. I decided, therefore, to use the word programming, and I wanted to get across the idea that this was dynamic. It was something not even a congressman could object to." Cystic fibrosis is one of the most common genetic diseases in humans. Approximately 1 in 25 people carries a cystic fibrosis gene. And when both parents carry a faulty gene, there is a 25% chance that their child will have cystic fibrosis. In the early 1980s, biologists started a hunt for cystic fibrosis genes, one of the first gene hunting projects in the framework of the Human Genome Project. 30 years ago, biologists narrowed the search for the cystic fibrosis gene to a million nucleotide long region on chromosome 7. However, this region contained many genes, and it was not clear which of them is responsible for cystic fibrosis. How would you find which of these genes is the cause of cystic fibrosis? I'll give you a hint. Cystic fibrosis involves sweet secretion with abnormally high sodium level. Well, this is a biological hint that does not help us to solve the challenge of finding something in this 1 million nucleotide area that is responsible for cystic fibrosis. Let me give you hint number 2. By that time, when cystic fibrosis hunt was on, biologists already knew the sequences of some genes responsible for secretions. For example, ATP-binding proteins act as transport channels responsible for secretion. You still may be wondering how these 2 hints may help you to find the cystic fibrosis gene in the found 1 million nucleotide wrong region on chromosome 7, but here's my 3rd hint. Should we search for genes in this region that are similar to known genes responsible for secretion? Biologists used this 3rd hint, and bingo, they found that one of the genes in this region was similar to the ATP-binding proteins that act as transport channels responsible for secretion. To learn how biologists find similarities between genes, we will first learn how to play a simple game called the alignment game. The alignment game is a single-person game. I give you 2 strings, and your goal is to remove symbol from the strings in such a way that the number of points is maximized. I have to explain you how you can get point for playing the alignment game. You can either remove the first symbol from both strings, and in this case you get 1 point if there's the same symbol. You don't get any points if they're different symbol. Or you can remove first symbol from one of the strings, and in this case you also don't get any points. So let's try to play this game. In the beginning it makes sense to remove the first symbol from both strings. We'll get +1. Then another pair of identical symbol, another +1. And now symbols are different, so it doesn't make sense to remove them both, because we'll get 0 point. Maybe we should only remove C from the second string, and after we've done this, there is a possibility to remove 2 G's from both strings. We get another point. We continue, and finally, after playing this game, we get score +4. Do you think you can get score +5 playing this game? We also, after playing this game, we constructed something that is called alignment of 2 strings. Alignment of 2 strings is a 2-row matrix such that the first row consists of symbols of the first string in order, possibly interspaced with the space symbol. And the second row consists of the symbols of the second string, once again possibly interspersed with the space symbol. After we constructed the alignment, we can classify different columns in the alignment matrix as matches, or mismatches, or insertions. Insertions correspond to the case when we selected a symbol from the second string, and deletions that correspond to the case when we selected the symbol from the first string. And moreover, we can score this alignment by giving premium for every match. We will give premium +1, and penalty for every mismatch and every insertion and deletion that we denote as indel. In our case, we will use penalty -mu for mismatches and penalty -sigma for insertions and deletions or indels. For example, in our case, if mu equals 0 and sigma equal to 1, then we get alignment score equal to 1. So we define the alignment score as the number of matches minus mu, number of mismatches, and minus sigma, number of indels. And the optimal alignment problem is, given 2 strings, mismatch penalty mu and indel penalty sigma, find an alignment of 2 strings maximizing the score. We will be particularly interested in one particular score of alignment. We will define common subsequence as simply matches in an alignment of 2 strings. In this case, common subsequence is represented by AT-GT. And the longest common subsequence problem that we will be interested in is the following. Given 2 strings, we want to find a longest common subsequence of these strings. And of course, you have already recognized that to find longest common subsequence, we simply need to find maximum score alignment with these parameters mu equals 0 and sigma equals 0. Another classical problem in computer science is the edit distance problem. Given 2 strings, find the minimum number of elementary operations, insertions, deletions, or substitutions of symbols that transform one string into another. And of course, the minimum number of insertion, deletions, and mismatches in an alignment of 2 strings represents the edit distance. For example, if we want to find the edit distance between the strings editing and distance, we can construct optimal alignment of the string with appropriate scores. Here I showed matches, mismatches, insertions, and deletions. And to see that the edit distance problem is equivalent to the alignment problem, let's consider this alignment between editing and distance, and let's compute the total number of symbols in 2 strings. Obviously, the total number of symbols in two strings equal to twice number of matches, plus twice number of mismatches, plus number of insertions, plus number of deletions. I will take a liberty to rewrite this expression, and after I rewrote it, you will see that the first three terms correspond to the alignment score, and the last three terms corresponds to the edit distance. Therefore, minimizing edit distance is the same as maximizing the alignment score, which means that edit distance problem is just one particular version of the alignment problem. Let's now see how dynamic programming algorithm solves the edit distance problem. We start by considering two strings, A of length n and B of length m, and we will ask question, what is an optimal alignment of an I prefix of A, which is the first I symbol of A, and the J prefix of B, which are the first J symbols of B. The last column of an optimal alignment is either an insertion, or a deletion, or a mismatch, or a match. And please notice that if we remove the last column from the optimal alignment of the strings, what is left is an optimal alignment of the corresponding two prefixes. And we can adjust the score of the optimal alignment for I prefix and J prefix by adding +1 in the case of insertion, +1 in the case of deletion, +1 in the case of mismatch, and adding nothing in the case of match. Let's denote dij to be the edit distance between an I prefix and a J prefix, and in this case, this figure at the top of the slide illustrates the following recurrency. Dij equal to the minimum of the following four values: dij minus 1 plus 1, di minus 1j plus 1, di minus 1j minus 1 plus 1 in the case the last two symbols in the I prefix of A and the J prefix of B are different, and di minus 1 j minus 1 if the last symbol in I and J prefix are the same. Our goal now is to compute the edit distance dij between all I prefixes of string A and all J prefixes of string B. In the case of string editing and distance, we will construct 8 by 9 grid, and our goal is to compute all edit distances dij corresponding to all nodes in this grid. For example, for I and J equal to 4 and 4, how will we compute the corresponding distance dij? Let's start by filling distances di zeros in the first column of this matrix. It is easy, because indeed we are comparing an I prefix of string A against of 0 prefix of string B, and therefore these edit distances for I prefix will be equal to I. That's what's shown here. Similarly, we can easily fill the first row in this matrix. And now let's try to compute what will be the distance d11 corresponding to comparison of string consisting of a single symbol E with a string consisting of a single symbol D. There are three possible ways to arrive to the node 1, 1 from the nodes 0, 0, 0, 1, and 1, 0. Which one should be the way we will select to find the optimal edit distance? According to the previous recurrency, we should select the one of three directions that gives minimum value for dij, which is minimum of 2, 2, and 1, and therefore we arrive to node 1, 1 by diagonal edge. Let's keep this in memory that the right direction to arrive to the node 1, 1 was the diagonal direction. We will now try to compute the edit distance for the next node in the matrix, and in this case D21 is equal to minimum of D20 plus 1, D11 plus 1, and D10, which tells us that the optimal way to arrive to this node would be again by diagonal edge. We'll continue further, once again compare three values, and it turns out that the best way to arrive to this node will be by vertical edge. We'll continue further and we'll fill the whole second column in the matrix. Now let's continue with the third column. What about this node? For this node, D12 is equal to minimum of D11 plus 1, D02 plus 1, and D01 plus 1. And it is minimum of 2, 3, and 2. In fact, there are two optimal ways to arrive to this node, and in this case we show both of them by diagonal edge into this vertex and by horizontal edge in this vertex. We'll continue further, and slowly but surely we will fill the whole matrix. The edit distance pseudocode implements the algorithm we just discussed. It first fills in the first column and the first row of the dynamic programming matrix, and then it continues filling it up by computing the cost of moving to vertex ij using insertion, deletion, or mismatch, or match. Or in other words, exploring all possibility, moving to the vertex ij using vertical edge, horizontal edge, and diagonal edge. And then it finds out which of these possibilities results in the minimum edit distance. We now know how to compute the edit distance or to compute the optimal alignment, but filling in the entries in the dynamic programming matrix. But it doesn't tell us yet how to construct the alignment, two rows with first row representing the first sequence and the second row representing the second sequence. Here's an idea. Let's use the backtracking pointers that we constructed while filling in the dynamic programming matrix to reconstruct the optimal alignment between strings. We can start by noting that any path from 0, 0 to ij in the dynamic programming matrix spells an alignment of a I prefix of A with a J prefix of B. For example, let's start aligning the sequences, which means let's start traveling from the point 0, 0 to the point nm in our dynamic programming matrix. As soon as we move along diagonal edge, it will correspond to either mismatch or match. Then we'll continue using horizontal or vertical edges, and it will correspond to insertions or deletions. Then we will use, once again, diagonal edge. In this case, it is a match. And we'll continue by constructing the n alignment of two strings. Please note that the constructed path corresponds to distance 8 and is not an optimal alignment, because we know that the optimal alignment, our optimal edit distance is 5. To construct an optimal alignment, we will use the backtracking pointers by starting from the last vertex in this matrix, particularly from this vertex, where the edit distance is recorded as 5. Using backtracking pointers, we see that there are two possible ways to arrive to this last vertex. Let's arbitrarily choose one of them. One of them, these ways correspond to a mismatch and another correspond to insertion. So let's arbitrarily choose a mismatch edge. It will correspond to mismatch between J and E. Then from the previous point, there is only one way to move into this point, and it will correspond to an indel. We'll continue further, match, further, 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 and we will finally arrive to the initial point at the same time constructing the optimal alignment between two strings. The output alignment pseudocode implements this idea. We simply look at the backtracking pointers that enters in the node ij. If we arrive to the node ij by using a vertical edge, that we will simply output the one column of the alignment with A of I in the first row. If, on the other hand, it corresponds to a horizontal edge, we output a column with B of j in the second row. And if it corresponds to a diagonal edge, we output a column of alignment with A of I in the first row and B of j in the second row. It appears that we actually need to store all backtracking pointers to output the alignment, but this slightly modified pseudocode tells you that you can compute backtracking pointers by analyzing entries in the dynamic programming matrix and thus saving a little space. Edit distance is just one of many applications of string comparisons in various disciplines that range from analyzing internet pages to finding similar genes. We started this lecture from the example of gene hunt for cystic fibrosis, one of the first successes of the Human Genome Project. If you want to learn more about comparing genes, protein, and genomes, you may enroll into Coursera specialization called Bioinformatics, or you can read the book Bioinformatics Algorithm, the Active Learning Approach.
Hi, today we are going to revisit the knapsack problem, the problem that we already discussed in the greedy algorithms module. In this very first segment of this lesson, we will recall the definition of this problem as well as motivated study by providing a few examples of applying this problem in real life. Our first example is the following. Assume that you are given a time slot, say 2 or 3 minutes, and together with this time slot, you are given a set of TV commercials. For each commercial, you know its revenue and you know its duration, that is, length in minutes. And your goal is to maximize the revenue. That is, you would like to select some subset of your available TV commercials so that the total revenue is as large as possible, while the total length does not exceed the length of your available time slot. In our second example, you are given a fixed budget, and your goal is to purchase a number of computers so that to maximize their total performance. Again, we assume that a part of your input in this case is a set of available computers or machine, and for each machine you know its price and its performance. Both the considered two problems can be easily seen to be special cases of the following general problem known as the knapsack problem. In this problem, you are given a set of items together with the total capacity of the knapsack. For each item, you know its value and its weight. For example, the value of the green item here is 4, while its weight is 12. And your goal is to select a subset of items such that their total value is as large as possible, while their total weight is at most the capacity of the knapsack. In our case, the total capacity of the knapsack is equal to 15. There are two versions of the knapsack problem: fractional knapsack and discrete knapsack. So for the fractional version, which you're already familiar with, you can take any fraction of any item. While in the discrete version, for each item, you either take the whole item in your knapsack or you do not take it at all. So in turn, the discrete version has two variants also. So the first variant is knapsack with repetitions. So in this case, you are given an unlimited quantity of each item. While in the knapsack without repetitions, you are given just a single copy of each item. So we know already that the fractional knapsack problem can be solved by a simple greedy algorithm. Such an algorithm at each iteration just picks an element, an item, with the currently maximal value per unit of weight. This strategy, however, doesn't work for the discrete version of the knapsack problem. So instead of using greedy strategy, we will design a dynamic programming solution to find an optimal value. Now, let me give you a toy example. Assume that our input consists of a knapsack of size of total capacity 10 and 4 items shown on the slide. Then the optimal value for the knapsack without repetitions problem is equal to 46, and it can be obtained by taking the first item and the third item into your knapsack. At the same time, for the knapsack with repetitions problem, the optimal value in this case is equal to 48, and it can be obtained by taking 1 copy of the first item and 2 copies of the last item. Finally, for the fractional knapsack problem, the optimal value is equal to 48.5 and can be obtained by taking the first item, the second item, and the half of the last item. Let's also use this example to show that greedy algorithm fails for the discrete version of the knapsack problem. Recall that the greedy strategy for this problem is to first compute the value per unit of weight for each item. In our case, the value per unit of weight for the first item is equal to 5, for the second item it is equal to 4 2/3, for the third item it is equal to 4, and for the last item it is equal to 4 1/2. So the first item has maximal value per unit of weight, so we take it into our solution. The next available item with the maximal value per unit of weight is the second one, so we take it also into the solution. Now the remaining capacity is too small to add any other element. So this is our constructed solution, and it has weight, it has value 44, which is not optimal. We know it already. For example, here by replacing the second item by the third item, we will increase the total value. This actually means that taking an element with the maximal value per unit of weight is not a safe step. But by doing this, we can lose a possibility to construct an optimal solution. Right? So this means actually that we need some other algorithm to solve this problem optimally. And we will design such an algorithm based on the dynamic programming technique in the next video. In this video, we will design a dynamic programming solution for the knapsack with repetitions problem. Recall that in this problem, we are given an unlimited quantity of each item. This is the formal statement of the problem. We are given n items with weights W1, W2, and so on, Wn. And its values are V1, V2, and so on, Vn. By capital W, we denote the total capacity or the total weight of the knapsack. And our goal is to select a subset of items where each item can be taken any number of times, such that their total weight is at most capital W, while their total value is as large as possible. To come up with a dynamic programming algorithm, let's analyze the structure of an optimal solution. For this, consider some subset of items of total weight at most capital W, whose total value is maximal. And let's consider some element I in it. Let's see what happens if we take this element out of this solution. So what remains is some subset of items whose total weight is at most capital W minus Wi, right? So this is easy. What is crucial for us is that the total value of this remaining subset of items must be optimal. I mean, it must be maximal among all subset of items whose total weight is at most capital W minus Wi. Why is that? Well, assume that there is some other subset of items whose total weight is at most capital W minus Wi, but whose total value is higher. Let's then take the ith item and put it back to this subset of items. What we get actually is the solution to our initial problem of higher value. I mean, its total weight is at most capital W, and its value is higher than the value of our initial solution. But this contradicts to the fact that we started with an optimal solution, right? So such trick is known as cut and paste trick, and it is frequently used in designing dynamic programming algorithms. So let me repeat what we've just proved. If we take an optimal solution for a knapsack of total weight capital W and take some item I out of it, then what remains must be an optimal solution for a knapsack of smaller weight. So this suggests that we have a separate subproblem for each possible total weight from 0 to capital W. Namely, let's define value of W as the optimal total value of items whose total weight is at most W. This allows us to express value of W using the values for smaller weight knapsack. Namely, to get a solution, to an optimal solution for a knapsack of size of total weight W, we first take some smaller knapsack and an optimal solution for it and add an item I to it. So first of all, to be able to add an item I to it and get a knapsack of total weight W, we need this smaller knapsack to be of total weight at most W minus Wi. Also, when adding i's item to it, we increase its value by Vi. And the final thing is that we do not know which element to add exactly. For this reason, we just go through all possible n elements and items and select the maximal value. The maximal value of the following thing: value of W minus Wi plus Vi. Having a recurrent formula for value of W that we've just discussed, it is not so difficult to implement an algorithm solving the knapsack problem with repetitions. Recall that we expressed the solution for a knapsack through solutions for knapsacks of smaller weight. This means that it makes sense to solve our subproblems in the order of increasing weight. So we do this in the pseudocode. Initially, we set value of 0 to 0 just to reflect the fact that the maximal possible total weight of a knapsack, the maximal possible total value of a knapsack of weight 0 clearly equals 0. Then we go in a loop from W equal to 1 to capital W. And for each such W, we just compute the corresponding maximum as follows. We go through all items I such that Wi is at most W. And for each such item I, we see what happens if we take an optimal solution of for a knapsack of size W minus Wi and add an item I into it. Clearly, in this case, the total value is value of W minus Wi plus Vi, and the total weight is at most W. So this is a feasible solution for a knapsack of size of total weight W. So we check whether the resulting value is larger than what we currently have. And if it is, we update value of W. In the end, we just return value of capital W. So this algorithm is clearly correct because it just implements our recurrent formula, right? So in particular, this loop just computes the maximum from the previous slide. Now let's estimate the running time of this algorithm. It is not difficult to see that the running time is big O of n multiplied by capital W. Why is that? Well, just because we have two nested loops here. So this is the first loop and this is the second loop, right? The first one has capital W iterations, and the second one has n iterations. What happens inside the inner loop clearly takes just constant time. We conclude this video by applying our algorithm to the example considered a few minutes before. So in this case, we are given 4 items and a knapsack of total capacity 10. We are going to compute the optimal value for all knapsacks of size of total weight from 0 to 10. So, which means that it makes sense to store all these values just in an array. So, shown here on the slide. Initially, this array is filled by zeros, and we are going to fill it in with values from left to right. So the first non-obvious cell is 2. So this is the first weight for which we can add any item. So in this case, we can actually say that to get a solution for a knapsack of total weight 2, we can get a solution for a knapsack of total weight 0 and add the last element to it. This will also give us plus 9 to the value. So this is the only possible solution for this cell, so we do not even need to compute the maximum. So in this case, the value is equal to 9. So what about value of 3? So in this case, we already have a choice. We can either get an optimal solution for total weight 1 and add the fourth element to it, or we can get an optimal solution for a knapsack of size of total weight 0 and add the second element to it, whose value is 14. So among these two values, the second choice is better. It gives us a solution of value 14, so we write it in this cell. Now, for value of 4, there are already 3 choices. Let's consider them. So either we can take an optimal solution for a knapsack of total weight 2 and add the last element to it. So this is plus 9. Or we can take an optimal solution for a knapsack of total weight 1 and add the second item to it, so plus 14. Or we can take an optimal solution for a knapsack of total weight 0 and add the third item. So this is plus 16. Right? So in this case, we need to select a maximum among 16, 14, and 9 plus 9, which is 18. In this case, 18 is the maximal value, so we write it in this cell. So by continuing in the same manner, we can fill in the whole array and see that the last element is equal to 48, which justifies that the optimal value for this knapsack with repetitions problem is equal to 48. And also let me remind you that this optimal value can be obtained by taking 1 copy of this item and 2 copies of the last item. In the next lecture, in the next video, we will learn how to solve this problem when repetitions are not allowed. In this video, we will be designing a dynamic programming solution for the knapsack without repetitions problem. Recall that in this problem, we are given a single copy of each item. So this is also to remind you the formal statement of the problem. So we emphasize once again that we are not allowed to take more than a single copy of each item. Well, we already know that our previous algorithm cannot produce the right answer for our new variant, namely for the knapsack without repetitions problem. Well, this is simply because in our toy example, the optimal value for the knapsack with repetitions was 48, while the optimal value for the knapsack without repetitions was 46. So this means that if we just run our previous algorithm, it will produce an incorrect result. Still, it is important to understand where our algorithm or where our reasoning more generally fails for this problem. So once again, let's consider an optimal subset of items for a knapsack of total weight capital W, and assume for the moment that we know that it contains the nth element, that is, the last item. So we argue, well, similarly to the previous case, that if we take this item out of the current knapsack, then what we get must be an optimal solution for a knapsack of smaller weight, namely of total weight capital W minus Wn. So if we take this smaller solution and we add the nth item to it, we get an optimal solution for the initial knapsack of total weight capital W. Assume, however, that the optimal solution for the smaller knapsack already contains the nth item. This means that we cannot add another copy of the nth element to it, right? Because then the resulting solution will contain two copies of the nth element, which is now forbidden by the problem formulation. So this is why we need to come up with a different notion of a subproblem. So still, let's take a closer look at our optimal solution. It is not difficult to see that there are only two cases. Either it contains the last item or it doesn't contain it. Assume that it contains. And let's again take this nth item out of our current solution. So what is left? First of all, it is some solution for a knapsack of total weight capital W minus Wn. And it also uses only items from 1 to n minus 1. Because, well, we just took out the nth item, right? If, on the other hand, the initial optimal solution for the knapsack of total weight capital W does not contain the nth item, well, then it contains only items from 1 to n minus 1, right? Well, this simple observation will help us to get the right definition of a subproblem for this version of the knapsack problem. Well, on the previous slide, we argued as follows. Consider an optimal solution for a knapsack of total weight capital W. And there are two cases. Either it contains the last item or it doesn't contain. If it contains, we can take it out and reduce the problem for a smaller knapsack using only items from 1 to n minus 1. On the other hand, if it doesn't contain the nth item, then we reduce it to another case when the knapsack only uses items from 1 to n minus 1. In any case, we reduce the number of items, and in the first case, we also reduce the size of the knapsack, the total weight of the knapsack. We might continue this process and express the solution for all two subproblems through solutions to four sub-problems. If we continue in the same fashion, what we get somewhere in the middle is a solution for a knapsack of some weight that uses some first I items. Well, let's just use this as a definition of our subproblem. Namely, for any W from 0 to capital W and for any I from 0 to n, let's denote by value of W and I the maximal value that can be achieved by using only items from 1 to I and whose total weight is at most W, right? Then it is easy to express it through solutions for smaller subproblems. Once again, value of W and I is a subset, is the optimal value of a subset of the first I items whose total weight is at most W. So we know that in this optimal subset, either there is the ith item or the ith item is not contained in it. So there are two cases. So we need to select the maximum out of two cases. In the first case, if we take the ith item out, what is left is an optimal solution for the following problem. We are allowed only to use the first I minus 1 items, and the total weight should be no more than W minus Wi. So this is the first term under the maximum. In the second case, if the ith item is not used in an optimal solution, then we just know that the optimal solution is the same as for the knapsack of total weight W, using only the first I minus 1 items. So we managed to express the solution for our problem through solutions for smaller subproblems. And this is probably the most important thing in designing dynamic programming algorithms. We now turn our recurrent formula into a dynamic programming algorithm. As usual, we start from initialization. Namely, we first set all the values of 0j to 0 for all j, and all the values of w0 to 0. Well, this just expresses the fact that if we have no items, then the value is 0. Or if we have the knapsack of total weight 0, then the total value is also 0, of course. Then recall, now we need to somehow compute all other values of wi. Recall that we expressed value wi through values of smaller w and I minus 1 and w and I minus 1. This means that we always reduce the problem from wi to something with smaller number of items, to I minus 1. This actually helps us to understand that it makes sense to gradually increase the number of available items, and that this is why we have in this pseudocode an outer loop where I goes from 1 to n. When I is fixed, we will compute all the values of wi. So for this we also go from w equal to 1 to capital W and do the following. So now I and w are fixed. We need to compute value of wi. First, we just check what is the value of what is the solution for the subproblem when we use the knapsack of the same weight w, but we only use the first I minus 1 items. This is implemented as follows. We first just assign value of wi to value of wi minus 1. Then we need to check whether we can improve this value by using the ice item. First of all, we can only do this if the weight of the ice item does not exceed the weight of the current knapsack, which is just w. So if it doesn't exceed, we see what happens if we take an optimal value for the knapsack of total weight w minus wi that is filled only by elements from 1 to I minus 1 and add the ice element to it. If this gives a larger value than we currently have, we update value of wi. So in the end, we just return the value of capital W and n, because this is the solution to our initial problem. So this is the solution for a knapsack of size capital W that uses just all the n items, right? Now, so it is clear that this algorithm is correct just because, well, it directly implements the recurrent formula that we already discussed. So let's analyze its running time. It is not difficult to show again that its running time is actually the same. It is again n multiplied by w. Well, this is again just because we have two loops here. So this is the first loop with n iterations, and this is the inner loop with w iterations, and what is going on inside only takes some constant time. Now let's apply the algorithm that we've just designed to our toy example. Recall that we need to store the values of all subproblems for wi for all w from 0 to 10 and all I from 0 to 4 in our case. For these purposes, it is natural to use a two-dimensional table or two-dimensional array. You can see such a two-dimensional array on the slide already filled in. So here we have I, so all the rows of our columns are indexed by all possible values of I, and all the columns are indexed by all possible values of w. Right? We start by initializing the first row and the first column of this table by zeros. That is, we fill this row by zeros, and we fill this row, this column by zeros also. Then we start filling in this table row by row. That is, we first fill in this cell, then this cell, then this cell, then this cell, and so on. So we go like this. So we first fill in this row, then fill in this row, then fill in this row, and then fill in this row. So the resulting value 46 is actually the answer to our initial problem. Now let me show you how some particular value, just to illustrate, let me show you how some particular value in this table was computed. For example, consider this cell. So formally, this is value of 10 2, which means that this is an optimal value of a knapsack of total weight 10 that only uses the first 2 items. So assume that we don't know what to put here. So we just need to compute it right now. So let's argue as well as we did before. So this is a knapsack of total weight 10 that uses only the first 2 items. Well, we then say that the second item is either used or not. So if it is not used, then this is the same as filling in the knapsack of total weight 10, just using the first item. And we already know this value because it is in the previous row. So this is value 10.1. Right? So the value in this case is 30. On the other hand, if the second item is used, then if we take it out, what is left is an optimal solution for a knapsack of total weight 10 minus 3, because 3 is the weight of the second item, which means that it is an optimal solution for a knapsack of size 7, of total weight 7, that only uses the first, that is only allowed to use the first item. Also, if we add this item to, if we add the second item to this solution, we get 30 plus 14, which is much better than without using the second item, right? So that's why we have 44 here. And also for this reason, we fill this matrix row by row. So note that when we need to compute the value of this cell, we already have computed the value of these 2 cells. So that's why we fill our matrix exactly row by row. Now, let me use the same example to illustrate an important technique in dynamic programming, namely reconstructing an optimal solution. By reconstructing an optimal solution in this particular problem, I mean finding not only the optimal value for the knapsack of size of total weight 10, but the subset of items that lead to this optimal value itself. Well, for this, we first create a Boolean array of size 4. In this array, we will mark for each item whether it is used in an optimal solution or not. Now, what we're going to do is to backtrace the path that led us to the optimal value 46. In particular, let's try to understand how this value 46 was computed. Well, first of all, 46 is formally value of 10.4. That is, this is the optimal value for a knapsack of total weight 10 using the first 4 items. We argued that the 4th item is either used or not. If it is not used, then this value is the same as the value 10.3, which is shown here. That is the value of the knapsack of the same weight using the first 3 items. If, on the other hand, it is used, then what is left must be an optimal solution for a knapsack of size 10 minus 2, which is 8, that uses also the first 3 items. Well, this value is already computed. It is 30, so we need to compute the maximum among 30 plus 9, because, well, the value of the last item is 9, and 46. In this particular case, the maximum is equal to 46, which means that we decided at this point not to use the last item, right? So we put 0 into our Boolean array to indicate this, and we move to this cell. Again, let's try to understand how this value was computed. It was computed as the maximum value of two numbers which depend on the following values. So either we do not use the third item, then it is the same as the value of this cell, or we use the third item. In this case, what remains is the knapsack of size of total weight 6, and using the first two items, and its value is 30, plus the weight of the third item, which is 16. In this particular case, 30 plus 16 is larger than 44, which means that this value of 46 was computed using this value. This in turn means that we decided to use the third item. Let's mark it by putting 1 into our Boolean array. Now we stay in this cell and we try to understand how it was computed. It was computed as the maximum over this 30 and this 0 plus 14, right? In this case, the first value is larger, so we move to this cell and we mark that we decided not to use the second item. Okay, and finally we realize that we arrived at this value 30 from the left upper corner, right? So this way we reconstructed the whole optimal solution. Once again, we backtraced the path that led us to the optimal value. Here, what is shown here is that we decided to use the first item and the third item. So let's check that it indeed gives us the optimal value of 46. So indeed, if we compute the sum of the weights of the first and the third item, it is 10, and while the total value is 30 plus 16, which is 46 indeed. And as I said before, this technique is usually used in dynamic programming algorithms to reconstruct the optimal solution. We conclude this lesson with a few important remarks. The first remark is about the trick called memoization. Usually when designing a dynamic programming algorithm, you start with analyzing the structure of an optimal solution for your computational problem. You do this to come up with the right definition of a subproblem that will allow you to express the solution for a subproblem through solutions for smaller subproblems. So when you write down this recurrence relation, you can actually transform it to an either iterative algorithm or a recursive algorithm. The corresponding iterative algorithm just solves all subproblems, going from smaller ones to larger ones. And for this reason, it is sometimes also called a bottom-up algorithm. On the other hand, the recursive algorithm to solve a subproblem makes recursive calls to smaller subproblems. And for this reason, it is sometimes called a top-down approach. Well, if you implement a recursive algorithm straightforwardly, it might turn out to be very slow because it will recompute some values many times, like with Fibonacci numbers, for example. However, there is a simple trick, and it is called memoization, that allows you to avoid recomputing many times the same thing. Namely, you can do the following. When solving some subproblems, right after solving it, you store its solution into a table, for example. And when you need to solve when you make a recursive call to solve some subproblem, before trying to solve it, you check in a table whether its solution is already stored. And if its solution is already in the table, which means that it was already computed, then you just return it immediately. So this recursive call turns out to be just a table lookup. So this is how a recursive algorithm with memoization works. Let's see how a recursive algorithm with memoization for the knapsack problem looks like. For simplicity, let's assume that we're talking about the knapsack with repetitions. In this case, we need to compute our subproblem for a knapsack of size W is just the optimal value for the knapsack of total weight W. So we compute it as follows. We compute it by a recursive procedure. First of all, we check whether its solution is already in a hash table. So we use hash table to store pairs of objects. So for weight W, we store value of W if it is already computed. If it is already in the table, we return it immediately. Otherwise, we just compute it and we make recursive calls to compute the values for the subproblem on W minus Wi. Okay, and when the value is computed, we just store it in our hash table. Right? So this way we use memoization by storing this in the hash table to avoid recomputing the same thing once again. So once again, an iterative algorithm solves all subproblems going from smaller ones to larger ones, right? And eventually solves the initial problem. On the other hand, the recursive algorithm goes as follows. So it starts from the initial problem and it makes recursive calls to smaller sub-problems. Right? So in some sense, an iterative algorithm and a recursive algorithm are doing the same job, especially if we need to solve just all the range of sub-problems. However, a recursive algorithm might turn to be slightly slower because it solves the same subproblems on one hand. On the other hand, when making a recursive call, you also need to put the return address on stack, for example. So a recursive algorithm has some overhead. There are, however, cases when you do not need to solve all the subproblems. And the knapsack problem is a nice illustration of this situation. So imagine that we are given an input to the knapsack problem where all the weights of n items together with the total weight of the knapsack are divisible by 100, for example. This means that we are actually not interested in subproblems where the weight of the knapsack is not divisible by 100. Why is that? Well, just because for any subset of items, since all the weights of items is divisible by 100, their total weight is also divisible by 100. So in this case, an iterative algorithm still will solve just all the range of subproblems, while a recursive algorithm will make only those recursive calls that are actually needed to compute the final solution. So it will make only recursive calls to subproblems whose weight are divisible by 100. The final remark of this lesson is about the running time. So as you remember, the running time of both algorithms that we designed in this lesson was big O of n multiplied by W. And this running time looks like polynomial. However, it is not, and this is why. So consider, for example, the following input. Assume that the total weight of the knapsack is as shown on the slide. This is a very huge number, roughly 10 to the 20. 20 digits of decimal representation. At the same time, the input size is really tiny, just 20 digits, right? So this is not gigabytes of data, just 20 digits, but on this input already, our algorithm will need to perform roughly 10 to the 20 operations, right? This is really huge. For example, we cannot do this on our laptops. And this is because to represent the value of W, we only need log W digits, right? So in case of the knapsack problem, our input is proportional not to n plus W, but to n plus log W. Okay, and if you represent the running time in terms of n and log W, then you get the following expression, n multiplied by 2 to the log W, which means that our algorithm is in fact exponential time algorithm. Put it otherwise, it can only process inputs where W is not large enough, is roughly less than 1 billion, for example. Okay, and in fact, we believe that it is very difficult to construct an algorithm that will solve this problem in polynomial time, in truly polynomial time. In particular, we will learn later in this specialization that this problem is considered to be so difficult that for solving the knapsack problem, for example, in polynomial time, one gets $1 million. Hello, and welcome to the next lesson in the dynamic programming module. In this lesson, we will be applying the dynamic programming technique for solving a wide range of problems where your goal is to find an optimal order of something. We will illustrate this technique by solving the so-called placing parentheses problem. In this problem, your input is an arithmetic expression consisting of numbers or digits and arithmetic operations, and your goal is to find an order of applying these arithmetic operations that maximizes the value. You specify this order by placing parentheses, and that's why the problem is called placing parentheses. As usual, we start with problem overview. Consider the following toy arithmetic expression: 1 plus 2 minus 3 times 4 minus 5. In this case, we have 5 digits and 4 arithmetic operations, and we would like to find an order of applying these 4 arithmetic operations to maximize the value of this expression. So when the order of operation is fixed, you do the following. You take the first operation, you take 2 adjacent digits, and you apply these operations. For example, if your operation is multiplication in this case, so then 2 digits are 3 and 4, so you multiply 3 and 4, you get 12, and you just replace 3 times 4 by 12. You then take the next operation, apply it also, and replace two numbers and the arithmetic sign by this result, and you proceed in a similar fashion. In the end, you get a single number, and your goal is to find an order that guarantees that this number is as large as possible. You can specify an order just by placing a set of parentheses in your expression. For example, if you would like to apply all your 4 operations just from left to right, you place the parentheses as follows. In this particular case, we compute the result as follows. So we first compute 1 plus 2, this is 3. We then subtract 3 from the result, this gives us 0. We then multiply the result by 4, this is still 0. And finally we subtract 5, so this gives us minus 5. And this is actually non-optimal because, for example, there is a better order. In this case, we first multiply 3 and 4. This gives us 12. We then subtract 5. This gives us 7. Then we go to compute the sum of 1 and 2. This gives us 3. So when the final operation is subtraction, we subtract 7 from 3. This gives us minus 4. So in this case, the order of applying operations was the following. So we first compute the product of 3 and 4, so this is the first operation. We then subtract 5, this is the second operation. We then compute the result of 1 plus 2, so this plus is the third operation, and this minus is the fourth operation, the last one. It is not difficult to see that the optimal value in this case is equal to 6. And it can be obtained as follows. You first subtract 5 from 4. This gives you minus 1. You then multiply it by 3 and you get minus 3. You then compute the sum of the first 2 digits. This is 1 plus 2 and it is equal to 3. Finally, you subtract minus 3 from 3. This is the same as 3 plus 3. It is equal to 6. Well, you might find the result as follows. You just go through all possible orders. Let's see how many different orders are there. Well, there are 4 arithmetic operations in this case. So you can choose any of the 4 possible arithmetic operations to be the first one. You can choose any of the 3 remaining operations to be the second one, and you can select any of the 2 remaining operations to be the third one, and the last one is unique. It is the only remaining operations. So in total there are 4 by 3 by 2 by 1 different orders. This is equal to 24, and you can just enumerate all of them, write them down, compute an answer for each of these orderings, and select the maximal value. However, our method of going through all possible orderings does not scale well, and this is why. Consider the toy example shown on the slide. In this case, we have 6 digits and 5 arithmetic operations. This example will require us to go through all possible 120 orderings. So just because there are 5 operations, so any of 5 of them can be the first one, any of the remaining 4 of them can be the second one, and so on. So this is 5 by 4 by 3 by 2 by 1, which is equal to 120. This is already not so easy to do this by hand. I mean, to go through all possible such orderings. Well, this is not easy, but we can teach a computer to do this, right? So we can implement an algorithm that goes through all possible orderings. However, in general, this algorithm will perform roughly n factorial steps, where n is the number of arithmetic operations. For exactly the same reason, if you have n arithmetic operations, then any of them can be the first one. Any of the remaining n-1 operations can be the second one, and so on. So this is n times n-1 times n-2, and so on. This is equal n factorial. And n factorial is an extremely fastly growing function. For example, 20 factorial already equals roughly 2 times 10 to the 18. This means that if you implement such an algorithm, it will not be able to compute the maximal value of an expression consisting of just 20 digits in a reasonable time, even in 1 year, not to say about 1 second. Which means, as usual, that we need another algorithm. As you might have already guessed, we will use dynamic programming to design a more efficient algorithm. In the meantime, you might want to check your intuition by trying a few possible orderings to perform in this small expression, and by using our in-video quiz. As usual, we start designing our dynamic programming algorithm by defining a subproblem in a way that allows us to solve a subproblem by solving smaller subproblem. As we said already, this is probably the most important step in designing dynamic programming solutions. So before doing this, we define our problem formally. So the input consists of n digits, d1, d2, and so on, dn, and then -1 operations between them, which we call op1, op2, and so on, opn. Each operation is either summation, subtraction, or multiplication. And our goal is to find an order of applying these operations so that the value of the resulting expression is maximized. As we discussed already, we can specify this order just by placing parentheses into our expression. We start building our intuition by reconsidering our toy example. So assume that the multiplication is the last operation in some optimal ordering, in an ordering leading to an optimal value in this toy example. Well, this means that in this expression we already have 2 pairs of parentheses. And our goal is to parenthesize the initial sub-expression and the second sub-expression so as to maximize the value. This means that it would be good for us to know what is an optimal value for the first sub-expression and for the second sub-expression, right? And in general, if you have an expression and if you select an arithmetic operation, which is the last one, then it splits your initial expression into 2 sub-expressions, right? And for both of them, it would be good to know an optimal value. And in turn, each of these 2 sub-expressions are split into 2 sub-expressions by the last arithmetic operations, and so on. So this suggests that a good subproblem in our case would be to find an optimal value for any sub-expression of our initial expression. So we've just realized that it would be good to know the optimal values for all sub-expressions of our initial expression. What do we mean, however, by saying optimal values for all sub-expressions? Assume, for example, that we need to compute the maximal value for the sum of two sub-expressions, sub-expression 1 and sub-expression 2. Well, this obviously means that we would like this sub-expression to be as large as possible and this sub-expression to be as large as possible. If, on the other hand, we would like to compute the maximal value of sub-expression 1 minus sub-expression 2, well, this means that we would like sub-expression 1 to be as large as possible, while we would like to be the value of sub-expression 2 to be as small as possible, right? Just because we compute sub-expression 1 minus sub-expression 2. This suggests that knowing just the maximal value for each sub-expression would not be enough. And this usually happens when designing a dynamic programming solution. This also suggests that instead of computing just maximal value, we will maintain both the maximum value and the minimum possible value for each sub-expression. Let's illustrate this reasoning once again on our previous toy example. So in this case, we are maximizing the product of two small sub-expressions. In this case, these two sub-expressions are so small that it is not difficult to compute their minimal and maximal values. For example, for sub-expression 5 minus 8 plus 7, the minimum value is minus 10 and the maximal value is 4, right? At the same time, for the second sub-expression, 4 minus 8 plus 9, the minimum value is minus 13, while the maximum value is 5. Right? Now we would like to parenthesize both sub-expressions so that their product is maximal. Well, it is not difficult to see that in this case, the optimal way to do this is to take the minimal values of both sub-expressions. Right? So this will give us minus 10 multiplied by minus 13, which is equal to 130, right? Which is much larger than the product of the maximal values of these two sub-expressions, which is 4 by 5, which is 20 in turn. Okay, we are now ready to write down the recurrent relation for our sub-problems. Before this, let's formally define E of ij to be the sub-expression of our initial expression, resulting by taking digits from I to j and all operations between them. Then our goal is to compute the maximum value of this sub-expression, which we denote by capital M of ij, and the minimum value of this sub-expression, denoted by M of ij. Okay, consider our initial sub-expression from I to j, and assume that we would like to compute one of the extreme values of this sub-expression. I mean, either the minimum or the maximum. Well, we know that in any ordering for this sub-expression, there is some last operation, say OPK. So this operation splits our initial sub-expression into two sub-expressions. Namely sub-expression ik and sub-expression k plus 1j, right? So to compute the maximum value, we just go through all possible such case from I to j minus 1 and through all possible extreme values for two sub-expressions. I mean, either we apply operation k to the maximum values of these two sub-expressions, or we apply operation k to minimum values of these two sub-expressions, or we apply it to the maximum value of one sub-expression and the minimum value of another, or vice versa. Right? To compute the maximum value of sub-expression ij, we just select the maximum among all these possibilities, while to compute its minimum value, we simply select the minimum among all such possibilities. We now convert our recurrence relation into a dynamic programming algorithm. We start by implementing a procedure which computes the minimum and the maximum value of the sub-expression ij through optimal values for for smaller sub-expressions. So the procedure is called min and max of ij. So we first declare two variables, max and min. Initially min is equal to plus infinity, max is equal to minus infinity, or to very large number and to very small number. Then we go through all possible values of k between I and j minus 1. I mean, we just go through all possibilities of splitting our sub-expression ij into two sub-expressions from I to k and from k plus 1 to j. When such a splitting is fixed, we compute four possible values. I mean, applying OPK to either to maximum values of this sub-expression or to minimum values, or to maximum and minimum value, or to minimum and maximum value. When such two values are computed, we just check whether one of them can improve our minimum or maximum value. If it improves, we update the min or max variable. Finally, we return the minimum value and the maximum value for our sub-expression. Our recurrent relation expresses the solution for an expression ij through solutions to smaller sub-expressions. What do we mean by saying smaller? Well, we mean just that they are shorter, right? So once again, when we compute the value for a sub-expression ij, we rely on the fact that all the values for shorter sub-expressions are already computed. This means that our algorithm needs to compute the solutions for all subproblems in order of increasing length, namely in order of increasing value of j minus I, right? So for this problem, we have roughly quadratic number of subproblems. Namely, our subproblem iij is parameterized by the value of I and j, which in turn range from 1 to n. Right? So it makes sense in this case to store the values for all subproblems in a two-dimensional table of size n by n. Recall also that we need to solve our subproblems in the order of increasing value of j minus 1. We can do this just by going through all subproblems in an order shown on the slide. So why this order? Well, this is simply because it goes through all possible values of ij in order of increasing j minus y as required. So let's take a look. On this diagonal, we have all the cells where j minus I is equal to 0. Right? So the first cell here is 1, 1, the second cell is 2, 2, the third cell has indices 3, 3, and so on. We then proceed to this cell. Here I is equal to 1, j is equal to 2, so the difference is 1. We then proceed to this cell. This is the cell 2, 3, with the difference 1 again. We then proceed to this cell, which is 3, 4, and so on. So on this cell, on this diagonal, we have all the cells ij where I minus j is equal to 0. On this diagonal, we have all cells ij where j minus I is equal to 1. For this cell, for this diagonal, this difference is equal to 2. For this diagonal, this difference is equal to 3, and so on. So the resulting value for our initial subproblem will be computed as the value of the last cell. Right? Because this cell corresponds to the initial sub-expression from 1 to n. Now everything is ready to write down an algorithm. In the algorithm, we will maintain two tables, M and capital M. The first one for storing the minimum values for all sub-expressions, and the second one for storing the maximum values for all sub-expressions. We start by initializing these tables as follows. So when sub-expression contains just one digit, which means that when j is equal to I, then there is nothing actually to minimize or maximize because there are no operations. So there is no order on operations. So because of that, we just initialize the main diagonals of both these tables with the corresponding digits. This is done in the following loop. So m of ii and capital M of ii is equal just to di. Then we go through all possible subproblems in order of increasing size. And this is done as follows. We gradually increase the parameter s from 1 to n minus 1. This is done in the following loop. When s is fixed, I goes from 1 to n minus s, and j is computed as I plus s. This is done to go through all possible pairs ij, such that j minus I is equal to s. Right? When I and j are fixed, we call the procedure min and max to compute the minimal and maximal value of the sub-expression ij. Right? So finally, we return the value of capital M of 1n as the result for our initial problem, because this sub-expression 1n corresponds to our initial problem, containing all digits from 1 to n. Okay, so the running time of this algorithm is cubic, namely big O of n cubed. And this can be seen by noting that we have two nested loops. So the first one with n minus 1 iterations, the first one, the inner one is with n minus s iterations, which is at most n. And also inside these two loops we have a call to min and max procedure. The running time of min and max procedure is proportional to j minus I, which is also at most n. So the running time of our algorithm is at most big O of n times n times n, which is n cubed. This slide shows an example on how tables M and capital M look like if we run our algorithm on our toy example, namely expression 5 minus 8 plus 7 times 4 minus 8 plus 9. Let's just go through this example step by step. So we start by filling in the values on the main diagonal in both matrices. So this is 5, this is 8, this is 7, this is 4, 8, 9. So this corresponds to sub-expression consisting of just one digit. So there is nothing to maximize or minimize. So we do this the same for the capital M matrix. We then proceed to the second diagonal. Well, we put minus 3 here, and this corresponds to this sub-expression. Again, in this case, there is just one operation, so there is nothing to minimize or maximize here, because, well, there is just one order when we have just one sign. So we put minus 3 here. This corresponds to the problem, to the subproblem 1, 2. Let me put all the indices here, by the way. Then we proceed to the cell 2, 3, which corresponds to this subproblem. Again, there is nothing to maximize or minimize, so we continue in the same way. In this case, it is not so interesting. And then we proceed to the third diagonal, namely to this cell. So this corresponds to the sub-expression 1, 3, which consists of 3 digits and two operations, minus and plus. So we know that one of them is the last operation in an optimal order when computing the minimum value, for example. So assume that this is minus. This will split this sub-expression into two sub-expressions, 5 and 8 plus 7. So for both these sub-expressions, we already know their maximum and minimum values. So once again, this sub-expression is 1, 1, corresponds to 1, 1. This sub-expression corresponds to 2, 3. So from second to third digits and from first to first digit. So we know that for the first sub-expression, we know already its minimum value, it is here, and its maximum value, it is here. So for the second sub-expression, we already know its minimum value, it is here, it is 15, and then its maximum value, it is also 15. So by going through all possible pairs of this maximum and minimum values, in this case they are all the same, we compute the minimum value, which is just 5 minus 15, it is minus 10. However, this was only the first case of splitting this sub-expression into two sub-expressions. Another possibility would be the following. So we can split it into the following two sub-expressions. So this corresponds to 1, 2, and this corresponds to 3, 3. Right? So for 1, 2, we know its minimum value, it is -3, and its maximum value, it is also -3. For 3, 3, we know its maximum value, it is here 7, its minimum value and its maximum value. Right, so then we can compute -3 plus 7, which gives us just 4. So for the maximum value of the sub-expression 1, 3, we select 4. For the minimum value, we select -10. So we proceed filling in this table in a similar fashion. So we then put 36 here in this cell, then -28 in this cell, and in parallel we put 60 here, 20 here, and so on. So in the end we see the value 200 here, and this is the maximum value of our initial expression. This still doesn't give us the optimal order itself, but we will be able to reconstruct it from these two tables. Now we are sure that the maximum value of our initial expression is 200, and we will find out the optimal ordering or the optimum parenthesizing in a minute. In this last video of this lesson, we show a method of reconstructing an actual solution from two tables computed by our dynamic programming algorithm. Okay, here on the slide we see two tables, M and capital M, computed by our dynamic programming algorithm, which contain minimal and maximal values respectively for all possible sub-expressions of our initial expression. Let me first put the indices for all the rows and columns of these two matrices, as well as numbers for our initial digits. Well, in particular, we see by reading the contents of this cell, capital M of 1, 6, that the maximal value of our initial expression is equal to 200. And our goal is to unwind the whole solution, I mean parenthesizing of the initial expression from these two tables. So our first goal on this way is to understand from which two sub-expressions of the initial expression the value 200 was computed. Well, let's see. When computing the value for the maximal value for sub-expression 1, 6, we tried all possible splittings of the expression 1, 6 into two sub-expressions. Well, let's just go through all of them. The first possibility is to split it into two sub-expressions, 1, 1, which corresponds just to the first digit, which is just 5, and sub-expression 2, 6 with a minus sign between them, right? So for both these two sub-expressions we already know minimal values and maximal values. Well, let me mark them. So this is the minimal value for the sub-expression 1, 1. This is the maximal value for sub-expression 1, 1. For 2, 6, this is the minimal value, minus 195, and this is the maximal value, 75. So we would like to maximize this sub-expression 1 minus sub-expression 2, which means that we would like the first sub-expression to be as large as possible and the second sub-expression to be as small as possible. Well, this means that we need to try to take the maximal value of the first sub-expression, which is 5, and the minimal value of the second sub-expression, which is minus 195. Well, we see that in this case 5 minus 195 is the same as 5 plus 195, which equals exactly to 200, right? Which allows us to conclude actually that the value 200 can be obtained just by as follows. So we subtract the minimum value, which is minus 195 of the second sub-expression from 5, right? So we restored the last operation in an optimal parenthesizing of the initial expression. However, we still need to find out how to obtain minus 195 out of the second sub-expression. Well, let's do this. Okay, so we need to find the minimum, how the minimum value of the sub-expression 26 was obtained. Well, there are several possible splittings, once again, of the sub-expression 26 into two smaller sub-expressions. The first of them is to split 26 into 2, which just corresponds to the digit 8 plus 36. Well, in this case, we would like the value to be as small as possible, and our sign is plus in this case, which means that we would like the value of sub-expression 2 to be as small as possible, and the value of sub-expression 36 also to be as small as possible. And we already know these values, they are in our tables. So the minimal value of sub-expression 2 is 8, while the minimum value of sub-expression 36 is minus 91, right? So we see that the sum of these two values is not equal to minus 195, right? Which means that plus is not the last operation in the optimal parenthesizing that gives the minimum value of sub-expression 26. Right, so let's check the next one. Another possibility to split the sub-expression 26 is the following. We split it into sub-expression 23 times sub-expression 46. Right? So once again, we would like to find the minimum value of sub-expression 26. Well, let's see just all possibilities. The minimum value of sub-expression 23 is 15. Its maximal value is also 15. As to sub-expression 46, its minimum value is minus 13. Its maximal value is 5. And we would like the product of these two values to be as small as possible. Well, it is not difficult to see that if we take just 15 and multiply it, which is the minimum value of sub-expression 23, and multiply it by the minimum value of the sub-expression 46, which is minus 13, then we get exactly minus 195. And this in turn allows us to conclude that to get minus 195 from the sub-expression 26, we can do as follows. We can first compute the sum of 8 and 7, this gives us 15, and then to multiply it by the result of the second sub-expression. Well, now it remains to find out how to get minus 13 out of this sub-expression 46, but in this small example, it is already easy to get minus 13. Well, we just first compute the sum of 8 and 9, and then subtract it from 4, right? So this way, we reconstructed the whole solution. I mean, an optimal parenthesizing or an optimal ordering of our arithmetic operations, leading to this value to this maximal value 200. Let's just check it once again, that our parenthesizing leads to the value 200 indeed. So we first compute the sum of 8 and 9. This gives us 17. We then subtract 17 from 4, and this gives us minus 13. We then compute the sum of 8 and 7. This gives us 15. We multiply 15 by minus 13. It gives us minus 195. And finally, we subtract this number from 5, and we get 200 indeed. So we reconstructed the whole solution. In general, I mean, for an expression consisting of n digits and n minus 1 operations, the corresponding algorithm makes roughly quadratic number of steps, because it needs to reconstruct n minus 1 operations, I mean an order of n minus 1 operations, going from last one to the first one, and for each operation it potentially needs to go through all possible splittings into two sub-expressions, and this number is at most n. So the running time is big O of n times n, which is big O of n squared. And this technique is quite general. It applies in many cases in the dynamic programming algorithms.